Hello?
Good morning, everyone. Good morning. Hello. Yeah, that's right. Woo! Good morning, everyone. Yeah. Nice to see you all back in person. So, my name is Martin Brown. I'm one of the board members for the GNU Radio Project. I'm not the president of the GNU Radio Project, who should be giving the opening, his name is Derek Cazell. Most of you will probably know him. Very, very unsadly, he could not make it due to visa issues, unfortunately. So I'll give you a pro-life tip. If you need a visa in the United Kingdom, make sure to not align it with like a major state event, like it delays things, and you might not be able to join this conference. It's so great to see you all back in real life. Like, for example, I couldn't actually fly out last year, where there was a travel ban, and then before it was virtual. So this is like the first, proper real life conference since the pandemic. And yeah, I'm very, very glad to be here. We're also back in DC. We didn't really start out in DC, but like a lot of the first conferences were all in DC. So yeah, there's some good memories. Anyway, I have a couple of organizational things to talk about. So first of all, like I said, I'm part of the board, like the sort of the project lead. I'm not taking any credit whatsoever for this conference though, because we have a fantastic organizers team, like amazing work that like a lot of volunteers have put in. Like you have no idea, like countless hours, like those guys have put into this conference over the last year, probably. I don't know. So first of all, I'd like to give a huge round of applause to those guys for us to be able to be back in person again. So huge round of applause for the organizers. All right, so I'm just going to give you a couple of pointers how you get through this conference. So yeah, this is the date, I guess. Yeah, that's right. All right, so we have, as usual, a 5-day conference where there's 4 days of presentations, and like the fifth day is sort of hands-on. And the schedule for the hands-on is not set in stone yet. And the last conference where I was at in Huntsville, the program for that Friday evolved during the week, and in the end it was amazing. We had like a huge amount of like very, rich, what's what I'm looking for, workshops that where we sort of got together and talked about technical stuff. And we're hoping this is going to happen again this week. Did I miss anything for Friday, Mark? That's about right? Okay. By the way, Mark, also fellow member of the board, sitting here at our, broadcasting station. Yeah, and very important, Wednesday night, the evening social. I'm hoping to see a lot of you there. I mean, I'm hoping to see a lot of you around this week, of course. But like evening social is like extra nice. So yeah, we're all looking forward to that. Where's the evening social? I'm sorry, I should know this. Okay, Penn Social. All right, and it's almost walkable, but you can also take an Uber, like kind of thing. Not very far from here. Perfect. All right. So yeah. So like I said, Monday through Thursday we have talks from 9 to 5. Except on Wednesday, I think there's some breakouts going on. There's a lot going on at this conference. So there's the talks. There's also the exhibit hall. It's like over there. All of our sponsors have stuff. Which they're showing off, and there's workshops. So yeah, the workshops have their own schedule, and you can find them on the schedule website. So all the workshop rooms are on this floor, and they're all like that direction. So there's I don't know, forgotten they call like something like South America or whatever, and they're easy to find. And there's also like an interactive map outside. Yeah, and then there's the Capture the Flag challenge, always like a highlight at this conference. Starts after the keynotes. Actually, Clayton, who's running the CTF, will actually. Clayton? Are you here? Can you raise your hand? Oh, perfect. Thank you. So yeah, he will be saying a few words on that, so I can keep that short. Now we have a chat server. Like this is not a conference thing. This is something that we have going all year round. Our GNU Radio chat server, chat.gnuradio.org, based on Matrix. Open source, powered by open source. But during the conference, I still recommend you join this channel. It's very useful to sort of coordinate, and also like if you have like discussions on the current presentation, we prefer you type them in chat than actually speak to one another, just so we can keep the noise down here. But after the conference, we strongly recommend you, and we invite you to stay on that chat server with us, because like a lot of people are there, and you can, ask questions all year round and see if there's like-minded folks working on similar things. Now we have this is like a hybrid-ish, not really a hybrid conference, but we have like this virtual element. So you could sign up as a virtual participant. Obviously, none of you did that because you're here in real life. But like all of this is being streamed out to YouTube, and there is a virtual registration that you could get. And for those people, like we can't offer that much for virtual participants because we can't send them stuff or whatever. And the YouTube stream is available for everyone who has access to YouTube. But we have virtual exclusive apparel, which you can, I don't know, where do you get that? Josh, like where do you get this virtual, if you got like a registration? Oh, got it. Okay, Marcus, just for those who are listening virtually, Marcus Müller just says they're on our Spreadshirt shop. All right, Wi-Fi, okay, if you haven't figured that out yet. Hilton Honors Meeting is the SID, and then Pound Can Radio 2022. All right, now, another highlight of the schedule are the lightning talks. These are 5-minute talks, and they are not 6 minutes. They can be 4 minutes, 30 seconds if you like, but they can't be longer than 5 minutes. So, very quick turnaround, interesting talks. We have a couple of them lined up, but we still have some open slots. And if you want to participate in the lightning talks, email mark@canoradio.org, and he'll give you a slot. And then we'll sort of do the usual, like you upload your slides ahead of time, etc., and then you will be able to present from here in 5 minutes or less, whatever you want to talk about. And we're very, very much looking forward to those lightning talks. Wait a minute. Oh, I accidentally skipped the next slide. That's perfect, because I was going to talk about all the other presenters. Now, first of all, huge thanks to everyone who submitted, an abstract and a presentation for this conference. I mean, that's really what's sort of the heart of the conference. That's where all the cool stuff, like, is shown. If you have not done so, we would really, really ask you to upload your slides to Indico. That's where you submitted your abstract, the same website. You can sort of attach a file, and then the people running the the AV stuff will be able to sort of download that and have it available here. So we want to be very efficient with switchovers, etc. Like try and minimize like people having to figure out the XR&R command to connect their Linux laptop, like stuff like that we want to keep to a minimum. If you really have to connect your own laptop because you have like some special presentation, of course we can accommodate for that. We're just trying to keep that to a minimum. Yeah, when it's your turn to speak, like you can just wait sort of in that area, and then we'll sort of like shuffle you up on the stage and lapel you up and all of that good stuff, and you'll be ready to go. All right, another highlight that we've had for a few years now is the amateur radio exams. So we always hope that more people go home who are licensed than arrive. Who is licensed already? Like, can I show of hands? Like, it's quite a lot. There's at least 50%. So for the rest, like, you can sign up and get like a technician license, for example, with like very little effort, and then you can start, get a little Baofeng or something like that, and then start radioing around, fully licensed and legally. Yeah, but you have to sign up first. So this screenshot is from our, not the GNURadio.org website, but the conference website. If you go to GNURadio.org, there's a huge button on the front page that takes you there, and then you can sign up to those, and then you will be, and then you can get licensed. Okay, we have a couple of students here. Now you don't have to sort of raise your hand or anything. I just want to give an extra welcome to the students. Thanks to our sponsor Sandia, we were able to give like a highly discounted rate to students so they could like join us here. And yeah, you're the future, leaders of this project. Not necessarily this project, but like SDR and everything. And it's great to have you here. This is a great place to, meet potential future employees, etc. And the same is true the other direction. So, if you're looking to hire, then like there's a couple of students running around here. So I recommend there's some networking goes on. But like I said, we didn't want to sort of call them out individually here. We're just very glad to be able to do that. Now, speaking of sponsors, we have a great lineup of sponsors. And I would, without the sponsors, we can't afford this conference, especially in DC. We have a couple of sponsors that you recognize, and a couple of new ones as well. I'm just gonna read out the first row here. Edis slash NI National Instruments, my employer, is as usual a conference sponsor, and of course Analog Devices. You've probably all used some of their chips. Epic, another vendor of PCIe-based SCRs, and who's also giving a great talk, I'm sure, this week. Elbit, and then I can't read all of them out now. I'm so glad to have all of you sponsors here. Many of the sponsors have booths in the expo halls. Not all of them do, but many of them do. So go around, see what they have. There's a lot of cool stuff. I'm looking forward to just seeing what kind of devices they're showing off. Many thanks, and we hope that this is something. This is a great networking experience on top of all the talks. So I hope this is going to work out for everyone. Finally, I already mentioned the exhibit hall a couple of times, so I'm going to keep it short. Go there, take a look around. That's what the breaks are for. Like I said, over there, that's where the exhibit hall is. And I think that might be it. Yes, that's right. So the actual presentation start in 15 minutes. Before we go to that, Clayton will give a quick intro to the CTF, and then we'll have a mini break of a few minutes. And the first presenter of the day, I should know this. Who's that? That's right, it's Igor. Fantastic. I'm glad to see. I'm looking forward to that presentation. Marcus will take over as MC from then, but now I'm going to hand over to Clayton to give a quick intro to the CTF, and that officially opens the conference for this year. So welcome again, everyone, and I'm looking forward to a great week with all of you.
All right, looks like we're ready to go. So let's talk about Capture the Flag. First off, who am I? My name is Clayton Smith. You may encounter me online where I use the handle Argilo. I'm also an amateur radio operator where I use call sign VE3IRR. And I love to play around with software-defined radios. I enjoy reverse engineering protocols and building out-of-tree modules to receive them. I also used to work in the information security field, and that was how I first got involved with Capture the Flag competitions. So what is Capture the Flag? Isn't that the game where you capture your opponent's flag and bring it back to your home base? Well, yes, but that's not the kind we're going to be playing here. We're going to play a game where you use your computer to find secret messages called flags that are hidden away for you to find. Now, at information security conferences where Capture the Flag is very popular, those flags are typically hidden inside vulnerable computer systems. And to get a flag, you need to figure out what the vulnerability is in a computer system, get yourself in, and then look around on the system and figure out where the flag is hidden. Once you find it, you paste the flag into the scoreboard, and you earn yourself some points. Now, at GRCon and other radio conferences, we have a wireless CTF. And at a wireless CTF, those secret messages or flags are embedded in radio signals. And to get the flag, you need to figure out how to receive the signal and demodulate it. And once you do, you'll find a flag, submit it to the scoreboard, and earn yourself some points. So what does that look like? Here's an example of a challenge from the 2020 GRCon CTF. And in this challenge, you downloaded a capture file, and if you had a look at what was in there, there were two FM audio signals, one of them at high amplitude, one of them at low amplitude. And the high amplitude signal was a decoy. The low amplitude signal contained the flag, if you were able to listen to it. But there's a twist. As you can see, these signals are very twisty indeed. They're moving up and down in frequency, and that made them very difficult to receive using an ordinary FM receiver. But with a little bit of work in a GNU radio flow graph, you could put together a phase lock loop that would track the high amplitude signal You would listen to that, figure out it was a decoy, and then you could filter it out with a high-pass filter, then use a second phase lock loop to track the low amplitude signal, and you'd get your flag. So this was an example of one of the more difficult challenges from the 2020 CTF, but there's going to be plenty of beginner-focused challenges. So even if you're brand new to GNU Radio or you haven't participated in a Capture the Flag competition, there'll be plenty for you to do. And of course, we'll also have lots of medium and difficult challenges for the experts to work away at. So, where does this happen? We have a Matrix chat channel called GRCon22 Capture the Flag. Anyone who's interested in participating or just observing the competition should drop by that channel. And if you're on site here in DC, we will be in the Ohio room. And here's a map of where that is. It's basically in the far opposite end of the conference hall. When does it happen? We start up today at 1 p.m. Eastern, 1700 UTC, and the competition runs through until Thursday at 4 p.m., 2000 UTC. Even though it's running over a 4-day period, you definitely don't need to participate from start to finish. And in fact, if you just find yourself with 15 minutes of spare time between talks, drop by, and it should be enough time to get at least your first flag. And on Friday, we're going to be doing a demo session where players will show off how they solved their challenges. We're still working out exactly when that's going to be and where, and as soon as we have that sorted out, it'll be on the conference schedule. If you want to get an early start, you can visit ctf.gnuradio.org or scan the QR code. It'll give you the same URL. If you go there, there is information about the CTF, the rules of participation. You can sign yourself up for an account so that you'll be ready to go at 1 p.m. when the challenges are revealed. So hope to see everyone there and have fun.
So, hi, I'm Mark Smiller. I'm going to MC the next session. We have a slight short break until we kick it off pretty punctual on 1:15. So, grab a coffee, talk to each other. Welcome to GRCon. Sorry? I mean, I can get Clayton back on stage. Yeah. Ah, you mean like motivate?
was the this one. Out. Well, this is this the same time? Maybe got better chances. Okay. So let's see. This one is down. I have your slide, the PDF slides.
Okay.
I have them over here.
Awesome.
So I'll have them loaded up. If you run into technical difficulties,
Okay, perfect.
no, that's up.
So, okay, welcome back to the session. In about a minute, we're going to kick off the first talk of GRCon 22. That's not the opener. It's an honor to introduce Igor Freire, who's the author and main maintainer, I guess, of GR-DVB-S2 RX, which I'm pretty excited about because it does a lot of stuff that it's actually pretty hard to do. He's a PhD in AE from Brazil, if I'm not mistaken, and you might know him from the Blockstream project. So give a warm hand of applause to Igor.
All right, good morning. Good to see you all here, and I'm very glad to be here. Thanks for the introduction, Marcus. Yeah, so this talk is about GR-DVB-S2 RX, and it's an overview of the project state and its path forward. All right, so just as a quick project overview, of course, GR-DVB-S2 RX is a GNU Radio OOT module, and it contains some signal processing blocks, some example flow graphs, and what I call production-ready Python apps, but I should probably put it in quotes, production-ready. But Yeah, so they are originally GRC generated apps, which were then customized, and they are like evolving separately, and they have just a bunch of command line options, making it easy to use, and they can be piped one to the other. So yeah, they are quite easy to use from the command line. Now, GRDVBS2RX is not a new project, and it exists since 2018, thanks to the great work by Ron Economos and Amit Inan. But by that time, it was more focused on the FEC, the FAC and upper layers. So it wasn't like ready to be used with live carriers. And what I've been trying to do, and which I released in 2021, is just make it like a full receiver. So I added the physical layer, the PHY, and the apps I just mentioned, some examples, some more documentation, and overall improvements. So with that, we can say it's now a fully functional software-defined DVB-S2 receiver, which is great. So in this quick presentation, I want to talk about the project state. I want to say a few words about its path forward for optimization and improvements. And I want to show some examples based on the Blockstream Satellite project, which is the project I work on at Blockstream. So yeah, this Blockstream Satellite project is essentially a very interesting Bitcoin broadcasting over satellite service. And it uses DVB-S2 to broadcast both the Bitcoin blockchain and Bitcoin transactions in real time. And it has a nearly worldwide coverage, which is quite good for those of you trying to find a carrier to test with in DVB-S2. And I also want to show some CPU performance results, which are quite important for what we are trying to achieve. Okay, so the DVB-S2RX architecture is like this. We have, of course, starting with a automatic gain control block, AGC, and then there's a frequency correction block, a symbol synchronization loop. And after that, we get the symbols and feed them to the first real DVB-S2 block. So that's probably the block I work the most on, and it's the physical layer sync block. In DVB-S2, people call usually the physical layer as PL, not PHY. So it's the PL sync block, right? And that is the block that does all kinds of synchronization. So it finds the frames, does frame timing synchronization, frame timing recovery. It estimates frequency offsets, both at the coarse and fine level. And it does phase tracking. It decodes the physical layer signaling information, which in DVB-S2 is encoded over read-MULA codes. And it also descrambles the physical layer frames, IQ samples. So yeah, it does a bunch of work, a lot of work. And then it feeds the constellation symbols into the LDPC decoder. And then the rest of it is previous work. And yeah, it's the LDPC decoder, BCH decoder, up to the structure that's called the baseband frame, BB frame. And from that, we unpack MPEG TS packets. So that's the upper layer. In this case, it could be another one, but we use the MPEG transport stream protocol. All right, so in terms of the project stage, I would say the current stage is of having minimal functionality. So we have some of the possible configurations in DVB-S2, like constant coding and modulation. We support QPSK and HPSK constellations. We support a mode called pilot mode, which is when the physical layer frames have pilot symbols on them. Right, so that's called pilot mode, and DVB-S2 also has the pilotless mode operation. Right, and we test with both RTL SDRs and USRPs. Now, for the future, the first thing I'm particularly doing is optimizing some of the blocks that are using most of the CPU. So that would be like the BCH and LDPC decoders, the symbol timing synchronization, and we also want to improve the signal-to-noise ratio limit. And when I say limit, it's because the synchronization algorithms, they must operate at really low SNR, like -2 dB, relatively low, at least for DVB-S2. And yeah, they are not quite there yet. They work up to, I would say, +2 dB, which is good already for us, but we will, of course, want to go lower. Next, I would say a more comprehensive DVB-S2 support, like other features, and one of them, which is quite interesting to use, is adaptive or variable coding and modulation, so ACM and VCM. That's not fully supported yet, but it's coming in the future. And then the final stage would be like a more mature state when it's more tested with more carriers, live DVB-S2 carriers, more SDR boards, etc. So I want to say a few words about current limitations of the project. So in case you find a chance to, and you want to explore the project, you may encounter some of these. So yeah, this can be useful. The first one is that the AGC at the moment, it really may not work if the oversampling is too high and the SNR is low, because it's not really data aided yet. So that's something that is probably going to change soon. And of course, the details are quite complex, so I'm not going to go over them. Yeah, the simple synchronizer is the most CPU consuming block at the moment. So that could be a problem if you try to run on like a low resources CPU, like a Raspberry Pi or something like that. And it's also something we want to improve, because the Raspberry Pi would be quite an interesting platform. So yeah, maybe that can be improved a little bit more. And by the way, this simple synchronizer is specific to this project. It's not the Intri one. We made one that's a bit faster with the specific configurations we need. So probably something like 40% faster. So yeah, but it can still be improved. The PL Sync block, as I said, is it's good, it works well, but it's still about an SNR limit of plus 2 dB. So if the SNR goes lower, then it may not work that well. And the decoders can, of course, they can always be made faster, but in this case, I'm currently working on the BCH decoder, which seems to be an easy gain in terms of CPU performance. So yeah, I'm refactoring and doing some benchmarks. All right, so moving on to examples. This is the Blockstream satellite setup for reception with an SDR. It's just the usual RTL SDR with a power supply to the LNB, right? And as I said earlier, we have nearly global coverage over 6 satellite beams in the KU and C band. In this case, I'm going to show some examples with the beam over the Eutelsat 113 satellite. And really the most important parameter here I want to show is that the baud rate in all of those carriers is 1 megabaud. So you can oversample by 2 and with a sampling rate of 2 megasamples per second. And that means you can run an RTL, you can receive with an RTL SDR, which is good. Not all DVB-S2 carriers are small like that, so that's one you can use to test with an RTL SDR. Right, so the command line would be something like this. You have DVB-S2RX, that's the command, and you specify the source. In this case, an RTL. It could be a USRP, it could be a file or a descriptor if you are piping. You specify the L-band frequency, the oversampling or the sampling rate, and you also specify whether pilots are enabled or not. You can also use something called auto mode in this case, and the physical layer will detect if you have or don't have pilots. But if you already know a priori that the signal has pilots, then it's better to just inform that, because the performance is going to be better. And there's also a GUI flag, which is just going to open a GNU Radio widget window with some useful plots for inspection. All right, lastly, so I want to show here some CPU utilization measurements taken over 10 minutes. And the curve up the top is the simple synchronizer CPU utilization. So it's using a lot more than the other blocks. Of course, it's the only block doing like a closed loop at the sample level. So processing the samples, not the symbols. And it's naturally doing more work, but yes, it can be optimized a little bit more. And the other thing here is the BCH decoder, because DVB-S2 uses both BCH and LDPC. It's a concatenated code. And the BCH decoder is using more CPU than LDPC. Maybe that will change after some optimization. Also, it's good to show here that the physical layer PL Sync block has stable and relatively low CPU utilization, which is quite good. In this case, because the SNR was high for this measurement, the PL Sync is just locked all the way. It doesn't lose frame lock, so it has a stable CPU utilization. Now I'm going to show a different scenario now, contrasting both a high SNR and a low SNR measurement. And in this case, of course, the symbol synchronizer doesn't change. It uses the same, but the LDPC decoder is going to do more work because it has to do more iterations per each frame when it's decoding. So the LDPC utilization is higher in this case, but the BCH is still the second highest. So yeah, the BCH is still using more. And the thing I mentioned earlier, the PL sync block, in this case, because the SNR is a little lower, it has occasional peaks. What happens here is that whenever the frame synchronization lock is lost, then the PL sync has to do more work. So it peaks in CPU utilization. But then if it locks again, then it gets stable again. So that's the idea. These are just some figures of CPU utilization, but overall, the project is good to go. You can try it and you can receive live carriers. With that, I end my presentation. Thank you very much for your attention. I hope I have some time for questions. Okay. Right. So the question is, what have I optimized already? And yeah, so there's a very interesting project called Affect. I'm not sure if you heard of it. It's a decoding, channel coding project, and it has some useful tools for benchmarking. And they are actually using and studying the GRDVB-S2RX project. They commented in the project. And I've been trying to use their tools for benchmarking of the BCH decoder and really trying to refactor the implementation and using their tools to do some benchmarking. Because the BCH decoder is sort of maybe clearly not so good in terms of the arithmetic. It could be made faster. So I think it is the easiest gain at the moment. So that's what I'm working on first. You.
Yeah, I was just curious what sort of improvements you did to symbol synchronization.
Sorry, I couldn't hear you.
Oh, you had mentioned that you had improved the symbol synchronization block. What sort of improvements did you make?
What sort of?
Improvements. You said you made it 40% faster?
Yeah, so if I understood correctly, what sort of improvements on the symbol synchronization block? Yeah, so the thing is, the entry version of the symbol synchronizer, it has so many options. Like it supports all kinds of interpolation, TED, which is a timing error detector. It supports a bunch of them. And really for the DVB-S2 project, we just need some specific implementations. We use a polyphase interpolator with a matched filter on it and a Gardner detector and that stuff. So we implemented really just what we need. So we have less function calls and it just runs faster. And we also do a bit of improvement on the loop. So yeah, but I think we can improve a bit more if we use more of the SIMD instructions. So yeah, that's what we're gonna try to do.
Luigi Cruz, if you could come up to the stage, that would be cool. I do have another question from the internet. So Daniel Esteves asks, does the symbol synchronization block do anything DVB-S2 specific, or could it be used with other RRC pulse amplitude modulation waveforms?
It could definitely be used in other projects. It's not DVB-S2 specific as long as the other project is happy with a Gardner timing error detector, which doesn't make decisions on the symbols, and something like a polyphase interpolator. And then that would work.
Thanks. So I guess I have to close the question session for this talk. We're handing over to Luigi Cruz, who's talking about the Cyber Ether, which is an exciting new visualization tool. You might know Luigi from his work on Cyber Radio, which is also a CUDA accelerated toolkit, if I remember correctly. I haven't worked with it. So please give a bit of applause for the last speaker and welcome the new one.
Hello, everyone. My name is Luigi. I'm here to present about my project, my pet project, called CyberEther. It's a heterogeneous accelerated GUI visualization for GNU Radio and other projects. So I will start talking a little bit more how it came to be the project, and also proceed to where it is at the moment, and what makes CyberEther different and how it works. And finalize with future and GNU Radio integration. All right. So first section is early development. So I apologize the amount of tweets in this presentation. So everything started when I started another project to run, to connect with an SDR using your browser, using web USB. So every USB call from libUSB was being translated to web USB using a C wrapper, working with WebAssembly. And I got this to work. It works with AirSpy, but I needed a way to display the information on screen. So I wrote a quick and dirty OpenGL using WebGL to display the data, and that was the first iteration of the project. And later, I figured that that visualization was good enough, and I could take advantage from being on the bare metal on the OS. So I decided to port from web to application and start to dive a bit more on that. Then after the OS application was ready, I started to code some accelerators like CUDA QFFT library to do the FFT, and that way I could run 60 plus megahertz at this, in real time, and also run on nice boards like the Jetson Nano and other CUDA-enabled computers. So Dev Nulling, he suggested that what's the chance of this being on a out of 3 blog on GNU Radio? And I thought about the idea and said, oh yeah, that's a very great idea. So I did it. I wrapped my code with GNU Radio using the GR mod tool, and everything works as expected. And just the fun of it, I ported my OS application running the same render on Chrome, so I could run the same thing from the desktop on Chrome using WebUSB, WebGL, and also WebAssembly. The only funny thing is that you can't have a multi-threading with a WebAssembly. They use a shared buffer, and the shared buffer is problematic because some x86 exploits, so that is now disabled by default. When it gets re-enabled, we can revisit this project. So section 2. What is CyberEther at the moment? So it's a portable and heterogeneous accelerated GUI for radio signals. So it's not built to display statistics and stuff. It's built from the ground up to display only signals generated by SDRs. And it currently offers some basic plots like line plot, waterfall, and spectrogram visualizations. It runs as close to the metal as possible using a heterogeneous API for, of course, battery and speed. And one important thing is to use like minimal dependencies with a modular design, because no one wants to install 500 dependencies to make the thing compile. It will check which dependencies are there, and it will compile just the modules that has all the dependencies. So you don't need to worry about that very much. And the code is the application is reduced by writing an abstraction graphical and compute APIs layer. So instead of talking directly to Vulkan or OpenGL, you talk with the render, and the render will translate the common calls to the backend API, so you don't need to rewrite your code for every backend you want to write. And yeah, and it is also very easy to implement on third-party projects. We don't make you use any window manager or something. It's just a frame buffer, and you can bind anywhere. So the first plot is the line plot. It's a line. It's a very simple, lightweight way to see frequency domain or time domain data, and has very little memory requirements, and also does not store data beyond the first time iteration, other than averaging. The second one is the waterfall. So here is also a very good way to visualize frequency domain data, but this time changing in time. And this has larger memory requirements because you need to save all the data from previous steps, and the data is retained. And one cool thing is that you can use a CyberEther if you are using CUDA, for example, to extract the frame buffer from the waterfall and feed directly to your machine learning model. So the copy would be internal on the GPU, and that would be very fast. You can run your inference and plot the data out like a UNet, or just have a text output on screen with markings. And we also, this is fairly new, a spectrogram view. So this is the same thing as waterfall, but better. You can see the same, like a different perspective as a waterfall, and has nice animations. It's colorful, everyone likes it. And the current implementations run on the CPU. You don't need to run on a CUDA. So most of these visualizations have CPU fallback. So for example, you are running on a potato computer, you don't have any fancy heterogeneous API to use, you can use the CPU to render. That's not a problem. Demo, maybe. Okay. All right. I will start here. So this is a Lime SDR block, so open source. Everyone is used to it, I guess. And this is the GNU Radio CyberEther sync. This is a very early prototype, so there's not many parameters here. So first is FFT size. You can change this at whatever you want. If you want more time variations, you put a lower value here. Also a buffer multiplier if you need to run something that is a little bit heavier. And also you can choose the compute backend. You can choose with whatever heterogeneous backend you want, and also graphical, Metal, or Vulkan at the moment. So if you run this, you can see the data streaming in. And yeah, this is the line plot, the spectrogram, and also the waterfall. And the nice thing here is that you can zoom in, and everything is handled by a computer shader, a graphical shader, so you don't need to run that back and forth your CPU and GPU and display data. there is also plans to integrate more controls here with better UI. But yeah, this is the current state of the GNU Radio. Okay, now. Thank you. So some specifications. It's written on modern C++20. Compiled with Meson, so don't need to deal with CMakeHell. And utilizes FFTW3 on the CPU-based FFT and QFFT with CUDA and Vulkan, VKFFT with Vulkan. And the standard way to contribute to it with it is with a GitHub pull request. So what you saw back there, this is the flow chart of the data. So first we get a circular buffer, then we pass to FFT, we scale, do some windowing things, and then we pass the same data to the line plot, waterfall, and spectrogram, and plot that on the screen. And this is, so the green ones are running on CUDA, and the blue ones is running on Metal or Vulkan. So section 3, how and why? So I will expand on what I said before. So CyberEther is built on ground up to display signals generated by SDRs, and this has some advantages, like less code to optimize. You don't need to optimize all the code for everything, and more importantly, it's real time. So it's built to run on real time. You are not hacking a plot to run on 120 FPS. You build something to run on that speed without data dynamic allocations. Everything is steadily allocated and runs after instantiation. And also other features are not required to be supported. And it's more friendly to integrate with project. As I said, it's just a frame buffer. You can bind anywhere. And you can expand the user interaction to support some SDR signals instead of supporting statistical work. Another thing is it runs as close to the Metal as possible using heterogeneous APIs like Metal, Vulkan, and WebGPU when that becomes available in the early 2023, apparently. So you can render the blocks with that graphic APIs using the backends, and also accelerated compute like CUDA, Metal, and Vulkan. CUDA being the more popular there. And the above graphic and compute accelerated pipelines will cover Apple Silicon M1, iOS, Android, NVIDIA GPUs, desktop or Jetson embedded ones, and also AMD GPUs with Vulkan, and Raspberry Pi with the V3D driver that Collabora just is maintaining for the Raspberry Pi 4. So you can run even that on a Raspberry Pi 4 when the Vulkan API is ready. And more importantly, it's CPU-based compute fallback. So if you don't have any fancy things, you can run on a browser anywhere that runs Chrome, and it will work fine. And dependencies are not mandatory. It compiles with the available ones. And another very important thing of the projects is the code duplication. You don't want to write to make like the VK frequency sync that will be limited to Vulkan or something, because that can change in the future. And if that changes in the future, your code is basically useless. So supporting multiple graphical and compute APIs is very important. So you can write a new backend for a new fancy API in the future and reuse your current code with that. And for that, I wrote Jetstream render that is basically a render. It will abstract graphical calls from the application and to backend like Vulkan or Metal. I already wrote OpenGL render for this and also Metal. I am currently working on the Metal one because I have a MacBook, and Apple decided to deprecate OpenGL. Maybe Vulkan in the future, yeah, probably Vulkan in the future. And also I want to work maybe DirectX and WebGPU. The graphical backend can be selected during runtime, so you don't need to compile your code using a define and wait 5 minutes to compile. You just need to toggle that on, for example, the GNU Radio block, and it will work with the selected backend. And the same thing applies with modules. So we have Jetstream modules. It will abstract the compute work required, because visualization is not just visualization. You need to do some pre-processing of the data. So this will handle that, and everything is bounded to a block. So CUDA block for scaling is just a CUDA kernel that is multiplying by a factor, and that kernel is combined with other kernels in the pipeline using CUDA graphs. So you don't need to worry about your CPU speed for instantiation. Everything will be pre-cached. All kernel instantiation will be pre-cached and will be run on whatever you need. And also you can select that on runtime. And the backend will support a mixed match of backends, but that's not ideal because you have some certain asynchronous synchronization boundaries between between different APIs. For example, CUDA and Metal, that you need to wait until CUDA is done to start the Metal work instead of running everything asynchronously with CUDA. So that's a boundary that's not ideal, but it will work fine. So it's easy to implement on third-party projects. So with this combined with the fact that we have minimal dependencies make this thing very useful to implement on iOS, macOS, Android, Mac, and even a browser, because it's first front-end agnostic. You don't need to use Qt to display things. You just have a headless frame buffer being rendered, and that can be bind using Qt surfaces or Cocoa or MetalKit vil on whenever you want. And in Linux, you even can use DMA-Buff to share your frame buffer with other processes. So if you want to, for some reason, run your program on a headless machine and then in a headless process, and then share that with a windowing application, you can with DMA-Buff. So too long to read. It's easy to implement on everywhere. So the last session, a brief one, future and current GNU Radio implementation. So line plot, waterfall, spectrograms are the current graphical interfaces. CPU implementations of all of them are ready. Metal is also ready with line plot and waterfall. I'm currently working on porting spectrogram to Metal, and also CUDA pipeline is done, but I didn't port to the new latest refactor that I did on the library. Some compute modules are CPU at the moment because I am focusing on adding capability at this moment, and then writing the other compute modules for other application, for other backends. But same thing, CUDA is written, but it's not ported yet because I have a MacBook. And also in the future, I want to implement CyberReefer inside a Qt window to run more smoothly with GNU Radio, and also add more Metal and graphical backends. Compute with Metal, that is a thing, and also compute graphical with Vulkan backends to make use of VK, FFT, and other accelerators for your project. And also FontSport. That's a little bit tricky to implement, and if we implement it, it will be hard to make changes. And we are in our current state. There are a lot of changes. So I'm putting the FontSport text rendering, like labels, X's and stuff, forward. So we don't have this problem at the moment because speed is more important at the moment. And also improve the handling of multiple compute backends at the same time. As I mentioned, you need to resynchronize every time you cross APIs like CUDA to Metal or Vulkan. So that's something to think about. No demo? Okay. Thanks for listening. Please contact me anywhere. I am on Twitter. Send me an email. Contact me here in the conference. I will be happy to give you like a demonstration, a better demonstration, and also answer your questions here and now on. And you can find CyberArray on GitHub. It's an open source project. There is a out of tree module also on my GitHub called GR Cyber. You can find the link on the CyberArray repository. Yeah.
So, are there any questions in the room? If not, please think about questions while I read one from the internets. Noto asks, is CyberArray designed to support remote visualization? If it is the bulk of processing power required on the computer that runs the flow graph or the one doing the display? So can CyberArray, run on two computers where one has the flow graph with radio in it and the other one does the visualization? And how is like the compute split?
Okay, so that's not that trivial because you need to, you are ideally displaying your information where you are processing it because the data after processing is larger than the current data that you receive from the radio in some cases. That's a good question. In theory, you can pipe the frame buffer through Ethernet or something to another computer and render that there. That's a possibility, and that's open.
Thank you. Any other questions? So actually, while I was walking the room, like people are actively using your project and trying to compile it, and some fail, for some it works, some are porting it forward. So
I'm sorry, it's not compiling. Yeah, I went to some seg faults too. Something with macOS synchronization. I'm trying to fix it.
Yeah, so I guess the right way to move forward, like if they have something that fixes or if they've noticed a new problem, is it like GitHub issues or PRs or?
Oh yeah, hit me on Twitter, GitHub PR. If you write your fix yourself, that's better. Just submit to as a PR and I will review it with the community. I'm open for contributions. If you have any suggestion how to improve the code, just open an issue or open a community forum there and we can talk about it, how to make things better for everyone.
Yeah, thanks. So I don't want to do like a penalty moment of silence for everyone not asking a question here, but you can always prepare questions. But then the next speaker might slowly move in the general direction of the stage as we shift over. Friendly reminder: we are putting basically all the slides on our event site. So if you need them, you can download them later. The video recordings are later cut and preserved on YouTube or your local hard drive if you're into decentralization. And you're always welcome to, follow up with speakers. So that's the whole point of speaking here, is probably, getting in touch with it, your own community. So give a warm hand of applause for Luigi. So we're starting a bit early on the next talk, which is Martin Brown on the ultimative guide to GPIOs on user peace. I will not start this class until everyone is silent. So Martin, used to be my bachelor's advisor. He's like, his interests include being outside and being an all over okay guy. He's a PhD of EE from KIT, and now he's working for Etis. So here we go.
Thank you. Oh yeah. Hello. There we are. Okay, I should add to that very, very fine introduction by Marcus that the company is called NI. But yes, we are the Etis research group. Yeah, I'm going to talk about GPIOs and USRPs. Now, this seems like a very, very basic low-level topic, and it is. I usually try and sneak in at least sort of one background, just like fundamentals of SDR topic. And the GPIOs on our devices are something we get a lot of questions about. So yeah, this will be hopefully like kind of a useful guide for everyone who's like ever used or planning to use GPIOs on USRPs. All right, let's go right into that. So first of all, just to make sure we're all on the same page. What is a GPIO? So a general purpose IO, as Wikipedia states, is an uncommitted digital signal pin, which may be used as an input or output and can be controlled by software. Now, actually, does the laser thingy work? No. Yeah, I'll just gonna. Can I enable the laser thing, Mark, without like messing up your AV setup? Let's see if I can figure out how to do that. I don't know how to do this. I'm just gonna keep going, whatever. Yeah, so if you've ever bought a Raspberry Pi or an Arduino, then you have like all of these pins. Those are GPIOs, and the whole point of those is that you can do whatever you want with them. Now, on a USRP, we also have them. They're like these pins in the middle, and really, in a very real sense, they're the least interesting connector, right? We have like 100 gigabit Ethernet and multi-gigahertz analog signals coming in and out, but we still get so many questions on these GPIOs that I thought it would be worth talking about them here at the conference. All right, so I don't know everyone's, but for many people, like your first electronics project was like blinking an LED. So can we do that? We'll just plug it in the USRP and get going. And I'm gonna stop everyone right here. Like, don't do that, please don't do that. Now in this particular case, nothing would probably happen. I don't think you can break the USRP that way, but you can break the USRP by misusing like GPIOs. So here's like rule number 0, like just always stick to that. Like you don't want to sink a lot of current into a GPIO. You don't want to draw a lot of current from a GPIO. 5 milliamps should be your budget. try and stay below that, especially if you're using many of those. Like just don't do anything like that. Like this is actually one of the ways you can fry a USRP, and then it's gone. Like, and that's not covered by warranty either. So yeah, be careful, please. All right. But honestly, this is not so different from other, like I said, other devices like Raspberry Pis. So that's fantastic because that means there's a lot of guides on the internet available. If you can't draw a lot of current and you want to drive an LED, for example, what do you do instead? Well, rule number 1, BYOP, bring your own power. You need to somehow provide, power so you can actually drive stuff. And LEDs are just an example here. Doesn't matter what it is. And make sure that your actual GPIO is sort of removed from the circuitry. Well, it's not removed, but it's like somehow decoupled. So a good way to do that is use Darlington transistors, have high amplification. So this is the simplest possible circuit that I could come up with to drive an LED. So on the right-hand side, you have your own power supply. You put current through an LED, and then the GPIO can open or close this transistor basically based on its state, and then that's it. So this is a good way to get started with GPIOs. Let's see, there should be. All right, now we need a little bit of software to set up the USRP to make the LED actually go blinky. And so this is like a short snippet of Python that'll do that. There's a few lines up here that'll actually, configure the pin to be in the state that you want it to be. And then we have this loop which goes up to 11 naturally. And then we just like write a 1 or a 0 into a register, and that'll like drive the GPIO high or low, which in turn will turn the transistor on or off, which will make the LED blink. And this is, let's see if this works. Yeah, this is a video. So it should blink 5 times, 3, 4, and 5, because like we have 11 flanks here. So yeah, that works. So blinking is fine. Great. Now, blinking an LED, I mean, it's cool and all, but you don't need to buy a user. I mean, you can, I wouldn't mind, but there's like much cheaper ways to do that. And also you don't have to go through these weird APIs that we provide. So if you want to blink an LED off a Raspberry Pi, there's like 1,000,001 tutorials on the internet. So why would you do that on a USRP? And one of the reasons is that those pins are actually useful not just for, sending like a software command to turn them on or off, but also this feature here, tracking the radio state. And that's like a really, really key feature, and I definitely want to make sure that you all know how that works. Now this is the ATR feature. Now, to blink the LED, we had to write a 1 or a 0 into a register, and that's the one at the top, like the GPIO out register, the sort of not quite so bright yellow one. But there are 4 other registers that you can also write to, and those follow the state of the radio. And this is a key feature, so make sure you pay attention now for the next 30 seconds. A radio can be in one of 4 states. It can be idle, it can be transmitting, it can be receiving, or it can be transmitting and receiving at the same time, full duplex, okay? So if you don't care about that and you just say, I'm going to write like 1s and 0s into that register to turn the pins on or off, you can do that, that's fine. If you do this ATR thing, then you sort of pre-select the state of your GPIOs based on the state of the radio. So at an early time in your program, you say, okay, whenever the radio is idle, I would like my GPIOs to look like this. And when it's transmitting, I want my GPIOs to look like this, and so on and so on and so on. And then the actual state switching happens on the FPGA at real time. So you don't have to, from software, control how that works. So how does that look in practice? So if you've ever used a USRP, then you've probably noticed that under the SMA connectors, or next to them, depending on which device you have, there is some LEDs that turn green or red when we are transmitting and receiving. And you might have wondered, like, how do they do that? Like, how does the LED know when we're transmitting or receiving? And internally, we have the same GPIO API. It's just not exposed to users. But if that's what's happening, maybe we can build a little script that mimics those LEDs. So can we like follow the state of that LED with my external LED? And this is how we do that. Here's again a little Python snippet on the right. And the interesting bit are these 4 lines here that have this ATR thing in one of those arguments. So you can read it as follows, like 0x is the idle state. So we say when the radio is idle, we want GPIOs to be off. When we're receiving, we want the first pin to go high. When we're transmitting, we want the second pin to go high. And when we're doing both, we want both pins to go high. And then we sort of step away and say, now go. And in this script, we're going to do a receive 1 second, and we're going to do a send 1 second to see if that works. And you can follow the LEDs here next to the SMAs to make sure those are the ones that we're trying to mimic. And I put this on a loop, so when we receive here, this LED will also turn on. When we transmit, you can see it here. This LED will also turn on. That's how you do that. Now, why on earth would you do that? Like, you may want to build like one of those on-air signs or something like that, but that seems overkill. This is really useful when you're controlling something like an antenna controls or external amplifiers or something like that need to know when you're actually transmitting. This is how you use that feature. And that's really one of the main reasons to use GPIO on a USRP. Okay, so that's most of the basics. I'm going to go, now before I go into the really interesting stuff, I need to talk a little bit how you actually connect those GPIOs on the USRPs. And this is like the most boring section of my presentation, so I'm going to rush through it as fast as I can. Actually, I have plenty of time, I realize, so I don't have to rush. Yeah, okay, I'm just going to go through the various connectors. We have a lot of diversity. This is one of those cases where diversity might not be helpful. But anyway, gives me something to talk about. All right, I'm going to start with the X310 and the N310 just because I used them in my examples earlier. So if you're my age, then you might have had a computer at some point where you had like one of those DB15 connectors where you plugged in a joystick. And those are the same ones that we use for exposing GPIOs. So there are 15 pins in a DB15 connector, 12 of which are GPIOs that you can use for your whatever you want to do. And they're all at 3.3 volts. So if they're high, then they are at 3.3 volts. And if you want to sort of start playing around with them, I recommend getting one of these breakout boards. You can see at the top, this one that we actually sell through our own shop. That's for, mostly for people who want to get like a stash of stuff like from the same vendor, because you can get like, you don't need a special one. You can, if you're lucky and you can get one like really cheap off of, I don't know, Adafruit or something, then that'll work just fine. Also depends on what form factor you need, etc., how much you actually want to expose. By the way, I didn't put this on the slide because I didn't want to, but if you're in a pinch, you can just put the jumper cables like from a breadboard straight into the DB15 connector, but please be careful. Okay, that's not recommended operation. All right, our flagship USRP, the X410, I only didn't put that first because I wanted to start off with the ones that you had seen earlier in the slides. Is much better designed when it comes to GPIOs. First of all, we have 2 connectors, which gives you more pins, 12 pins per connector, 24 pins total. And then they're on an HDMI connector, which is just a much better connector, more common. You can also get breakout sets for HDMI. That works as fine. And we have a bunch of cool features that we didn't have in the past. So we've been evolving like sort of the GPIO functionality along with all the other features, like bandwidth, etc. But this is sort of a usually like less talked about one. So for example, we have a dedicated pin on those HDMI connectors that you can actually draw power from, so you don't need to bring your own power supply, which can come in handy in some cases. And you can also switch the voltage. You can get much higher switching speeds. I'll talk about that later. And another thing that I'll talk about later is there's sort of a built-in hard SPI mode for people who want to control peripherals that use SPI on the other side. But I'm going to talk about that towards the end. E320 also has an HDMI connector. It's a mini HDMI connector, but if you have a mini HDMI to HDMI cable, you can use the same breakout boxes, etc. It's very neat. You only have 8 pins though on the E320, and we don't have any software support for switching the voltage there. Even though it's theoretically possible, if that's something you need, then you can talk to us. The E310 is probably our worst offender when it comes to GPIOs. Like I said, this is something we evolved over the years, and when we built the E310, this was not on the top of our minds. But to get to the actual connector, you have to open the box, which is I'm not gonna lie, is a disadvantage. And the connector is also not the most common. I think it's 2 mil pin spacing connector. I don't know what the name of the connector is, but there's some nice features there. So for example, we exposed the regular 3.3 power rail through that, which means you can actually draw power from there. But be careful, this is not dedicated to the GPIO, so you can actually brown out your device if you draw too much. And you have 8 pins available to do the usual stuff. B200 series. So the Mini series, and Mini is, like the name implies, is a very small USRP. So the connector is also small. Most of you would probably do best by getting one of those adapters that expose a 12-pin, 100 mil spacing standard GPIO, thing, like, looks like on a Raspberry Pi or something like that. The regular B200 series, the ones with the Euro card size, they don't need that. Like the connector is directly on the board. Although there are some revs where that's not populated, and you have to hand solder it down, which is not difficult though, by the way. Just in case you're curious. So I highlighted all the locations where they are, and then you can look in the manual for the specific pin assignments. And finally, if you're like using the really old USERPs, like this is an API we've had for a long time, you can actually use daughter boards to access GPIOs. This even works on the X310, but on the older USERPs, we don't have a dedicated separate GPIO connector. So yeah, this is definitely useful for those scenarios. Okay, that's the connectors. Now it's going to get a little bit more interesting. So I'm going to have to go through a couple of concepts here. So if you are used to programming GPIOs on a Raspberry Pi or something like that, this is where it actually gets a bit different. Like the circuitry design, etc. That's all very, very similar. You can use existing designs from other projects that are not specific to SDR, like decoupling your GPIOs, etc. But here we have a couple of things that are more or less unique to the way we've implemented this. Okay, first of all, remember this little picture here at the bottom. This is the when I was explaining how the ATR registers work, we have 4 registers, and then we have like the actual manual GPIO register that we can write to. All of that is what we call a GPIO bank. So that's the first word that you have to remember. And we have usually more than one of these banks per radio. So a radio is any part of the device that can transmit and receive. So for example, on the X310 and the X410, we have 3 of these banks. We have one for TX, one for RX, and one for the front panel connector. And they are actually physically connected to the TX connector and the RX connector and the front panel connector. So despite the name, they all support all the radio states. So you can say the TX connector GPIO state should also change when we're receiving. That might be useful because you need to, I don't know, do some isolation something. So these are completely programmable with respect to those states. So yeah, so we have 3 of those banks, but you might ask, wait a minute, okay, this makes sense, but there's 2 radios on the X310, so what about that? And the answer is yes, that's correct. And all of those banks are duplicated, so we actually have 6 of these banks that you can program. And in the USRP X310, we have like the A side and the B side. So there's a TX connector on the A side and there's a TX connector on the B side. But there's only one front panel connector, which means this bottom register here, FP0, that's just its designator in software. Like we have 2 of these registers, or banks, sorry. Now I'm confusing my own terminology. We have 2 of these banks connected to the same front panel connector. So how do we arbitrate that? And we have the concept of a GPIO source. And we have 3 APIs for that: get GPIO sources, get GPIO source, and set GPIO source, which you can use to query available modes, the current mode, and then obviously set one. Now I mentioned earlier the X310 has 12 pins. For each of those 12 pins, you can decide who's going to drive that. Is it going to be radio 0 or radio 1? So that's freely configurable, but it can only be one at a time. So you could say like the bottom 6 pins go to radio 0 and the top ones to radio 1, or I'm just going to assign them all to radio 0 or whatever. That's all up to you. All right, but that's not all the available sources we have. If you look at the USRP N310, for example, we have 2 channels per radio, which means we also need 2 banks like per radio. And that means we already have 4 of these registers that are all potentially able to drive the front panel connector. But we have another mode, which is the PS mode, like that's the processing system mode. And that's a mode where we yield control of those GPIOs to software that is not controlled by us. And that's when you go back to like sort of the Raspberry Pi programming mode. So you can say, okay, front panel connector, I don't know, top 6 pins, I'm just not going to care about those. Like, I'm just going to hand them back to the user to, you know, have some random software running on the device to control those. But otherwise, it's the same principle. And if you go to the USRP X410, you know, our like I said, our current flagship product, which you can, by the way, take a look at the at our booth, we have 2 front panel connectors. So it gets yet a little bit more complicated, but only a bit, because this API call, set GPIO source, takes multiple arguments, and it takes, one of the arguments is like, which connector are you actually setting the source for? So basically this API, you say, for front panel connector 0, I would like pin 0 to be assigned to radio 0, and pin 2 should be assigned to radio 1 or something like that. One thing that I forgot to mention, depending on what kind of API you're using, there might be a requirement to uniquely identify all of these banks. So if you look at this slide, for example, I put in parentheses like the unique name that, for example, the multi-USRP API understands. Because, you know, if you're saying I want to program register FP0, is like, which one are you talking about, the top one or the bottom one? And that's how we differentiate those. Okay, so how would this actually look like in software then? So this is like the shortest snippet that I could come up with that sort of shows off all the available features. So again, I'm like in this specific example, I'm talking to an X310 or an X300, which you can see on like one of the third line. And first of all, I'm going to query. Oh, wait a minute. No, there's one thing I need to mention here. On this slide, I mentioned that you pass in the name of the connector and the name of the source into the API to say which pins should be controlled by whom. And this is one of the things where I'm like, going back, I would like to rename this API. Obviously, we're not going to do that. It would break people's applications. But we use this word banks like twice. Like once for this like yellow box on the left, which is the register we're talking to. But also then we have this thing called a source bank. We just should have called it connector in retrospect. So that's a little bit confusing. The manual has like a huge, bold-faced thing. So this is not the same as that. Like here's an example of how to use it. So I think if you read the manual, you'll be fine. But like the API naming could have been a bit better. So you can ask the device by calling get GPIO source banks which connectors are available to you. And that's what we're going to do here. So we're going to first ask the device which connectors are available, and then we're just going to pick the first one. And because it's on an X310, there's only one connector, which means this variable db15con name will now contain like the identifier that we use in software to identify the db15 connector. So we're just going to use that in the following. So, and then in the next line, we'll say, okay, Mr. DB15 connector, can I please have 8 pins assigned to source RFA and 4 pins assigned to source RFB? And those correspond to the individual radios. So you might say, why aren't they just called radio 0 or radio 1 or something like that? And that's because there is a distinction between the physical sources in the FPGA and the actual RF knock block. So because you could potentially rewire them. I highly recommend not doing that, but something that you could feasibly do is just remove one of the radios because you need to recoup that FPGA space, and then that name would no longer be available, but the pins would still be available. So that's why they have different names here. Okay, so now we're gonna ignore the top 4 pins. So we can set a pin mask of just 8 pins. So that's the pin mask. And then we're going to go through a couple of exercises. So first of all, we have a register called control, which decides whether or not a pin is tracking the radio state, or if it's to be controlled by the user. The DDR attribute defines if it's an output or an input. You can see I have 2 pins defined as inputs. A 1 is like if it's a 1, it's an output. If it's a 0, it's an input. And then the 4 states. So I'm basically doing a one-hot encoding of my radio state onto the GPIO. So I have 4 pins available to track the state, and basically one of them will go high depending on which state I'm in. And then at the bottom, you can see an example of me programming like the specific pin that I can manually set, like through software, but I'm using a time command to do that, which means I can very, very accurately decide when a GPIO pin will go from 0 to 1 or from 1 to 0. And then the last line, I'm actually reading back a GPIO. So like if you know externally I'm like monitoring something and I just want to know if this is 1 or 0, that's how I would do that. Okay, so there are two things that I decided to not put in my presentation. I just couldn't fit them in time-wise, but I just want to mention them here, and maybe I'll do a longer one of these at some other event, or I don't know, on YouTube or something. The first one is, I mentioned earlier the X410 has an API to control the voltage of the GPIOs. And it's explained in the manual, so I'm not going to talk about it here. And the second one is I also mentioned that you can yield control of the GPIOs to software when you're running on the embedded devices, and we use a standard kernel API. And there's a Python package called GPIOD, which is installed on the device, which you can use to just control them. So you can just write Python code to directly talk to the GPIOs without having to go through UHD. Okay, finally. Protocols and signals. This is where it gets really interesting. Now, blinking LEDs is nice to get started, but that's not really like the killer feature. So what am I talking about here? Okay, I mentioned already that we can use time commands to set GPIOs to go high or low. Now, here's a code snippet at the bottom where I do exactly that. So this is actually similar to the LED blinky code snippet that I showed at the beginning. However, I am using this set command time API to decide when those toggles occur. And I want to generate a 1 kilohertz signal here. So like at exactly multiples of like my period, or like half the 1 kilohertz period, I'm either going up or down. And here's sort of a scope capture where I'm putting, you know, cursors on the down flank and the up flank, and you can see it's exactly 1 millisecond apart. And you'd say, well, 1 millisecond is like, that's not that fast, that's not that interesting. But you have to keep in mind that this is going over the network and it's like controlled by some Python script. So I don't have any kind of scheduling on the software side here. And yet I still achieve like that very exact flank. Now, if I can do that, then I can also let all the other pins go up or down, you know, depending on what time I want them to do something, which means if I have multiple pins, I could, for example, implement an SPI transaction this way, where, you know, I have one pin, that's the SPI clock going up and down, and then, you know, a chip select goes high or low, whatever, depending on what I needed to do. I don't know, half or full clock cycle before the transaction starts, and then I have my actual SDO, SDI lines that I will read or write to. So, and if we write software to implement like a SPI transaction or something like that, we call that bit banging. So that's something that you can do with very high accuracy, but not with high speed, because you still have to like push all those commands to the device. So you're speaking of like kilohertz range, but that's still useful for many peripherals. There's another reason you can't go super high in the speed, which is not software, but hardware related. Like in the bottom, I've actually zoomed into one of those flanks. And you can see it's not perfect. It takes a while to sort of, you know, go up and then become 1. And it's the same is true on the way down. So takes about 40-something nanoseconds here. We have 2 flanks, you know, rounded up a bit. It's approximately 100 nanoseconds of like transition time, which means that we can't go below that, which means that sort of limits our rate that we can switch up and down at, which is approximately 10 megahertz on these devices. On the X410, like we took great care that that's not the case. You can switch you can toggle these pins at up to 100 megahertz on the X410 without running into these kinds of problems. But then how do you do that if the software is still slowing you down? And we also have a solution for that. So if you want to do an SPI transaction specifically, we now have additional features on the device similar to like a hard SPI core and like a microcontroller, that you can just use to say, okay, instead of saying, hey, I want this pin to go high and then low and high and low and blah, 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 you can just say, okay, this is my SPI transaction, take care of it, and clock it out at whatever rate that, you know, I configure it to. And you can do that. So you're limited to about 100 megahertz, and the actual SPI clock that you can use is always an integer fraction of your radio clock. So in this example, let's say you run at 250 megahertz, so that would be 250 megasamples coming in and out, then you can say, okay, I'm going to divide that by 4, gives me 62.5 megahertz, and then that's my clock speed. So you can do pretty good stuff, not just timed, but also fast. And this is really interesting when you're talking of things like antenna control, like something like, antennas that require code books or something to actually set up with, something that's more interesting to control. Yeah, that's when you would really want to do that. This API is not exposed in Python yet. Talk to us if that's something that you need, but it's available through C++, and it's pretty well described in the manual. I put a screenshot here. All right. I try to leave a little bit of time for questions. So if you have any, I'm very, very happy to answer those now or later. This was, like I said, a very basic intro talk to GPIOs. I could have given the same talk probably 5 years ago, but I hope this will like clear up some questions for some of you. Okay, thank you very much.
So we have one question from the audience. I'm directly handing over to you.
Thanks for the presentation, very good. I have some experience with the GPIOs, and maybe it's more of a comment slash question. Is there a way to, like, you can use the ATR feature, but also configure for the GPIO transition to happen like slightly before or slightly after the radio switches state? The way I've been doing it is I use the timed command, but then it's a little bit more work. You can't just trust the radio to do it in hardware. You have to do it in software, and it's a bit
No,
more.
I'm sorry, that's not possible. The pin. I mean, what you could do is you could like put that delay. If you want to do slightly after, you could put the delay in your circuit, in the electronically. But yeah, like especially slightly before is difficult for obvious reasons. Yeah, I mean, we could probably have a delay in there somehow, but that doesn't come up a lot. So you could probably like have a shift register or something, do that in hardware.
So we have another room question.
First of all, many thanks for the presentation. It was very interesting and explained a lot of things that were a bit fuzzy on the ON documentation. When trying to control the pins over software, right, using the HUG drivers, Python API, or even in GNU Radio over the asynchronous message interface, right? What kind of delays should be expecting from issuing a command to seeing the pin being toggled?
Okay, so you're asking about the delays, right? I'm guessing between sort of software and hardware. So it's similar to any other command, like set frequency, etc. Like you should give it like several milliseconds ahead of time, because in software we sort of packet up the command, and an Ethernet packet has to go over the network and then has to get unpacked, and then it goes into the radio. That's where like time commands come in really handy, because you can say, okay, I can plan ahead a little bit. This has to trigger at exactly this time, but I know like 10 or 20 milliseconds, or even like a full second ahead of time when that needs to happen. That's when that comes in very handy. If you like my first example, or this one here where it's just blinking in a 1 second, like I don't have any, I'm just like sleeping in Python, and you can see it works okay, but like we're talking of like 50 to 100 millisecond like jitter, and you probably couldn't tell just by looking at it. So yeah, you want to avoid that. You use time commands, and then yeah, that's our solution.
So there's one last question.
So all of your examples were using like the Python UHD interface. If I'm using GNU Radio blocks, what's the best way to interact with the GPIO? And
Yeah,
control it?
I think the other gentleman just mentioned that. So obviously C++ or C will let you do that as well. The GNU Radio block has, I think you can send messages to it to toggle that. So just using the message passing interface. Like I don't know the exact API, but I'm sure that's like I think that's probably in the manual actually. I know not everything is documented, but I'm pretty sure that is. So yeah, you send a message command, and you can include a timestamp, so you can do like time toggles that way as well. And there is also a Python API exposed through GNU Radio that you can use, and it does the same as the UHD API. But the message commands, I think that's sort of the most GNU Radio-ish way to do that.
That's true, and also stream tags, right? If you
Yeah. If you, so the stream tags and so in general, like stream tags and messages, they can do the same thing. So you can do in-band or out-of-band messages into a block, and then they will be executed on time. That's probably it, right, Marcus?
That's totally right. Yeah.
Okay. Well, thank you again. And did you have the next speaker? Can I hand the mic
Yes,
to
we
someone?
do. So give a warm hand of applause for Martin. And up next is Josh. Don't hurry too much. I have much to tell before you're on stage. So, Josh is currently with Peryton Labs. He's the heart and head of GNU Radio 4.0 development. And, you know, he's basically running a lot of the project. So that's pretty cool. Couple of things. If you haven't registered yet because you were late and you rather, you know, instead of standing in line, you want to come here, please do not forget to register today. This is really important for us to, you know, gauge attendance. So if you don't have your lanyard and your badge yet, you still need to get that. Then we will have merchandise available later in the lunch break. So if you want a t-shirt that says Washington, D.C. on it, these are the coolest t-shirts that say Washington, D.C. on them. So get them later on. So anyways, I hand off to Josh. Thank you, Josh.
Thanks, Marcus. All right, so I'm Josh. Thanks for the introduction, Marcus. Want to go through just some tips and tricks. So a quick session on some practical things that might help when things go wrong with your GNU Radio blocks. So, you know, a lot of times you'll make your own block, you'll think everything's great, run it in GNU Radio Companion, and just nothing, right? Say, you know, you're early in the process, you haven't added good logging, you don't have good exception handling. So what do? So this is where you want to get to the debugger. Now, for this talk, primarily focused on C++ blocks and runtime errors, so not necessarily compile errors or linkage errors, anything like that. So standard approaches, of course, the best is good exception handling and logging so that at runtime you can see everything. The block API has a logging mechanism, which we'll go over briefly. So every block has a very easy way for you to just either dump to a file or dump to standard out. And that was very recently updated in the 3.9, 3.10 releases. You can examine core files when there's some sort of seg fault, or what we're probably going to spend most of our time here is how you hit breakpoints. So who here uses Visual Studio Code? All right, so about half people. So started the last few years, really, this has become, you know, my tool of choice, and being able to debug GNU Radio blocks in here, hit breakpoints, it's embarrassingly easy. So we'll just go through the basics of how this is done. So when you're in Visual Studio Code, say you've compiled everything with your debug symbols, there's a little button on the side that you create a launch.json file. It's very apparent, and then you add a configuration with GDB launch. So the only two things that you have to do in that file is set the program to Python. Say this is a Python flow graph. If it's a C++ flow graph, the name of the program is your compiled C++ flow graph. If it's a Python flow graph, program is Python 3, and the args is wherever the rendered flow graph from GRC is. So GDB is very straightforward. It takes your current environment, whatever you launched Visual Studio Code with, you know, if you're using some custom prefix. If you're using LLDB, which is another plugin, this requires that you set that environment in that JSON file. And so we'll show an example of that. So here's a little example of setting that up. So we go over here, click that, we're going to debug, create a JSON file if it doesn't exist, C++. Now we're going to add a configuration, GDB launch. I know that was very quick. So I'll go back. Let's go a little bit slower here. I'll pause. So we debug, create a launch JSON file, C++, and then we add this GDB launch. Okay? So it populates all of this stuff for us. We're going to add as the program name, user bin Python 3. Now, this is on Linux, of course. And then the args is going to be the path to the flow graph that was generated here. So we're just going to copy this and paste it right there with quotes. All right, and now all we have to do is run start debugging, and it's going to go. I don't even have any breakpoints here. I just have a program here that's going to segfault. So what happens, we wait a little bit, it runs. It's loaded up all of our threads here. The threads are running. They're caught by the GDB debugger. Oh, and it found our segfault. So we know now where the crash was happening. So that not much we can do here. We can fix that problem. Go back, try again. Let's see. Now, if you want to step through with the GDB debugger, there's a few caveats. One, anytime you're compiling with debug symbols, with debug, no optimization, it's going to kill any runtime performance because there's no optimization. And then with the GDB plugin, if you try to step too fast, it will just disconnect and crash, and you'll have to restart. So if you want to view the contents of the arrays and the pointers, over in the watch window, there's just a simple syntax. You do star, pointer, @, and then the number of elements you want to display. So we'll see an example of this. Okay, so now we're going to GDB launch. We're going to set our breakpoint. Start debugging. Now this goes on for a little while. The GDB debugger is pretty slow for it to catch up, but I will speed this up. And it catches the breakpoint. So now we can go over to the watch window, and we want to look at let's say we want to look at the output pointer. We put star out at 10. It's unpopulated. And then as we step through this for loop, it's going to populate that. You see it right there. I think you can even change values. That's what GDB will do. So this is much, much easier than debugging used to be, say, with like Eclipse or if you're using command line GDB. So our goal is to make developing blocks as easy as possible, and just bring in, and educate whatever tools we have available to make it as easy as possible for people. So the Code LDB plugin won't go into too much detail. The only difference is that you have to load up your environment variables in the JSON file, and there's also a different syntax for viewing arrays. But this one, if you're having trouble with GDB, this one can be quite a bit quicker. It doesn't seem to crash if you step through too quickly. Now, Python scripts, the top level script that gets generated from GRC, this is very easy to step through. All you have to do is select Python current file as your configuration, set your breakpoints, run, and step. And then there's an interactive Python console in the debug, and you can type stuff in. You can launch matplotlib plots, do whatever you want to do. So this one, we're going to switch over up here. We're going to open up what got generated from GRC. We're going to switch over to our add configuration, Python, current file, and we don't have to change anything. Switch back over to the Python file, set a breakpoint, and start debugging. And this one's very quick. Hits the breakpoint, and we step through. So this is not a Python block. This is just your top-level script. So if you've got say a vector sync or something, you can hit a breakpoint, plot some things at the Python level. All right. So debugging Python blocks is more complicated. The reason for this is the way this is integrated into GNU Radio. The GNU Radio runtime, all written in C++, has an embedded Python interpreter that calls out, this is using PyBind 11 magic, and it calls out to the Python block work methods. So you can debug it. I've gotten it to work once, sort of. And the way you get this to work is by using the debug py package. So you can, in your block, you can import the debug py, and then you attach to it. So rather than launching the debugger, you run your flow graph, and then you'll attach to it. So I don't have an example of this running, but you would have to launch your flow graph using something like this command, where you call debug pi, launch your flow graph, and then in Visual Studio Code, then you're going to have an attached to process. And the process ID would pop up, and you pick that one. And it's a little finicky, but it's doable. If someone figures it out, how to do it robustly, please write something up on the wiki. All right, now core dumps, if you don't want to bother with Visual Studio Code, you have a whole nother tool chain. You can examine your core dump very easily. All you have to do is include your debug symbols. And on Ubuntu, you have to type, before you run your script, ulimit -c unlimited. And then run, wait for the inevitable, and then your core dump will show up in different distributions, put it in different places. Ubuntu 22, it throws it into this directory, and then all you have to do is gdb python 3, and then the name of this nasty file, and then it'll show up and show you the whole call stack where it dumped. So example of that we won't step through. I think we've got a logging. So Marcus redid the whole logging system in 3.10, and each block has an object natively in it that all you have to do is say, all you have to do is edit your config conf, tell it that you want debug logging, but every block has this dlogger object that you can just say, rather than doing printfs, because printfs are there permanently, you can't just turn them on and off at runtime. All you do is you say, my logger, I'm going to log at info level, and then it's FMT style formatting. So when we do that, we can get, say we're logging to standard out, or in this case, we're logging to a file, I think. Here, we're logging to a file, so that'll be better at runtime, then we can examine the file, and we see everything. And so those are great. You can put those all throughout your code, and then when things go wrong, you can just examine your logs. All right, one last thing I want to go through, running out of time, is Python snippets. So not so much a debug thing, but if you're not aware of this feature, snippets allow you to insert little bits of code from GRC, so you can do all of your programming from GRC if you'd like. Keep it all in GRC. Quick example of this, I want to replace this Qt time sync with something that's going to just plot a bit of the signal at a very specific time. So I'm going to skip head, and then I'm going to add a head. And so what the skip head is going to do is it's going to drop some number of samples. The head is going to stop the flow graph after it gets some number of samples. And then I'm going to capture in a vector sync. So this vector sync, in order to use the snippets, you have to give the vector sync a name that you put into the snippet. So I'm just going to call it SNK. Skip head, let's skip ahead 3 seconds into the flow graph. And we're going to capture 1024 samples. So now let's do our snippet. So now this snippet block, after it stops, we're going to take a look at that sync, and we're going to plot something. So I will skip a little bit here. I'm going to import matplotlib, and we're going to plot this. The data from everything is in the namespace of self, all of these blocks. We're going to run it no GUI, run it to completion. Okay, now we're going to run it. It's going to take 3 seconds because it's dumping 3 seconds worth of samples. And then it plots something in Matplotlib. So there's another debug mechanism, not necessarily at the runtime crash level, but if you see something funny in your signal at a specific time, that can be really hard to catch in the Qt plots or any real-time plots. So I believe that's all I had. So yeah, here's the snippet and the entire flow graph. So any questions? All right.
Well then,
Perfect.
please give Josh a warm hand of applause. So we're going into a small coffee break until 11. So yeah, see you soon. There's one more thing. Oh, yes, yes, yes. Sorry, I forgot one thing. We have lightning talk slots. If you check the schedule, there's lightning talk slots. That's 5 minutes.
If you just go to the main registration table for details, we have several slots open this afternoon. And it's just a time to share with the community something cool you're doing, an idea, maybe what you want to do over the conference, like you want to meet up with some people. So please stop by. This is something that you just sign up here. Anyone can sign up. So very encouraged.
Yeah.
Testing 1 2 3. Testing 1 2 3.
So we're about to start again. So I know there's going to be a bit of trickle of people coming in. In a minute, we'll talk about a Haystack GSI project, and GSI is a globalized satellite, like a ground station interface that's standardized. And I'm pretty excited about that because these are our two student presenters coming in today, Michael Gutierrez and Maximiliano Riccioli. I guess I spoke that correctly, from Caltech and the University of Texas at Austin. Yeah, so I hope they enjoyed this as much as I did standing on the stage as a student. So please give a warm hand of applause for them too. Thank you.
Hi, everybody. Thank you very much for coming out. I know we just had our 15-minute break, so it's really nice to see people starting to come back in for this. My name is Maximilian Riccioli. I'm a third-year undergraduate at the University of Texas at Austin studying electrical engineering.
I'm Michael Gutierrez, sophomore at Caltech. Michael Gutierrez, studying astronomy.
And today we'd like to tell you a little bit about this project that we helped to develop at our internship at MIT Haystack Observatory over this summer. Sort of this satellite communications hub built around GNU radio processing. So here's a map of our presentation. We'll be starting at the left. I'll give a little introduction to our satellite mission as a whole. It's a little bit unique in terms of satellite missions, so we'll talk about how that kind of motivated the development of our very general ground station interface here to process for different types of satellite missions. And then about halfway through, we'll switch over to Michael, who will tell you more about the actual GNU radio implementation, the nuts and bolts of this thing. So, a little introduction about MIT Haystack Observatory. It's a multidisciplinary research facility, and one of their disciplines that they research is geospace, which very broadly is the study of space weather. So kind of the interactions between the solar wind and the magnetic field and the ionosphere, the atmosphere. Anything above the Earth, not too far away, they'll look at it, right? So one geospace phenomenon that you might be familiar with is the aurora, the northern or southern lights. This is an optical phenomenon which occurs at the poles whenever high energy electrons come in and interact with neutral particles, causing, again, this optical disturbance. This is around 150 kilometers altitude, but if you go up to around 500 kilometers altitude, you'll actually find a radio aurora. So this is interesting, right? Not as many people are familiar with this as the, pretty northern lights, but it's just as real. And we can detect it from the ground on occasion. But what's interesting is that plasma physics and radio propagation theories both predict that this should not be possible at all. It should be completely attenuated by the time it reaches the ground. So MIT Haystack really wants to study these phenomena, because of course, whenever you have observations that go against what your model predicts, that's where the most interesting science occurs. But part of the issue is that even though we can receive these signals on the ground, a lot of the important characteristic information, like their polarization and their angle that they come from, can get lost or muddied on the way down. So we need a way to more directly observe these radio aurora, which brings us to our satellites, which are planned to go into low Earth orbit. That's between 200 and 2,000 kilometers. And these will be able to get us clear access to observing this radio aurora from the top down, so we can not have it blocked by the atmosphere, basically. In order to do this, and just like I mentioned on that last slide, in order to get this polarization and incidence angle information, we'll be using electromagnetic vector sensors, which very broadly are one element which can discern all 6 dimensions of the electromagnetic field, XYZ electrical, XYZ magnetic. And from this, you can process out polarization and the incidence angle. And this will allow the scientists to test their different theories about how these emissions are created. So Arrow and Vista, that's the name of these satellites. These will be the vessels for these vector sensors. You can see on the little mission patch there, those crosses at the top of each of those satellites, those are the vector sensors. They'll kind of expand out from the satellite. Arrow, just as we discussed, its primary mission is to observe these radio emissions high up in the atmosphere. But Vista is actually an interferometry experiment to hopefully improve the data acquisition of Arrow. which interferometry is a whole entire field of research on its own. But very, very broadly, if you have two observers watching the same event, you can more than double the data output or the data resolution from it using interferometry techniques. So these satellites will be performing interferometry in space. It looks like the GIF didn't load, but in the top right, here was, yeah, it's a PDF. This was supposed to show the vector sensor kind of exploding out from the satellite. It's really an engineering marvel that they fit this whole thing into such a small satellite, both of which, Arrow and Vista, are CubeSats, 6U. 1U is 10 centimeters by 10 centimeters by 10 centimeters. So each of these satellites is 6 of those, so 20 by 30 by 60 centimeters. And they fit this whole really like 2 meter by 2 meter antenna into it. It's kind of amazing. Yeah, it's huge. As discussed earlier, we'll be performing interferometry on the experiment, but we need to basically have 6 streams of IQ data coming down from the satellite in order to do that. So that's a huge amount of data that will need to be processed by our ground station, which of course leads us to talking about our ground operations. So for any spacecraft mission, Arrow included, one of the most important tasks is ensuring that you can actually talk to the satellite. Because if you put it up there and you can't speak to it and it can't speak to you, then you've basically spent millions of dollars and thousands of man hours to put space junk in space, right? So we're going to use a ground station. We're going to use MIT's and various other collaborators in order to uplink meaning up from the ground station to the satellite, mostly low volume telemetry data and command data over UHF, which is on the order, as you can see there, of around 10 kilobits per second. And we'll also be downlinking, called that because it goes down from the satellite to the ground station, UHF telemetry data and health data, so letting us know what the satellite is doing at any given time, as well as downlinking over X-band, our experiment data, as discussed before, this IQ data. So fortunately for us, that wasn't really our project. The ground station hardware is pretty well set up as it is. Again, as I said, there's a lot of collaborators on this project, one of whom is Morehead State University. That's one of the primary dishes that we'll be using. It's a 21 meter. And yeah, we'll also be using the 18.6 meter reflector at Haystack, which has its own phased array feed, which has previously been used a lot for radar and satellite tracking. It'll allow us to kind of beamform and track these satellites with greater precision than you could just by angling the antenna. And there's also a cryogenically cooled X-band receiver, which only receives right now because in the past it was used mostly for sort of measurement experiments, again with this geophysics and the other disciplines at Haystack. But hopefully it'll also be transmit by the time that this mission goes into orbit. And all of this feeds into a big stack of Edison 310s that live down in the server room underneath the ground station. Do you want to?
Oh yeah, I was just going to highlight that. Is this on? Oh, hello. Yeah, so we have a very diverse array of hardware that we want our software to work with. So that kind of defines, as we'll get into, GNU Radio really helps us to have compatibility for all of these out of the box.
Exactly, yes. One of the reasons why we ended up going with GNU Radio for our ground station interface, we'll talk about this a lot more later, but the hardware that we're using is pretty diverse, and we feel like this could be kind of extended to even more hardware, even outside of what we have. So our second objective then is to have a way of conveniently talking with the spacecraft. A sort of unique problem with low Earth orbit is that your satellite passes are very short. After coming up over the horizon, you can only have between 5 and 15 minutes to actually talk to this thing. So any mistake that you make could also turn it into space junk, right? So it's really unnecessary. It's not the best to have a human doing this within this 5-minute window. because you don't want any mistakes to be made. But there's no real solution to this quite yet, it seems. Currently, what mostly happens is you'll either use a bunch of disconnected software in order to facilitate all this. So you'll be copying and pasting values between each window. You can see that on the bottom left there, sort of this one-off solution just for the mission. You can shell out a pretty significant amount of money for a proprietary solution, but other than causing a recurring cost, that can actually sort of lock you into using a specific vendor through your whole mission. And it's nice to not have to do that, right? You want flexibility. And if anyone here is familiar with satellite operations, NASA's OpenMCT does support scheduling, but it actually doesn't support any of the radio side. So there's no easily configurable pre-built solutions for this issue, which really brings us to why we were developing the Haystack ground station interface in the first place. So I'll hand it off to Michael here.
Yes, no easily configurable pre-built solutions until now. So this is the Haystack ground station interface, which we're working on. Well, we plan to open source it once we finish developing it, but the idea is that it's human readable and extendable to any satellite mission. So even if they say another university or science team doesn't have our exact satellite hardware, and obviously they won't have access to the specific satellite dish that we do. Actually, the UHF phased array feed that we have, there's only one in the world right now because it was custom built. But yeah, so we are building this, like I said, with GNU Radio at its core because it's very human readable. You can load in, the idea is you load in one configuration file or flow graph or what have you for specific to a satellite, and you can hot swap whatever signal processing and data syncs and sources that you need. So yeah, the critical thing is we want to keep it human readable because yeah, we don't want to, in case there's a contingency or like you need to change something quickly during a satellite pass, you don't want to have to dig through the source code. So I'll give some specific examples of kind of the problems that we were working with in building this software. So one of the most important things is the packet processing, because so this is after you have the radio signals downlinked from the satellite and you've demodulated them into a bit stream. There's a million different ways that you could package those up into a packet where you might have preambles and sync words and data scrambling and error correction and all of this. And there's a huge diversity of those different systems throughout all kinds of different satellites. So, and we want to be able to support all of them with minimal configuration. So first thing we tried was there are some built-in GNU Radio blocks for this. They didn't quite fit our purposes because most of them use tagged streams, more like in a synchronous manner. And for ground station operations, it's very much asynchronous because you're not going to have data constantly coming in. It's going to be coming and going. So to that end, we built a bunch of custom blocks that used asynchronous message passing system. So we utilize a lot of tools from the GNU Radio Satellites package by Daniel Esteves, which was really great. And we also built lots of our own custom blocks that are all of them take in one configuration file. In this case, you outline the packet format that you want to decode. So you say, oh, the first 8 bits are the length, and then the next 8 bits are the type field, and et cetera. And yeah, it's much easier than creating, for example, a packet header object in each flow graph custom. So we wanted to abstract it out a little further. So, and we found that the GNU Radio higher block infrastructure is really, really effective for doing this. So, for example, again, we have one config file. So on the right there, That outlines like pretty much all of the communication parameters for a given satellite. So it's like, oh, we're going to use the UHF radio. This is the sync word, and it's going to use FSK modulation with the frequency offset of this, etc. And all you have to do is load it into this one Haystack GSI block, which is part of the out-of-tree module that we're developing. And it will automatically build this entire receive chain for you. So you don't have to click and drag every individual filter and clock sync, etc. Yeah, so essentially we're going for user-friendly interactions. Ground station in a box, as the slide says. The user should not have to have really deep signal processing knowledge in order to perform the actual basic functions. But of course, if you do need to change some low-level settings, those are still accessible. And then on the other side of this, so after we've decoded the payloads, we want to, so in AeroVista's case, we want to send it off to a Redis database so that the science team and the mission ops can access it. So what we had been doing before was using a lot of ZMQ. So we would send all of the byte stream into a ZMQ sync, and then we had to have a Python script that wrapped the entire flow graph to receive from ZMQ and then send off to Redis. And that it had a lot of moving parts. It was very cumbersome, hundreds of lines of code to deal with multiprocessing for different flow graphs, et cetera. But we realized we could just write a custom block to send the byte streams directly to Redis, which simplified things a lot. And it really simplified it a lot in terms of the lines of code. And it's this kind of scheme is really expandable to, it doesn't just have to be Redis. It can be theoretically send data wherever you need to. So that's kind of what we've been working towards. So with an eye to future development, the end goal really is to use the GNU Radio Companion as a user interface, essentially. The visualization is having the ground station operator as like an old-timey telephone switchboard operator. So say you have like science data coming down on the X-Link band. So the operator can connect up the X-Link radio and send it off to the, we're using this packet structure, so we plug it into this demodulator, and then, we want to send this to the science cloud, so we'll plug it into this database sync. And then on the other side, if there's instructions coming in from mission commands, then we can pull from that scheduler database and then put it through the UHF demodulator and send it right back up with minimal configuration of the low-level parameters. So on that note, so Max and I we spent a very large amount of time staring at GNU Radio Companion this summer, 10 weeks, multiple hours a day. So we have developed a few quality of life improvements to GRC as a whole that we hope we can integrate into the main branch at some point. So we added dark mode because, again, 6 hours, 6 to 8 hours of staring at the screen, the white background tends to singe the corneas a little bit. And then also with an eye to accessibility, we added color-coded blocks depending on their function, which really helped read like the functionality at a glance, which is again kind of what we're working towards, the human readability of it all. And then with more towards the functionality end, we want to expand the block user interface a lot because right now it's mostly static. Like you can hide and show some parameters depending on a drop-down, but an example that we were playing with here on the screen is it's a packet parser block that starts out blank. You import a YAML configuration file detailing different packet protocols, and then it'll read that like in compile time basically, and present you with different options based off of that. So yeah, we think it could be a lot more dynamic. So we have some of this stuff implemented in our own GNU Radio branch, but don't actually know how to integrate that with the dev branch. So I'll have to connect with somebody about that. Yeah, so that's about all we have. We just wanted to highlight some resources that we found very helpful. In particular, wanted to give Mark Lichtman a shout out at the AAB booth. His PySDR website was supremely helpful because I don't know, at least for me, when I was coming in over the summer, I had zero knowledge of DSP. I was opened up GNU Radio and I was like, what is a filter? So that, yeah, we had the PySDR tabs open, I think, probably just the entire summer, like never closed it. So, and then, oh yeah, as I said, Daniel Esteves' GNU Radio Satellites repo and blog were very, very helpful. Integrated a lot of those tools.
Ryan Voles developed Radioconda, which was super useful for us. He was actually one of our mentors at MIT Haystack, so it was really interesting to talk to the guy who made it, and we're also using his package, right? But other than that, I think that's all we really wanted to talk about. So thank you all very, very much for listening to us. And if any of you have questions about sort of the satellites or the ground station or the GNU Radio operation of either of these things, we would love to take them right now.
So, any questions in the room? Yes, the gentleman in beige.
So I've been working with the protocol formatter for quite a bit, and it was one of the most tedious things to work with because they're not all, the blocks aren't compatible with other blocks. So something like the header payload demux did not work as expected, and it took a lot of trial and error to get to something like that. I guess my main question is, what was your experience with those blocks, and more so, how did you replicate them?
Yeah, so like I said, the way we were kind of importing the data was asynchronously. So we had like a USRP source coming in with just the raw modulated data, and I think we used like there's a GR satellites block, which is like sync to bytes sync to PDU, sync to packed PDU, which takes in bytes and then looks for the sync word and then crops it at the appropriate length and sends it off. So we kind of were, by the time we wanted to process the packets, it was already in PDU form. So that was a little bit difficult with the built-in blocks because they pretty much only have support for like, oh, the header is this long, and then you can maybe check the CRC. But we wanted to add support, like easily configurable support, like all using the same block for as many different protocols as we could. So yeah, that was the main motivation behind not using the built-in blocks.
So before we continue with in-house questions, there's an out-of-house question that asks, like, what's the advantage of Redis, of using Redis in your setup, seeing that this is like another message distribution thing?
Yeah, sorry, I didn't hear all the questions.
Sorry, seeing that Redis kind of is also distributing messages and state and stuff.
Oh, why did we use Redis? Yeah, so actually I can go back to the other slide, the diagram. So this is kind of like the whole overview of the entire project, and we really worked mostly on just the little GNU Radio box down in the bottom, but the Redis server is kind of what's going to connect the ground station to everything else. So we're going to load all of the, for example, the telemetry and health data into NASA OpenMCT. Oh yeah.
No, keep going, sorry.
Oh, I guess there's also two microphones. Yeah. And then we're the Redis server also is going to interface with like the file transfer function. So if we need to upload like new firmware or whatever up to the satellite, then that'll also go through the Redis. And also for like any automated mission control software, like for example, we use Nano MCS from Nano Avionics because that's what the Aero and Vista satellites are use Nano Avionics M6P buses. So we can also hook that up directly to, well, almost directly to Redis.
And a lot of the specific motivation for using Redis was to be able to kind of dump in commands onto a Redis sort of receive stream, which would be picked up by this ground station software transmitted. And then at some other point, it would dump in these received commands back into a Redis downlink stream. So the point of Redis was to make this asynchronous and also able to be accessed from different locations, sort of, so that way our partners, you know, at Moorhead, thank you very much, excuse me, at Moorhead could interface with it and perhaps, you know, transmit, get things ready to transmit over our dish as opposed to their own, right? So just kind of distributing this, it made it was a lot easier using Redis.
Okay, thanks. Then there was an in-house question, I think here somewhere.
When's your launch date?
That's a good question.
I believe it's 2024 or 3. I don't exactly remember. I'm sorry.
Well, theoretically, this will be done before that because we're also going to be using at least the ground station at Haystack to track other satellites. Yeah, we think it's going to be like a backup center for NASA because we got like a NASA SDR set up in there also. So,
So Derek actually asked, said that your YAML format for like the form, like your YAML definition looks like it has a lot of overlap with, you know, SAT YAML from other projects. Is there like some advantage to maybe, you know, coordinate and merge these formats?
definitely, yeah. Actually, I mean, I started writing a lot of this code as like within the GR satellites package actually, and then it got too different, so I turned it into another entry module. But definitely, definitely a lot of this is reliant on other packages, and would definitely love to, yeah, combine efforts.
Okay, is there another question in the house? Then we have a time for a question online, and it's been asked whether like there's a lot of overlap with what SatNox basically does as a distributed array of satellite ground stations. Do you feel like you reinvented the wheel a bit out of necessity, or is that just intentional, or are you doing something different?
Sorry, I'm having trouble here.
Yeah. Okay, sorry, that's sorry. There was a question whether you're not replicating the effort that SatNox does, basically, and whether you feel that's intentional or necessary, or just too separate a problem to solve.
Yeah, SatNogs definitely is a really great program. So we also, in this presentation, we focused a lot on the receive side, but just as important is going to be the transmitting side going back up, which I don't think SatNogs does. So yeah, we want to be able to transmit commands. And
really a huge focus of this project is getting the infrastructure in place to be able to transmit. So that's a really huge consideration and also a really huge reason why we built a lot of it in GNU Radio.
Okay, cool. Is there another question? Otherwise, I'd say we give the speakers a big round of applause again, because, you know, students.
Thank you very much.
Thank you.
So we have a very relaxed handover. You can choose. We have a very relaxed handover to Arion Zuccio from Analog Devices. So he's been with ADI, I think, like about 6 years, right? He has been with ADI, I think, like about 6 years, right? He has been with ADI, I think, like about 6 years, right? He has been with ADI, I think, like about 6 years, right? He has been with ADI, I think, like about 6 years, right? He has been with ADI, I think, like about 6 years, right? He has been with ADI, I think, like about 6 years, right? He has been with ADI, I think, like about 6 years, right? He has been with ADI, I think, like about 6 years, right? He has been with ADI, I think, like about 6 years, right? He has been with ADI, I think, like about 6 years, right? He has been with ADI, I think, like about 6 years, right? He has been with ADI, I think, like about 6 years, right? He has been with ADI, I think, like about 6 years, right? He has been with ADI, I think, like about 6 years, right? He has been with ADI, I think, like about 6 years, right? He has been with ADI, I think, like about 6 years, right and he's going to talk about a GNU Radio on the go, right? How to get GNU Radio onto Android devices. And I know this has been, an exciting problem for a lot of people. So, and I know it's all, there's a solution. It works very short term, and things get better by the way. And I know that ADI, and I guess you personally have a lot to do with Scopy and how that fits in. So I'm really happy to see you on stage. So hands off to you.
Thanks. Oops, can you hear me? Yeah. So like Marcus said, my name is Adrian. I'm working for Analog Devices, and I'm going to show you how to build basically Android applications with GNU Radio. So the motivation for this project was to run the Scopy application on Android. So if you don't know, Scopy is a Qt-based application that uses the ADLM 2000 hardware to implement a bunch of virtual instruments. So it's basically like a lab in the box, electronics lab in the box. It has an oscilloscope, it has a signal generator, a voltmeter, power supply, spectrum analyzer, network analyzer, different types of instruments that you would use in an electronics laboratory. So most importantly here is that we use GNU Radio for signal processing and data acquisition using GRIO and GRM2K modules. So for this presentation, I used Scopy to exemplify how to build Qt GNU Radio apps for Android. So running GNU Radio on Android is not really a new idea. It is based on previous work done by Tom Rondeau in 2015 and Bastian Blösel in 2020. So this provided us with a very good starting point and a build recipe for GNU Radio 3.8. So our work adds on top of that work by adding support for GNU Radio 3.10, IO device support. We also added support for GRQT GUI on Android, so you can use the GUI pieces bundled with GNU Radio to build your own applications. Also, we have Python support. So basically, it allows you to write flow graphs in Python and then run them on Android. So just a disclaimer, I'm not a subject expert on Android or SDR or much in general, but there may be some inaccuracies in the slides, especially about how Android works, but it shows my understanding of how I built everything. So before we begin, I'd like to say a few words about Android. So Android, it is a Linux-based operating system designed for mobile devices. So, these devices usually have a high-performance CPU. They have different connectivity options. You have cellular or Bluetooth or Wi-Fi. You have storage and a big screen on them, and they're self-contained and they run on a battery. So this can make them pretty interesting for software-defined radio applications, mobile software-defined radio applications. So when doing Android development, you need to install the SDK, which consists of Android libraries and tools. So the tools here are stuff like Gradle, which is the build system that converts from Java to eventually an APK, an Android application. You have an emulator, you have ADB, which is the software used to communicate with Android and debug Android devices. Additionally, if you want to compile C++ libraries into your application, you need to install the NDK. So the NDK is the native development kit. So this is basically a cross-compiler toolchain, which has all the necessary utilities to compile libraries for Android. And this is what we use to compile GNU Radio. So what exactly is an Android application? Well, an Android application is a piece of software that runs on the Android platform. So they can be written in Java or Kotlin and are distributed as APK files. So APK files are just fancy zip archives that have a few key files. So there's the classes.dex file, which is basically the Java executable. This is where the application is implemented. DEX stands for Dalvik executable, Dalvik being the Java virtual machine that is running on Android. There's also the Android manifest.xml file, which is sort of like a descriptor file that shows how the application interacts with the with the Android operating system. So here you find stuff like the application name, permissions, what activities are started when the Android operating system runs your application, and this kind of stuff. There's also a few other folders in there, but most importantly, the libs folder is where the native libraries are stored. So the native libraries are C++ libraries that your application may use to perform different tasks. So GNU Radio, libio, Qt, all of it is bundled in this folder. So I'll now show you a brief overview of how Qt runs on Android. So Qt apps are C++ applications that make use of the Qt framework. But if Android apps are written in Java, how can Qt run on Android, because it is C++? So what I noticed is that Qt does a clever trick here, where it actually, instead of compiling the application as an executable, it compiles it as a library and puts it together in the libs folder with the other native libraries. So when you start an Android application, basically a Java loader powers up, which loads your Qt application, and then at that point, the C++ space pretty much takes over. There is some interaction between C++, the C++ domain, and the Java domain. Basically, sometimes the Android operating system, you may want to do something in the Android operating system. You want to create a notification, or maybe the Android operating system requests killing your application or something like this. And this is where the Java native interface comes in. This interface basically creates like it basically eases communication in between the C++ and Java space. And from a source point of view, Qt projects are basically CMake projects. So CMake generates build recipes for the application library as well as the APK. So there are two important pieces in Qt Android projects. First, you have the C++ sources, which will generate the application library which will be bundled with the rest of the native libraries. The same sources will generate the same application executable on PC. So you pretty much have the same source that's running on both Android and PC target. Second, there's the Android package source, which is an Android-specific folder for Qt project. And in this folder, you basically have the native libraries. You have instructions to build the APK in build.gradle. You have resources. You have the native libraries. You have Android manifest.xml. So yeah, I know that this looks a little bit complicated, but Qt has boilerplate implementations for everything. So if you just want to get started with Qt on Android, it's as easy as doing new project, compile, run, and then you can start your application on both PC and on the target, the same C++ application. So Qt takes care of everything Qt related, but when non-Qt libraries such as GNU Radio are involved, we need to build them separately with the NDK and bundle them together with the application. So while experimenting with Android, I developed this workflow where basically once you install all the necessary tools and compile the dependencies, you can code your application in Qt and then test, like I said, the same application on PC and on Android target. So this makes it pretty useful for debug and test purposes. So we use this workflow to get Scopy up and running on Android. So Scopy has, similar to GNU Radio, Scopy has lots of dependencies, and their dependencies have lots of dependencies. Usually on a Linux PC, all of these dependencies are handled on using a package manager. But on Android, we need to compile almost each of these dependencies ourselves. So there are multiple build systems involved. You have CMake, AutoTools, QMake for building the libraries. But you only really need to do this once. So once you compile all of the dependencies, you should be up and running. So some patches needed to be added to these dependencies because they were not really meant to run on Android. But in the end, we managed to compile GNU Radio using the recipe from Bastian and Tom's previous work. And besides GNU Radio, we ended up compiling GRIO, GRM2K. We compiled Python and libcgrok decode because Scopy uses Python and libcgrok decode to do logic analysis and protocol decoding. Also, we compiled the QWT and all of their dependencies. And in the end, we sort of created like an environment which compiles these dependencies, and this environment was also used to compile Scopy itself. Yeah, so before I show you what Scopy works like on Android, I wanted to talk a little bit about GRQT GUI because Scopy uses a modified version of GRQT GUI to plot things on the screen. So because screens on Android devices usually have higher pixel densities than on PC, we needed to enable a feature in Qt which is called GUI scaling or Qt scaling or something like this. So basically when the application is running on a high DPI display, everything is very spaced out and looks kind of small. And the scaling mechanism brings everything closer together so it looks more and more natural on Android screens or high DPI screens. However, we noticed that when enabling this, we get very, very bad performance, especially in the FFT plot. So after some profiling and benchmarking and debugging, we found out that the problem actually originates in the QWT library because it tries to scale the plot that's being drawn on the screen. So for each pixel, it computes positions of different pixels. So when you have lots of pixels on the screen, there's a lot of computation that's going on that's kind of choking the CPU. So the solution here was to enable OpenGL rendering in QWT and eventually in GRQT GUI. So with this optimization, basically it removes the bottleneck. We use the GPU to plot, and this frees up a lot of CPU cycles for GNU Radio to actually do computations and not plot stuff on the screen. So another quick word about libUSB. So libUSB is used by libIO to handle USB device support. So due to the security model of Android, you cannot access USB file system directly on Android, but you should use the Android USB manager. So there's a pull request with libUSB that handles, that enables better Android support. That's actually the name of the pull request, better Android support, which takes care of this for you. It basically makes it transparent for the developer whether it's accessing USB from an Android platform or for another platform, so you can just write your driver once. Yeah, after compiling this better Android support version of libUSB, we can just use the regular USB driver. So in our case, this driver was actually libIO, but we simply just needed to add a small snippet telling libUSB how to access the JNI, the Java space that I previously mentioned in order to access the Android USB manager. So after adding permissions to USB in Android manifest.xml, things went pretty smoothly. So using this version of libUSB greatly reduced friction when using drivers, and you can pretty much use the drivers right out of the box. In the end, we managed to build everything. Scopy is just a library for the Qt application loader, So there were a few changes that were needed in the source code, specifically in the CMake project to make CMake aware that we're actually building for Android. But the rest of the modifications were just interactions with the Android API. So stuff like permission handling, USB handling, notifications, because Scopy creates a notification when you send it back to, when you send it to sleep, but the device is still running to tell you, hey, your device, the device that you're running might be draining your battery. So it creates a small notification for that. So now I'll show you a demo of Scopy on Android in action. Basically, this is a screen grab from my Android tablet, and Scopy requests access to the USB interface, and once you grant it, the device shows up on the screen. You can connect to it. It takes a little while to calibrate, but this calibration procedure takes a lot even on the PC, so I mean, that's fine. Once the calibration is done, I can go to the signal generator, generate a waveform. So in this particular case, I'm generating like a 2 megahertz waveform. I run it, and I have a loopback between the signal generator and the oscilloscope, and I can just view the waveform and maybe do measurements with it and different kind of stuff. So again, the same thing in the spectrum analyzer. You can see that the spectrum analyzer is definitely not 1 frame per second, but it's kind of smooth. So this is because of the QWT OpenGL optimization that we did. So yeah, all in all, it worked out fine. You can see the demo at the Analog Devices booth, where we have Scopy up and running on a tablet. And yeah, we eventually published Scopy in the Google Play Store. So we developed both 32 and 64-bit of the application and published it to the store. So publishing to the store kind of has its perks because Google provides automatic tests for your application, and you just upload an application, and then they run tests on different devices. I imagine they're virtual devices, but they run tests on different devices, and you get a report what device it crashed on and why. So this is kind of useful. And also, Google provides a crash report collecting system. So basically, if you install the application and it crashes on your phone or tablet, Google sends an anonymized crash report which contains a stack trace to their servers. So we can analyze it. So we can analyze the full stack trace which happened on your phone. And this makes it that we actually caught bugs in the software because before they're actually reported by the users, because the crash collecting system send the stack traces beforehand. So in the end, the work is contained in 2 repositories. It's Scopy Android Dependence, Scopy Android Deps, and GNU Radio Android, which is basically a fork of Bastion's work. So this repository contains some test applications and some scripts to initialize the cross-compile environment, to build all the dependencies necessary for Scopy. It has Docker recipes to build Docker images that set up the environment. And then there's a special folder called Android Application Helper Scripts. Basically, what this folder does is it provides tools to help you get started with Android applications. So it contains an example CMake lists file, which configures a CMake project for GNU Radio, libUSB, libIO. It has a Android CMake script file, which is basically a wrapper for running the CMake command on for compilation on Android. Has Android manifest.xml, the Android folder, which has Android configurations I previously mentioned. And there are also some scripts that help with copying the libraries in their correct places and generation of the APK files. So I previously showed you this workflow, and after some development, you only really need to code your application in C++ and test it. You let Docker and the scripts take care of the rest. So we can code the application once, test it on PC, and then run the scripts, and you have the Android APK generated for you. So you probably know that GNU Radio also ships GNU Radio Companion, which is a nice GUI application to create and test flow graphs. So you can also create GUI applications with GNU Radio Companion using GRQT GUI. So the companion also has its own C++ code generator. So you can actually has a C++ and Python code generator. So you can create your flow graph and then generate code out of that flow graph. So upon C++ code generation, a similar project like previously mentioned is created, a CMake project, and some sources which represent the application. So we can then take this generated code and apply the Android app helper scripts that we developed in order to create this Android application. So this makes it that you just create your GNU Radio flow graph in the companion, and you can generate Android APKs without writing much C++ at all. So this works great, but the problem here is that not all blocks have C++ implementations. Some of them only have Python implementations. So if you try to put in a block which has only a Python implementation in the C++ code generator, you get an error. And this was kind of a blocking point for us. But then we realized that we actually ship Python with Scopy because we use Python for the logic analyzer and protocol decoding pieces. So the question that we got is, can we make a Python runtime that supports GNU Radio on Android? So I checked out the Python dependencies needed for Python support. So there are NumPy, there's PyBind11 and PyQt5 and their dependencies. And if we build those, things should work. And we did that. So at this point, things are a little experimental, but I think they are still worth presenting because it shows how you can actually build Python flow graphs in GNU Radio. So in order to build the Python packages, I used the CrossEnv package, which basically creates a special kind of virtual environment that cross-compiles and that is used to cross-compile and deploy Python packages to an embedded target. And once you compile Python for both the build machine and the target machine, you can use it to install packages with pip. So this works great for Python-only packages, but you can also use setup tools for packages that need some compilation with Python. So the resulting virtual environment can be deployed to an embedded target, which in this case is Android. And I used this CrossEnv package to build and install NumPy and PyQt5. PyBind11 is not technically a Python package, but rather is a C++ library that creates Python bindings. So the installation of this library went pretty smoothly. However, in practice, I got some weird undefined behavior, especially when using hierarchical blocks. And the solution was here to use a different branch of PyBind11, which is called the smart holder branch. So this branch modifies some aspect of smart pointer lifecycle in PyBind. The problem here is that this branch uses a different syntax for generation. So I needed to port GNU Radio and all of the out-of-tree modules that I use in this project to the new syntax. But eventually things worked out. I left because Marcus was laughing. So eventually I created this very crude application, which is called the GR Flow Graph Runner. So this application is like super simple. It has very bad error handling, so it crashes like a lot. But in the end, what this application does is that it loads a Python file and runs it. It's as simple as that. So ideally, that Python file would have a GNU Radio flow graph in it. On Android, it also bundles the full Python runtime. So you get a full Python interpreter in this Android application. So in the end, running a flow graph on Android is simply reduced to creating a flow graph in the companion, loading the resulting Python file from the Python code generator into the GR flow graph runner application, and that's it. You can run it. You can even go further. You can set up like a sync between your PC and the Android tablet or the Android device, something like Google Drive or Dropbox. You work in that folder, and then you always have the latest version of your flow graph that you've been working on and testing on PC, and you can test it on the Android tablet. So it's like pretty seamless. Yeah, so like I said, I promised you that I'd show you how to create your own FM receiver transmitter. You just create it in GNU Radio Companion and use the code generator either for Python or for, you use the code generator for Python to load it into the GR flow graph runner. Or alternatively, you can generate C++ code and compile it to an APK using the scripts I provided. So this is a small demo of the FM receiver transmitter. Here I created the flow graph for an FM receiver, and I connected a Pluto to the Android tablet. And then I used the walkie-talkie to talk to the Pluto and receive what I'm talking. The GNU Radio flow graph demodulates my voice on Android, and you can hear it on the speakers. So like I said, the application is kind of not that good. So you need to actually press the load button twice, first to grant permissions to the USB and then to load the flow graph. But once you load it, the GUI shows up, and this GUI is the same GUI that's I created, and it's the same it looks like on the Android PC. Now, I don't know if we have sound, but here I say, hey, testing. Yeah, there I said something like, make sure you stop by our booth and check out this demo as well. So, in the end, getting up and running is a little complicated, so I created Docker images to help you get started. So these Docker images are also useful for documenting the setup because you have to install a lot of stuff. And also, the Docker images were super useful to integrate in our continuous integration infrastructure. So once we commit to a code change to Scopy, we spin up the Docker image to generate APK files, like 10 minutes, you get an APK within committing your code. So it's pretty useful for testing as well. You have links for the Docker images, you have links for the repository, and yeah, this is about it. We can use Qt to reliably create cross-platform applications, including on Android. And with this approach, you don't need to write that much Java code. I mean, in some cases, not even that much C++ code. You just use the companion. On top of previous work, we added support for GNU Radio 3.10. We implemented OpenGL in GRQT GUI, and we added Python support. So most importantly here is that this project can be extended by adding more libraries and adding more modules to the project and to the Docker image. In the end, yeah, it was a very interesting project. I learned a lot about Android and cross-compiling, and in some particular cases, I learned a lot about myself. Yeah, thanks. And this is it. Do you have questions?
Are there any questions in the room? You're a strange room.
Sorry for speeding you through the presentation, but I just finished in the nick of time.
That was on point. So anyways, yes, so see analog devices over in the vendor area. Before we head out to lunch, I shouldn't have said that first. Anyways, before we head out to lunch, a couple of announcements. I've been kindly reminded that we're kind of 2 blocks away from the White House. So if you're operating an SDR, SDRs some SDRs can transmit. Few SDRs have proper output filtering. There's a talk by Robin Getz, who's probably also over the edge, from GRCon 2017, which you want to watch before you transmit on frequencies that you think are safe. If you want to legally transmit, reminder, there's the ham radio exams, and you can get a license to actually transmit. Talking about signing up, there's still Lightning Talk slots available. At least today, there's 3. We have Lightning slots, talk slots on other days as well. A Lightning Talk is really just to walk on stage. You have slides, you don't have slides, doesn't matter. 5 minutes, you talk about what you want to talk about, as long as it has something to do with SDR, or might be just interesting to a majority of attendance. That's fine. So if you want to do that, just see the registration desk. They will tell you how to arrange for that. Also, at the registration desk, you can buy T-shirts. How that works is you basically just order them online and have them handed over to you as soon as you can show the order confirmation. So there's no money handling at the venue. You just order to the website there. There's an extra charging area in the Ohio State room. So that's the Capture the Flag room. So if you have something that you need to get done there, please head over there. So with that, I'll dismiss you to lunch, I guess. That's right behind the curtain. So leave through that door, or please don't. You can also go through that door. Please don't congest that too much. And we'll be back after the lunch break at exactly 1 o'clock. See you then.
I'm gonna come down.
Good afternoon, folks. It is 12:58. In about 2 minutes, we're going to get started with the next talk. Now is a great time to refill your coffees, make sure your laptops are charged up, and we're going to get started shortly. Excellent. It's like that time at the bar where everybody suddenly stops talking as the music stops. Welcome back to the first day of GNU Radio Conference 2022. Today we have Luke Bogner from Peraton Labs going to talk to us about open source large-scale radio frequency machine learning data sets, tools, and models. And as somebody with an intrusion detection background, this sounds really exciting to me. So please give a warm welcome to Mr. Luke Bogner.
Thank you, thank you. Is this guy on? Can you hear me? All right, awesome. And looks like the slides are good. All right, so hello everyone. My name is Luke Bogner. I'm a research scientist at Peraton Labs. And this talk I'm going to be sharing some of the work that I did with my colleagues at Peraton Labs as well as colleagues at the Laboratory for Telecommunication Sciences. So the title of this talk is Open Source Large Scale Radio Frequency Machine Learning Dataset, Toolkit, and Models. Just a quick disclaimer is that it should probably read almost open source. So we're still looking for one more checkbox for getting this work released. It should be any minute now, though. So hopefully we at least have some things for you to look forward to. So on the agenda today, I'm going to focus in on narrowband radio frequency machine learning. So this is kind of, we're adopting the standards of narrowband versus wideband RFML that's been in several works in the literature where narrowband RFML focuses in on signals that have already been kind of extracted, isolated, coarsely basebanded, versus wideband RFML where we might be doing tasks that involve multiple signals that may or may not be overlapping in time and frequency. So for this talk, we're focusing on narrowband RFML, and in particular, there's three pieces that I want to talk through. The first one is the SIG53 dataset that we're introducing. The second piece is TorchSig. It's the soon-to-be open source machine learning toolkit for complex signal processing. And then I want to end with some signal classification results. So just kind of share some results that we've put together with using the SIG53 dataset and the TorchSig toolkit. So jumping into narrowband RFML, in particular the dataset, I just want to start off by kind of setting the stage for why we're introducing a new data set. And to do that, we kind of need to start with the existing data sets that are out there. So anyone who's done any RFML research already is probably familiar with the RadioML data sets. So these were first introduced in 2016 and then later revised in 2018. And they can kind of be seen as the seminal RFML data sets. These works, along with some papers back in 2016, were kind of seen as the catalyst for the entire application of deep neural networks to the RF world. So since we're now towards the end of 2022, one thing that we're finding is that the ML model research seems to be outpacing the dataset capacity of these initial RadioML datasets. So something that's not shown here, but we have in the paper that we submitted along with these slides that I invite you to take a look at is some empirical results that are showing this limitation with the dataset capacity. So we took some of these modern neural network architectures, for example, EfficientNet, which is a common architecture in the computer vision world that has some built-in scaling. So there's a B0 meta architecture, and it scales up to B7, and there's even been more work to increase the scale even further, where the scale in the CV world, as you scale up the model complexity, generally improves model performance as well at the cost of additional computations. So one thing we wanted to see was, do these scaling properties still exist with these RadioML datasets? And what we found was, even at the very minimal scale, the EfficientNet B0, the smallest of this modern neural architecture, we were immediately overfitting on these initial datasets. And even once we applied a pretty heavy set of data augmentations, we would still see some overfitting, and we would see that even with this performance scaling across the B0 to B4 architectures, the performance did not change at all. So kind of lending itself to some empirical findings showing that we're kind of at the dataset capacity for these previously introduced datasets. So this leads us into the SIG53 dataset that we'd like to introduce. The SIG53 dataset that we're showing is a new dataset primarily for RF machine learning tasks that has over 5 million data samples or data examples that we pre-split into 4 subcategories or 4 sub-data sets in the clean training, clean validation, impaired training, and impaired validation. So part of this pre-splitting can really help with standardizing both collaborative and competitive performance comparisons from different architectures from different companies, different research institutions, et cetera. As you might have guessed from the title, SIG53, we are introducing 53 signal classes within this data set. Within these 53 classes, they all come from the same 6 modulation families. So one thing that I'm showing on the slides here is just one example or one signal class from each of these families, where we have an ASK family, a PAM family, a PSK, QAM, FSK, and OFDM. So then across all of these different modulation families and signal classes, we also have increased impairment diversity, moving from the RadioML datasets to the SIG53 datasets. So we, at generation time, apply a randomized set of a slew of different impairments that are realistic to conditions you might find in an RF environment. These might be on the system impairment side or the wireless channel side. And then finally, the thing that I think is arguably the most important and will be done very soon is that this data set is going to be completely open source. So by this, what we're doing is sharing the generation code for how you can generate this code locally. This makes this data set easily reproducible and customizable. So if you have any specific tasks that you might not be as interested in comparing back to our performance on the impaired validation set, but maybe you have some domain-tailored application that you want to use this data set for, you can customize it since we're planning to open source this code. And then finally, it's also reviewable. So another critical piece of this data set that the open sourcing buys us is that the community can review it, can make changes to it, and just verify that everything lines up with their specific applications. So the way that we're doing the open sourcing of this data set is through TorchSig. So TorchSig is our soon-to-be open source signal processing machine learning toolkit. And really what we're trying to do with TorchSig is kind of fill in a blank that we've seen when investigating just the whole RF or the whole machine learning landscape. So anyone who's familiar with like the vision world might be more familiar with the Torch Vision toolkit, or in the audio world, there's the Torch Audio toolkit. And something that we were finding was that there isn't really a full-fledged toolkit for applying these different ML techniques to the complex waveforms or the RF space. So we're introducing TorchSig as a Python-based toolkit that mirrors a lot of the best practices from these other PyTorch libraries. This toolkit, like I said, is capable of generating the SIG53 dataset. We also include some dataset wrappers such that if you're doing existing work on the RadioML datasets, you can continue doing this work, but still get access to a lot of the features and data handling pipelines that we're introducing as part of TorchSig. And additionally, you can build your own custom RF datasets just by following our dataset class templates. So whether this is a synthetic data set that you're modeling your particular signals, or if you wanted to wrap existing data sets that are file-based, whether that be SIGMF-based file data sets or any other file format. One of the biggest benefits of TorchSig is the fact that we're introducing over 50 domain-tailored data augmentations. So within machine learning, the CV world, the audio world, NLP world, they've all kind of seen that data augmentations are pretty critical for a machine learning training pipeline. So what we did with TorchSig is we've built out over 50 domain-tailored data augmentations. So I've pictured a few here where we just have like a spectral inversion data augmentation where you can see the frequency is flipped. We have an IQ imbalance transform. It's probably a little difficult to see on the slides, but we have like the original constellation diagram, and then it's been amplitude, phase, and DC offset augmentations applied. And then on the bottom, we have a randomized resampler, so that can go up or down from the original data. And with all of these changes, we're dynamically updating the label information with any of these updates as well. So while I said that this talk is focused on the narrowband RFML side, if you were doing a localization in time and frequency task, the labels with the spectral inversion would be followed, for example. So just a few examples of some augmentations that I've shared here. But on top of that, we also have a slew of expert feature transforms. So everything from the data augmentation side works on complex INQ data. However, a lot of machine learning architectures expect real valued inputs. So we have these transforms that can map the complex components to channels, or you can do a DFT transform or a spectrogram transform, such that you can still get access to all of the transforms that and augmentations that act on the IQ world, but then feed your model data that's been already transformed to the format that your model expects. So the next step naturally is to verify that the SIG53 data set is a sufficiently challenging problem that overcame some of the limitations that we saw earlier on with the existing data sets. So to do this, we started off by taking that same efficient net architecture that I named before and training up 3 different scales, B0, B2, and B4, on the SIG53 data set. And with this, we have the blue circle dots in the top left, where we can now clearly see that with the increased complexity in terms of flops and parameters, we are getting increased performance as well on the SIG53 data set. So this is giving us a good feeling that this data set is sufficiently challenging and complex for these modern neural architectures. Additionally, something that has kind of shown a lot of progress in the machine learning field since a paper that came out in 2017 is the application of transformer architectures. So we wanted to not only try out an efficient net, which is a convolutional-based architecture, but we wanted to try out a transformer architecture as well to see do these performance gains still happen on the RFs and complex signal space. So in particular, we picked the cross-covariant image transformer, so that's EXIT here. And pretty much we just chose this one because it has linear complexity with respect to the input sequence size. So we get a little bit faster performance with this transformer as opposed to the vanilla transformer that was originally introduced in 2017. So EXIT also has some built-in scaling properties. So we just picked the smallest 2 scales, EXIT Nano and EXIT Tiny 12, and tested this again on the SIG53 data set. And once again, we saw performance scaling with the model scaling. And interestingly, these EXIT models did outperform the efficient net models on the SIG53 data set. So the same performance gain that's happened in the computer vision and the NLP world seems to be holding true, at least on the SIG53 data set. Additionally, we were getting accuracies in the 60 to 70% range. So it seems like this was a good knee in the curve for presenting a data set that's sufficiently challenging but has room for improvement as well. Following these experiments with the SIG53 data set, just to the plain vanilla static SIG53 data set, we wanted to really evaluate how the TorchSig augmentations could further improve our performance. So on the bottom left, we have some results for taking the performance on the static data set, but then now applying these data augmentations during training time. So each time these samples are requested from the SIG53 data set, we're applying new out-of-distribution data augmentations that were intentionally from a different set of those used in the impairment selection that we used in the generation of the SIG53 data set. And as you might expect with these additional augmentations, our performance is increasing effectively for free because we're just applying these existing augmentations at training time and then seeing this increased performance by roughly 1 to 1.5% across both the efficient and the exit architectures. As one final step, since the TorchSig toolkit is capable of generating the SIG53 data set, we did what we're calling here an online experiment. So this online experiment is, rather than pulling from the static previously generated SIG53 data set, since TorchSig gives us all this generation already, we can just continue evaluating against the static impaired validation set. But at training time, we can, on the fly, create new samples. So what this is effectively giving us is an infinitely sized data set that's only limited by the amount of training time that you have to put towards training these networks. And once again, as you might expect, we did see increased performance, particularly with the efficient net architecture. So this is an intuitive result that's just nice to see carried through with these experiments. And then one final figure here on the bottom right is a plot of the validation loss versus the training loss. This is for the, in the blue circles, the efficient net B4 architecture with just the static SIG53 data sets. The red diamonds are with the augmentations, and then the green squares are with the online data set. And what you can kind of see with the blue circles is at one point we get like a little bit of a plateauing happening in the bottom right, where the validation loss seems to kind of stop learning, but the training loss continues. So this is just like your classic case of the B4 architecture starting to overfit. But once we introduce these augmentations or the online data set, you can kind of see how those lines snap back down to a linear relationship so that we can kind of show the power of how the TorchSig augmentations and the online data set kind of can overcome data limitations that your model might be hitting with these overfitting issues. So we additionally did some performance analysis across a few different metrics, where on this slide I just am walking through a few of them. The top left figure is showing the SNR versus accuracy curves for the 5 different architectures that we experimented with. And from the bottom to the top, we have pretty much the smaller efficient net architectures scaling up in size, and then the exit architectures again scaling up in size. And what's interesting here is that a lot of the performance gain that we can see in this plot happens at the high SNRs. So what this is saying is that the SIG53 dataset is a sufficiently challenging dataset even at the high SNRs. So there's still enough complexity in disambiguating these different signal classes, even when there is a very high SNR, a very clean signal. At the top right, I am plotting some accuracies across modulation families. So what you might expect to play out here seems like it is for the most part, where FSK is appearing to be the easiest signal for the networks to classify, while the QAM signals are definitely the hardest. So you can kind of think intuitively how the higher order QAM signals are much more difficult to disambiguate, particularly for the lower SNR signals. So once again, just an intuitive result that is nice to see play out with the actual results we're finding. And then finally on the bottom, I have the modulation family confusion matrices, where we take all the 53 signal classes, collapse them down into just the 6 modulation families. So once again, a pretty intuitive result where these findings are rock solid across disambiguating the modulation families, which means that most of the errors that are coming in with these models are distinguishing the different orders of intra-family signal classes. And then here I just have two pictures for the full signal classes. This is across all 53 classes within the SIG53 dataset for efficient FB4 and the exit Tiny12 architectures. So you can kind of see there is that rough diagonal going down the full class list, as you like to see. It's probably a little difficult to see in the slide setting, but I invite you to check out the paper that we've submitted as well that you can find on the GRCon website. But there are some patterns to the errors that are being presented with these confusion matrices, which kind of verifies the previous claim where most of the errors are happening at the intra-family scale, just having difficulty disambiguating the same families but different orders. Around the midpoint, you can kind of see where the line gets a little bit darker. That's where the FSK families come into play. And you can see how that line stays dark going diagonally down, but then the errors at the higher order FSKs start coming in. And then for OFDM, the subclasses within OFDM are related to the number of subcarriers. So again, you can kind of see how most of the errors here are within different subcarrier counts within the OFDM family. So that about wraps up the talk. I just wanted to kind of end with a challenge to the community. So once this toolkit and the SIG53 dataset go live, I'd like to invite anyone who's interested to try to see if you can beat our performance on the SIG53 dataset. By open sourcing this code, we're really hoping to get some community engagement and see if we can together as a community bring up the whole field of RF machine learning. And then part of that is also sharing your results back with the community. So we're trying to be very open with eventually sharing the TorchSig and the SIG53 dataset and toolkit. So if you could see how you can perform with our datasets if you're interested in RF machine learning tasks, and then kind of feed that back into the community, that would be really great. We currently have a workshop scheduled for Wednesday for TorchSig. We're hoping to get the code released in time for that, but definitely monitor torchsig.com for any updates if that's going to be able to get that out in time, and we'll make an announcement here as well. It wouldn't be a GRCon talk if I didn't put a plug saying that we're hiring both Peraton Labs and LTS. So if you're interested in RF machine learning or contributing to open source or both, feel free to reach out to me or any of my colleagues. And then just one final comment is that this work was funded by the Lab for Telecommunication Sciences. So with that, that about wraps up, and I think I have some time for some questions.
Yep, you definitely have time for questions. The internet is very happy to hear about the open sourcing of it, and they are waiting anxiously. Do we have any questions from the room? I see a question from the room. Excellent.
Yeah, thank you for a great presentation. So is TorchSig like Torch Vision and Torch Audio in that it's built on top of PyTorch, but it has like, special data classes that's, domain specific, but for signal processing, and then also domain specific models for signal processing, just like how in Vision you would have, classes to load the data for certain types of image classification data sets, and then they will have like Deep Lab and other kinds of like image specific models. So is that what TorchSig is? Or like, yeah, is that a correct understanding?
Yeah, it's we do definitely try to mirror the best practices from the Torch Vision and Torch Audio toolkits. We even are trying to build, or we even have the model API based off of how those Torch Vision in particular, those model APIs work. So the results that I have shown here, we do have built into TorchSig, where you could just do like the model API call to pull down the model architectures. And then you could even change the number of classes, just like Torch Vision for a signal class, or for a vision classification or a signal classification task. We try to limit the amount of times that we're inheriting directly from PyTorch classes. There are still some cases where we do inherit from them, so that is currently a dependency, I believe, of the TorchSig toolkit. But the dataset classes themselves, we have our own, pretty much it's like a signal data object that kind of carries around the data for all these different tasks and transforms and everything. So that's how we kind of standardize the data processing pipeline, so that as a new transform is built, we can make sure that not only the data, but the label information is updated as well with these transforms. Does that answer your question? Okay, cool.
Do we have other questions from the room? Okay, I think you have completely whacked us with a glue stick. Thank you so much. Let's give a round of applause. Our next talk is at 1:30 from John Saleh, who's going to be telling us about improved messaging using modern polymorphic types. That's in 5 minutes, so you have time to go grab another cup of coffee. All right, we are now on time for our next talk. John Saleh is going to tell us about improved messaging using modern PMTs. And if chat at my lunch table was anything to go by, this should be really interesting. I know there's lots of people excited about improvements in PMTs. Thank you, John.
All right. Hi, as was said, my name is John Saleh, and we're going to be talking about PMTs. Just note, I work at a little place called B Cubed. It's a cool place with a dark blue slide, and we make cool stuff, both hardware and software, and we've got good benefits. So if you're interested, come talk to me, or if you're interested in being convinced to be interested, come talk to me. So many of you are familiar with PMTs already, but we'll give a brief overview. I find that it's a part of GNU Radio that a lot of people avoid learning about. Talk about why we're going to do something new, what that new thing is, where we're at, and where we're going. So PMT is a super fancy kind of sort of acronym for a polymorphic type. I don't feel like that's the most meaningful term. I like to think of it as a Python dictionary in C++. And frequently we have data that may be a center frequency that's expressed in floating point, and then we'll have a burst index number or something like that that's an integer, and maybe we'll have a string description. We want to jam all these together, just like you can very easily do in Python, but not easily do in C++. And that's where the genesis of PMTs came from. There's also serialization, deserialization functions, because we may want to run a flow graph or a set of flow graphs on multiple nodes and be able to transfer the data easily between them. And so the goal of PMTs is to make that really easy. In GNU Radio, there's two primary uses for PMTs right now. One is for asynchronous messages. Those are transferred using PMTs. And then the data tags, you have your main data stream, and there's a parallel tag stream, and the data in that tag stream is also comprised of PMTs. So PMTs can be hard to use. There's weird, sometimes inconsistent function names. Good example is that you convert from long to a PMT, but if you'd like to check if something is a long PMT, you ask, is it an integer? There's also fun functions like a car or CDR or CAAR, and it can just sometimes not be the most friendly of interfaces. Where I got involved in this is I had a PMT dictionary, and I just wanted to make sure that the values that someone was passing me were correct. And I got really frustrated because message validation is really hard right now in the current interface. There are certain aspects, especially if you have a lot of data that you're working with, where the performance can be really slow. And when I deal with PMTs, I get seg faults all the time. And at least for me, it's difficult to be memory safe there. So I wanted to make something that was easier for me, and hopefully is easier for you. And so a big emphasis of the new PMTs is to use modern C++ and to have things just work without a lot of effort on your part. And so here's some example code using a PMT map. And so just kind of walking through here, I declare some variables, and then I declare some variables and then use a C++ initializer list, which looks almost like instantiating a Python dictionary. Not quite as nice, but pretty close to the same syntax. You can also access it just like you could a dictionary in C++ or Python. So you can ask for a key, get the value out. At the bottom, I am printing the dictionary out. And so types are converting in a friendly way. You don't actually have to know that in the for loop at the bottom here that value is a PMT. The operator is defined for, yes, the streaming operator is defined for value in a way that it will be able to print out for you. And so to me, at least, this is a nice, friendly way to deal with maps. We also have vectors, another common data type. And so you can declare a vector with an initializer list. You can use all of the STD vector constructors are valid here. So the second one is constructing a vector of size 4 where all of the values are initialized to 1.0. The hope being both with the map and the vector that if you know how to use a standard template library mapper vector, then you know how to use the PMT mapper vector. You can do range-based for loops. You can do equality operators, which took some effort, but I felt was worthwhile. It's really nice to not have to know what kind of PMT you have to be able to ask if it is something else. There's also PMT scalars and PMT strings. Those are more straightforward. I didn't produce examples here, but they're fairly simple. The new PMTs encapsulate most of the functionality of the previous ones. Last year, I presented kind of the idea of this, and Josh Mormon was helping me out, and a few weeks before GRCon, he was doing some benchmarking and sent me the most disappointing chart I've ever seen, which is this top chart. A very important operation is that we want to serialize a vector or a packet data unit, PDU, and send that from one flow graph to another, be it on the same host or on a different host. And for small vectors, the new PMTs were a little bit faster, but for large vectors, they were actually slower. And having a nice, modern C++ interface is great, but if I had to pick between a good interface and fast performance, I would generally pick the fast performance. So I discovered what the issue was, and sadly, it involved a major rewrite of the library. There were some design considerations or design flaws in there. But after the major rewrite, we can now see that the serialization time is, for the old PMT and the new PMT, is linear in both cases with the size of the vector, but the scale is much smaller in the new case. So it's faster in every case, which makes me happy. Thanks to whoever clapped there. And then Josh Mormon has been doing a great job on the GNU Radio 4.0. I'm going to call it a rewrite. And this is fully integrated in there. Now this is, the plan is that this is going to be the new PMTs in GNU Radio 4.0. And if you were to check out 4.0 today, you would be using these PMTs. So some places that I'd like to go from here. If you remember, this all started because I really wanted to check and make sure that the dictionary that someone handed me had the fields and types that I wanted. And I sadly have not fixed that problem yet. What I would love to do is integrate something similar to JSON schemas, where you're able to declare, this is what my message should look like, and it will validate all of those types for you. And there's a C++ library that lets you define your own JSON schema-like structures that I'm looking at for using for that. There's also a lot more benchmarking to be done. We would not have known of the major design flaws had Josh not done some benchmarking for me. And so there's a plan to go through and benchmark all the major functions and compare them to the previous PMTs because we want to make sure that this is better, not just from an interface perspective, but from a performance perspective in any way possible we can. I have started doing this and already found a few areas for potential improvement. And so the plan is to just keep going from there. Along with that, I don't have the exact numbers for code coverage. It is pretty high right now, but given that this is something that will be used all over the place in GNU Radio, and I'm hoping it will be more user-friendly to use in GNU Radio, I'd like to have 100% coverage in there. And then I like Linux. Linux is good, but sometimes people disagree with me on that. And there are already a few cases where people have tried to build the library, say using Clang, and it didn't work. And so we need to go through and make sure that we build this on different operating systems, architectures, different compilers, and make sure that this is going to work for all the use cases that we're using. One note that I did not include in here is that this requires features from C++ 17, and so you will need a reasonably modern compiler to use this. But if I'm not mistaken, GNU Radio is already at C++ 17, correct? Yeah. And so if you're running GNU Radio, the latest, then you should be good there. And then just make sure that, that this is supporting GNU Radio 4.0, and that any features that are needed to help there will be supported. So that's where we're going. So thank you all for the time. If anyone is interested, the repo is available on GitHub. It is part of the main GNU Radio project. And there have been a few people who I don't know who have made pull requests, which is great, including one person who has no association with GNU Radio. And you can contact me as well. I've also got some coworkers here from B-Cubed, which is a great place. So feel free to reach out. Thanks.
Thanks. That was really informative. I see no questions from the internet yet, but do we have any questions in the room? Stand up, wave, interpretive dance. Okay. I think we are all informed. Thank you again.
Thanks.
And now we wait while I expand the font on my phone to figure out what we're doing next. The Kuiper Linux distribution.
Hello, everybody. My name is Michael Hennerich. I'm software engineering manager at Analog Devices in Munich. And I'd like to welcome you to the presentation Linux, Kuiper Linux, Simplify Hardware Prototyping with GNU Radio. So software-defined or radio systems in general are much more than just the digitizer. There are lots of active mixed signal front-end components that require configuration, runtime, and control. Oops. Oh, okay. So this includes programmable gain amplifiers, attenuators, synthesizers, PLL up-down converters, RS switches for filter banks, tunable filters, beamformers, PA control, offset bias, or even like some system monitoring stuff. Sorry, but the slides do not advance. I can't control my slides anymore as soon as I plug this. maybe I get my wrong. Can oh, with the mouse it works. Okay, sorry. So some typical challenges. On the left, you see some pictures how a typical lab bench may look like. You see lots of interconnected evaluation prototype boards, lots of different power supplies, and typically no homogeneous way to control this mess. This has some implications, sometimes loss of RF performance, but more difficult is that this is very difficult to test in the field or bring to a customer. Also, it's a kind of a control nightmare because you often have like different vendors, evaluation, hardware, software systems, and sometimes there's no software at all, and there's no easy way to remote control this, and you cannot integrate that in a GNU Radio flow graph. So there are a number of possible solutions. One is to kind of do a custom PCB design with a system controller, some custom firmware, but that's typically high cost and high risk, and it typically comes second after the prototyping phase. So in this presentation, we want to use commercially off-the-shelf control hardware and open source software, in this case, Linux. So in the abstract, we said we would build an FMCW radar system. That's what we're doing now. FMCW stands for frequency modulated continuous wave. It's kind of different than from pulsed radar. In the figure below, you see a kind of a ramping waveform that ramps in frequency over time. And in red, it's the transmit waveform, and in green, the receive waveform. And there's a time delay, and that time delay manifests in a offset, frequency offset, that's called the beat frequency. So to the right, there's the radar equation, and you basically see that the distance to target is proportional to that beat frequency. Also, you see that the kind of the ramp rate as well as the bandwidth of the modulated signal is significant in the equation and defines the characteristic of this radio system or radar system. So thanks to John Graft, he kind of helped me prototyping this and also was so kind to actually build that up and to take a video. We were gonna see that in a minute, but here it's kind of the top level overview. We have a digitizer. In this case, it's an Adron Pluto. It can be anything. It can be any USRP or any other SDR, because we have pretty low bandwidth on that side. Then we have the RF front end that's kind of composed by a number of blocks. Most important is the frequency ramping synthesizer in here, the ADF 4159 with an external VCO, some attenuators, splitters, mixers, filters, and also a power amplifier. That all is controlled by a single Raspberry Pi in kind of as a control bridge, and that Raspberry Pi connects to your PC running GNU Radio Companion over a network interface. So this is how the prototype looks like. In this case, we're using like an X microwave plate with an X microwave controller, and that controller has kind of two interfaces. One is a Raspberry Pi head with control signals for SPI, I2C, GPIOs, and the other one is a FMC connector, so you can also connect that to a FPGA carrier. That is our very simple Hello World FMCW flow graph. Again, I've split it into two portions. One is the digitizer with some source and sinks. And on the right side, we see the RF front-end control portion that we want to discuss a little bit more in this presentation. But now I think it's time for the demo. And I hope it's playing.
Right, so this is our setup with that radar that we just built. You can see the X microwave plate there connected to Pluto and connected to two X-band antennas. It's actually an array of antennas, but we've only connected two of them, one for transmit and one for receive. And then on the left-hand side, you can see our corner reflector. We can actually make that move, and we'll do that a little bit later. Here's the GNU Radio flow graph. Let's go ahead and start that. And the FFT comes up, you can see that. So right now we're outputting one continuous frequency, but we can change that to what's called continuous triangle. So here we're ramping the frequency up and then ramping it back down again. And you can see what that looks like on the waterfall plot here. So this is all for a stationary target, but that's not very exciting. So we can make our target move on the target trolley. And you'll notice that as the target gets closer to the antenna, that the beat frequency gets closer to its 100 kilohertz carrier frequency. And as the target moves further away from the antenna, we get further away from that 100 kilohertz frequency. That beat frequency is directly correlated to the distance to target. And here's now the sawtooth. The sawtooth, since it doesn't have the ramp down, you only see the positive deviation in beat frequency there. We'll switch back to continuous triangle mode. But now we'll start increasing the ramp time of that frequency ramp. And you can see the impact that that has on beat frequency. As we make that ramp longer, the beat frequency for the same bandwidth goes down.
Okay, so basically, so we control the external components directly from the flow graph, and this way you can actually play with all the characteristics of the system while you're evaluating it. So there are multiple ways to accomplish that. So that is what we just seen. We had like a Raspberry Pi just as a control bridge. Wired it back to the computer that runs the GNU Radio, and we have the digitizer also connected to the same PC. As an alternative, if you have a Raspberry Pi, you can also run GNU Radio on the Raspberry Pi, and I call this the ARM-based compute platform, where you just connect the HDMI monitor and USB to that Raspberry Pi. A third, and probably the most interesting alternative, is what I call the all-digital back to the same SoC FPGA. So that basically means your transceiver data, your transceiver control, all the clock control, all the microwave RF front-end control runs back to the same entity. So this enables a single cohesive environment to interface with digitizers, RF and microwave. It has lots of benefits. For example, easier synchronization between your digitizer and your microwave, or a better synchronization of data and control. And we can control all this together from GNU Radio, MATLAB, or Python. On kind of this slide, we kind of show that. On the back end, all the components remain actually the same. And on the front end, where we have our compute, we can either use GNU Radio, Python, or FlowGraph exactly in the same manner. And there are different ways to actually integrate that. There's GRIO in GNU Radio. There's the MATLAB system object in Python, in MATLAB Simulink, and or libio in general for Python. So the presentation is named Kuiper Linux. So what's so special about Kuiper Linux? It's actually just a distribution based on Raspberry, but not only for Raspberry Pi. So it incorporates Linux device drivers for a lot of ADI products, and is kind of created with easy use in mind. So it supports multiple circuit node evaluation board, FMC boards, Raspberry Pi heads, Arduinos, or PMOD connections. And it's kind of out there to minimize the barriers to integrate hardware devices into a Linux system. So you don't need to compile the kernel, it's all there. You don't need to install GNU Radio Companion on it. It's all there. There's all Python, libio. It's kind of out of the box. And we also use this for customer evaluation, where they want to have a good out-of-box experience, plug and play, and it all works. So Kuiper solves this by including a lot of host of additional applications, software, and libraries, and utilities. So how do you get that? So there's going to be a imager utility for Windows, Linux, Mac that kind of downloads the latest image from the internet while it actually writes it to a SD card. There's some extra menus to customize the boot partition for a certain carrier, FPGA, FMC add-on card. And this utility is going to be released in the coming weeks. But as an alternative, you can just VW get the image, unzip it, and just dump it on a SD card. And later on, you just move some files around. So I mentioned customizing. While Raspbian just targets Raspberry Pi, this distribution includes lots of bit streams, kernels, device trees for a lot of different popular FPGA carriers from Xilinx, AMD, or Intel, for MPSoC, SoC FPGA, Area 10, Area 5, and so forth. So what is customizing? It's basically configuring the SD card to be used with a specific hardware, and hardware can mean base platform plus attach, and it's basically moving files around so that the first stage bootloader can pick them up. For Raspberry Pi, there's a special thing that's just special to the Raspberry Pi first stage bootloader. There's a file, it's called config.txt, and you can edit that file and kind of instruct the system to load a certain device tree overlay. So what is a device tree and what is an overlay? And at the end of the day, kind of writing device trees is more or less the only thing that you have to do with this distribution if you want to enable certain devices to be present in your system. A device tree is a tree data structure with node that describes physical devices in the system. It's typically used to describe device information that cannot be auto-probed. For example, a USB bus can be auto-probed, PCI bus can be auto-probed, a memory mapped XE bus cannot be auto-probed. It's organized in nodes and in properties. And overlays are kind of a special device tree that allows you to add nodes to a device tree, a running device tree on an active system. So there are various formats of those device trees. So there's one, the textual format that is human readable, and it's kind of the file that you edit, and you convert that file into a binary file, which is then machine readable using a device tree compiler. And you can use that compiler in both directions. You can also disassemble device tree binary into a source file again. So let's look a little bit how a device tree looks like. On the right side, we see an example. So there are first two directives. Those are for the compiler, and then we have nodes. And we basically want to add a node for our ramping digitizer. So, but we need to create that node somewhere. And you basically create that node under the bus where this device is attached to. In this case, it's a SPI device, so we attach it under a SPI bus node. And in this case, we attach it to SPI bus 0, so we just reference that node, and then we add a node. And in that node, there are a number of kind of required properties. One of them is kind of the compatible property. It's kind of a string, and that string is being matched when the device tree is loaded against a list of available device drivers in your system, and in case those both match, then the kernel instantiates that device using that particular driver. And we are having here a kind of a SPI device, so another important property is the rec property. And in this case, it instructs the SPI subsystem to use chip select 0. So there can be other properties in here, like SPI max frequency, SPI modes, polarity, CPHA bits, and so forth. So in our analog devices Linux kernel tree, which is nothing special, but we have a bunch of extra files in there that are not upstream. It's kind of device tree overlays, for example. We kind of create them just for internal testing and also for customers who just want to test something without actually writing something. And those are located in ARC, ARM, boot, DTS overlay. And once on the SD card image, they are on the first boot partition, which is typically a FAT partition, and you can find those compiled device tree overlays in boot overlays, or from within the root file system of your running Raspberry Pi, those are mounted to boot overlays. There are basically, for Raspberry Pi, there are two kind of methods how you can actually instantiate a certain device tree overlay. One option is to do it at boot time by editing the config.txt file on the boot partition. So you just add a line dt overlay equals kind of the overlay name, excluding the file suffix. Or you can also do it from the command line by typing dt overlay and then the overlay name. You can also remove those overlays if you want. So at this point, we have a kind of a running Linux kernel system that we just added new drivers to it. And now how do we want to use it? Most of the drivers that we do, which are kind of interesting for these RF systems, are so-called I/O drivers. And I/O is a kernel subsystem that is not really just for industrial input-output. It basically covers all non-human interface devices. And that includes ADCs, DACs, transceivers, synthesizers, amplifiers, gyroscope. There's actually a pretty long list. So what are I/O devices? So they are kind of represented as files or directories in a virtual file system called SysFS on your running Linux system under SysBus I/O. And each of these devices do have a structure. A device can have attributes, can have many attributes. A device can have channels. Channels can have attributes. Channels can have events, and also events can have attributes. Devices can also have one or multiple buffers, and buffers can also have attributes. So what are attributes? Attributes describe hardware capabilities, for example, sampling frequency or controlling a certain power mode, power down, for example. You can, on a PLL, you can use PLL locked to check whether the PLL has locked. I/O channels. So channels are a representation of a data channel. Channels always have a direction, can be input or output. Channels do have types, whether it's a voltage, whether it's a temperature, an alternating voltage, whether it's humidity. Basically, there's a long list of different types. Then channel can have index and can also have like modifiers, for example, I and Q. And also channels can have attributes. And in this case, we see frequency as the attribute, but there can also be like phase, hardware gain, scale, offset, draw. And the nice thing about I/O is that those things are kind of standardized, and you can construct physical SI units from it. For example, if you want to know the real voltage on a channel, you basically take the raw attribute, add the offset to it, and multiply it by the scale. And then the convention is that the result is in millivolts. Here's an example how to control a gain amplifier or an attenuator. The difference here is just that the hardware gain is negative. Here in this example, we just write 6 dB into voltage hardware gain, and after we read it, we kind of returns 5.675 because that was the closest possible value that this amplifier could do. Here we have the fast ramping waveform generator that is being used in this FMCW radar system. Again, this device has just one channel, alt voltage 0. That means it's an alternating voltage. And then we have frequency, deviation range, deviation step, deviation time, power down, ramp mode available. And on the right top side, you kind of see where that maps to your to your waveform. Start frequency, deviation range, which is kind of the bandwidth of that signal, and the deviation time. And these kind of attributes or properties directly map into your radar equation. You can also select different modes for the ramping, sawtooth, or sawtooth burst, continuous triangle, and so forth. And you do that by just writing strings into that attribute. So how do we control this from our GNU Radio flow graph? As part of GR-IO, there are the IO attribute sync blocks, and these are generic writers for any attributes for IO devices. This includes channel, device buffer, device debug, or even like direct register writes. All the messages must be PMT dictionary, where the key is the attribute and the value is the value that is going to be written. So this block has a number of properties. One is the URI. It can be an IP address. It can be a USB URI. It can be serial. It can be many things. Then we list the device name of that IO device, what kind of attribute type it is. In this case, it's a channel, and it's an output channel, and the channel name is alt voltage 0. Since GNU Radio 3.10, there's a very nice new block. It's called blocks var to message, and this block will monitor a variable, and when it changes, it generates a message. So before that block, there was also like an IO attribute updater, but that IO attribute updater would just like read a variable, and with a certain rate, it would just hammer it into the device. And sometimes this can have some side effects, for example, some glitches in RF, and you just want to do that if you really change a variable in your system. But kind of the downside with this is that this block has a callback that emits a PMT message pair. And that is not compatible with the IO attribute sync. That's why we kind of, in this example, added kind of a custom Python block of type GR basic block. And this block will convert the PMT message pair into a PMT dictionary. You can see kind of the basic Python code on the right side. This is how the control portion looks like for all the different properties of our frequency ramping generator. We created some Qt GUI widgets, a Qt chooser for the different ramp modes, a toggle button for the power down, and some Qt range widgets for the frequency, ramp rate, and so forth. And for each of those, we have this variable to message block, which connects to our translation block, and then to the IO attribute sync. So some of the conclusions I had was that you don't need to be a Linux expert to use and enable ready-made Linux device drivers. It can actually be quite easy. It's most of the time just like editing a device tree, or when you use Cooper, you don't need to rebuild your kernel because all the drivers are enabled. GR-IO can be used for much more than just controlling a transceiver or digitizer. You can also do some front-end controls with it. And maybe GR-IO attribute blocks need to be updated to also accept PMT message pairs, or maybe the new PMT messaging that we just heard about will maybe solve this problem also. I don't know. If you're more interested in GR-IO and the next generation of libIO, there is going to be a talk, I think it's on Thursday, from Paul. He will talk about libIO design and how it will affect GNU Radio. He will talk about multi-buffer support, async protocol, DMA-buff compatible interface, and a new timestamp API that is also currently discussed. Also, maybe even with the latest version of libIO 0.24,
It also supports now hardware monitoring devices. So if you are interested in kind of integrating your CPU temperature or your fan speed into your flow graph to do something differently, you can do that with that. So thanks, everyone. I put in some references, and that's it.
Thanks. I don't see any questions from the internet yet, but I'm somewhat curious. Are there going to be versions of this for x86 and AMD 64 hosts, or is this designed to make embedded use a little simpler, and those of us with bigger computers shouldn't?
So you with libIO, you can run libIO today on your x86. So lots of notebooks to actually use IO for the gyros or for any for various other things. And libIO has kind of this remote backend mechanism. So you use libIO on your x86 system, but it can magically connect to a remote backend that runs on an embedded target. And that's being used heavily in all these examples. So you can connect to your FPGA platform, to your Raspberry Pi, and have the IO devices on your x86 system, just like they would be local to your embedded system.
Thanks. Moving to other questions from the room. No more questions from the internet? Okay, thank you again. And in a few minutes, we have a talk from Elbit Systems. Okay, looks like our next speaker, Alex Kozlov from Elbit Systems, is ready to talk, and this looks like it's going to be really interesting.
Thank you. My name is Alex Kozlov. I'm a DSP engineer at Elbit Systems, and I'm here today to talk about Elbit Systems and what we did with GNU Radio. So a little bit about me. I'm a communication systems engineer. I work at Elbit for 11 years now, ever since I've been a student. I work in the C4I and Cyber division, specifically in the radio department, and my fields of expertise are DSP, modems, and machine learning, both in terms of developing algorithms and implementation. So a little bit about Elbit. We were founded in 1966. Our revenue is $5 billion. Third of it is here in the USA. We're publicly traded. We have subsidiaries all over the world. We make total of 18,000 employees. Out of that, 3,600 here in the USA. Headquarters in Israel, in Haifa. I come from Israel. And few words about our portfolio. So we're a high technology company engaged in a wide range of programs throughout the world, primarily in the defense and homeland security arenas. We develop and supply a broad portfolio of airborne, land, and naval systems and products for defense, homeland security, and commercial applications. Our systems and products are installed on new platforms, and we also perform comprehensive platform modernization programs. In addition, we provide a range of training and support services. And additionally, I'd just like to add up that we are set up to support classified projects here in the USA. So a little bit about the division where I come from, the C4I division. Our flagship product is called E-Lynx. It's a family of tactical radios. We have handheld radios, manpack radios, vehicular adapters, really the whole portfolio. We also have high capacity line of sight radio links, network solution, HF beyond line of sight, which is close to my heart because most of my career I was developing HF modems. Soldier dismounted communication systems, airborne SDR, data links, military SATCOM, intercom and vehicular communication systems, and naval communication systems. So that's a bit about Elbit. Now, this presentation is targeting both beginners with GNU Radio and also people that are coming here to see some new modem algorithms that are being developed. And I'm going to talk about a life cycle of an idea. And I'm talking about an idea that is off roadmap idea in a big organization like Elbit Systems. So we have a roadmap of certain products that we're developing. And for example, few engineers are having a concept which they would like to promote inside the organization. And they think that, for example, a concept of a new modem. They think that this modem is gonna be good for our customers, but it's off roadmap, so it has to be done in parallel to our main work. So if we have such a concept, there is like an initial step of initial R&D phase, and after that, there is the proof of concept that we would like to present to our management. And hopefully, if they like it, we can move on with it, and they can sell it on to potential customers. And there's the rest of the chain, but it's less important for this presentation. So, proving your concept, what I was used to before I discovered GNU Radio. So, basically, simulate the idea, then I would implement it, given that the simulations were good. I would like to have some supporting features. For example, if it's a modem, I have to have a front end. I have, there's the filters, there's the upsampling, downsampling, stuff like that. I'm dependent on the current state of hardware and firmware to be ready for what I would like to prove as a proof of concept. I'm depending on schedules of other engineers, and because I'm working off roadmap, and also hopefully the management gives me enough time and priority to work on my side project. Now with GNU Radio, this whole process became much shorter than I was used to. So I had to simulate the idea, it's the same thing, but after implementing the code, I could just take several EVBs of components that are in any way are going to be in our product. And by putting them together and having some already ready-to-use drivers, and these drivers, I have to say special thanks to Analog Devices for providing LibIO and stuff like that. And some ready-to-use supporting features like all the down conversion, up conversion, stuff like that. and plug and play, and I could prove my concept that easy. So a bit about what we did, what concept we wanted to prove. So there are some ways for multiple access in radio systems. There are the orthogonal multiple access methods, which are TDMA, FDMA, CDMA, all of those. And those are really the types that are currently used. And one interesting way to approach multiple access is with non-orthogonal way. So in this multiple access, we would have several transmitters transmitting to a single receiver on the same frequency at the same time, and without any PN spreading sequences. And by this, we would be able to increase our network capacity dramatically. So this is the concept that we wanted to prove. So instead of trying to accomplish this on our currently being developed hardware, I could just take few EVBs. For example, I could take the Xilinx Zinc EVB and the ADI Navasa EVB, and I could connect them with a combiner for 2 TXs, with a combiner that would be on the same frequency and at the same time being inserted into a receive channel, into one of the boards. This is the setup that we used. The GNU radio was on the PC doing all the digital processing. And that way I could prove to my management that this idea could really work because I did it with the actual EVBs of the actual components that are going to be part of our next generation radio. And it was easy because, as many of you know, the integration is so simple because so much of the features are already there. All the blocks that are not highlighted are blocks that are already existent in GNU Radio. I had to implement just several blocks, which are the algorithm-specific blocks for my use case. And so what I had to do was very minimal to prove the concept to my management. And just for people here who are familiar with digital modulations, this is just the execution of what we did. So the interesting graph here is the middle one, where we can see 2 transmitters transmitting at the same time, at the same frequency. And the demodulator of the non-orthogonal multiple access is able to distinguish between the 2 transmitters, and in that way we can double the network capacity. So that's what we did with GNU Radio. And about my personal experience, getting started with GNU Radio was very, very fast because the wiki is great. And one thing I didn't know at the beginning was that there is a great chat where people are always ready to help. And that's also where I got much help to make it happen. The vendors are involved. For example, we had help from Analog Devices because they already had the LibIO developed, so we didn't have to do that from scratch. What we would like to see in the future focus of the GNU Radio community. So currently GNU Radio is more used as a prototyping application, but would like to have it used as something that can be really embedded into products for faster SDR implementation. So more focus on FPGA accelerated blocks. There is a mention of that in the wiki, and there's been work done there, but we feel that An additional focus would be really much beneficial for us, and I think for many of the people sitting here. If the GNU Radio could be turned into a platform that's more hard real-time, more controllable and versatile, something that's more fitting to be implemented, to be embedded into a product, into an embedded product. Also, we feel that out-of-tree models, it's a bit complicated to integrate them, and if there was a kind of a mechanism for simplification of this, it will be very beneficial, I think, not just for me, but for many that are sitting here. And also like a contribution store, maybe if you could like download from a repository different out-of-tree blocks that others are doing, that could be, I think, very beneficial to many users. And this is the demo. This is the set of boards that we used to simulate this idea, and it will be available later on today and tomorrow, as of tomorrow, the expo hall. And you are welcome to come and see it and let us know what you think. Thank you.
Thanks, that was neat. Looking to see if we have any questions in the room. Does not seem to be any questions from the room. I know that there's been some work over the years on packaging out-of-tree modules for GNU Radio. That's probably, like any sort of packaging system, an ongoing project forever, where it's, everybody's always trying to make it easier to load out-of-tree packages for any system. But that does always sound like something that people would find useful. In a little while, we're going to go into lightning talks. Oh, I see a question from the room.
Are you allowed to share how you were able to discriminate between the two users in the communications channel?
You mean speak about the algorithm itself? There is a certain amount of detail that I can get into. For apparent reasons, I can't speak about everything, but I suggest that you come to the booth, to our booth at the expo hall, and I think you'll be very fascinated. Thank you.
Other questions? Okay, lightning talks will be happening shortly. We have two that I know of. One is going to be about PMTs, and I think there was a CTF walkthrough that's going to be happening. And there's still time if anybody has some quick ideas that they want to chat about for 5 minutes.
Yeah, if you want to, yeah.
He was here.
Oh, yeah.
You know what?
No,
Try
that
this
one?
one. Yeah. Let's do this. Let's do that. That'll load up. Okay. Can you mirror your display?
Yeah, probably. Hello. Hello.
Hello.
Echo. Yeah. Hey, so my name's Ben, and on the chat I go by Muad'Dib because I have a messiah complex. And but seriously, yeah, I just wanted to introduce myself because I talked to a lot of you under my pseudonym, and it's good to see so many people here that I really respect and enjoy talking to. So I'm going to go do a quick walkthrough for our CTF. I am going to be using a challenge from the 2020 all virtual CTF. So if you try to use the solutions I'm about to show you, will most likely not give you any points. I don't know that for sure, but I don't think they will. So the CTF, you basically just log in. This year's CTF is just ctf.gnuradio.org, and you can sign up, register, and then log in. And you can start a team. If you're an individual competitor, just make a team. You can be an army of one, go you, or make some friends. I know that's hard for us, but yeah, it's advantageous. So, oh yeah, hey, good to see you too. So basically, I'm going to start out. It's a Jeopardy style challenge, and so I'll just pick one. So this one says right hand rule thumb, and that sounds familiar for some reason. I think somewhere in my education I learned about that. So it says, wow, listen to this, and it's a WAV file. So I'll download the WAV file, and we go to, well, I downloaded it, and basically I can ingest this into any program I want, right? So let's try, I don't know, Universal Radio Hacker. Not GNU Radio, but based on GNU Radio, like most things. So if I look at the spectrogram, I can see there's some stuff going on here, but it's not, I guess I could read it backwards or take a screenshot or something like that. I could also open up in Spectrum. If I want to open up a WAV files are a little weird when they do IQ because they're going to have a header and stuff like that. So you can change the file name to be complex signed. So like a CS16. So I can just rename the file radio.wave to radio.cs16, open that up, and then, hey, look at that. There's some stuff going on in the Spectrum. I could also just play it back in GNU Radio. If I do that, I get a lot more control because GNU Radio is awesome. Seriously, it's awesome. And so I can see what's going on here, but it's going too fast. So I usually like to slow down the sample rate, go slow-mo, and then I can see that my flag is in here. It's backwards, but if I turn my head, I can see it and basically enter it in the form that it's entered. There's also a Doge in there, and it says such NRSC5, which is HD radio. So that gives me a clue as to what these seemingly, these OFDM carriers are. So that's kind of a tip off that like there might be another challenge where we want to use that because there's clearly a flag here, and I can go punch that in on the scoreboard and win the day. So there you go. That's it. But you don't win the day, you just win that challenge. That's like 10 points, and there's a bunch of points on the board. So, yep. So that's 3 minutes and 50 seconds. And I was told I have like 10 minutes. So now I'm going to talk about a tutorial that I wrote in GNU Radio. This has nothing to do with the CTF. I wrote a tutorial that does something that a lot of people get on the chat and ask about, which is how do I detect something and then show that I detected it. So if you go to wiki.gnuradio.org, you can look for tutorials. It's on the left-hand column. And this one is called Band Limited Threshold Detector. No matter how long I've been out of academia, I still tend to put these weird academic type names to things. It's just basically a threshold that you can limit by frequency. And so you can reject things that are to the left or right of a box. So we want to put a box around some signal and detect it and show where in the spectrum we detected it. So basically, running through this very quickly, I give the flow graph. first off, I set up the problem, and then I put the flow graph up here. And what I want to do is generate some synthetic signal. So I show how we can simulate that with vectors and just basically put up some narrowband and a wideband carrier. And also we can modulate them with a square wave at random intervals. So you get this sort of like jumping around random different amplitude signals. Then from there, we make our detector, and we're going to use, this entire thing is done with in-tree blocks, with the exception of the very, very end where I do just a very simple conditional, like if it's above the threshold, print it out and write it to a file. But other than that, this whole thing's done inside of GNU Radio. So I think a lot of us ask this question and say, oh, let me go figure out how to write an out-of-tree module. And I don't do DSP, so I'll probably do this poorly. But if it works at the end of the day, great. But like really, there's already mechanisms in GNU Radio to do a lot of stuff. And I think that's where, for me anyways, it's been beneficial just to learn how to use GNU Radio and all the mechanisms that are there. So yeah, so we make a box around some spectrum, and we can actually draw lines on the plot and have them be adjustable so that the end result looks like this. So you have the threshold I'm adjusting, and then you have a lower frequency and an upper frequency that you can box out these intermittent carriers. So that big wideband carrier, we don't care about that. But these little intermittent ones, like if you're doing some ham radio stuff and it's in an adjacent band to like some cellular carriers, you don't care about that. This would give you the ability to just look at that, but you can still ingest at a high rate so you can get, good resolution. And so here you'll see just what's inside the box is shown down here in the bottom left. And then on the right, it's only the things that exceed the threshold. So as I'm lowering the threshold, you'll see the two little carriers pop up. And then to the right, I did give some code here. This is just a very simple not out of tree. This is just an embedded block. It's a Python snippet to basically print out. I'm tailing the file here. So it just writes to file the bin number and what the amplitude or the magnitude was in dB. So that's it. But yeah, this was really fun to do. Someone showed me how to do this a long time ago. I will not take any credit. This is just something that someone passed along to me a long time ago. And I think a lot of people don't realize that you can actually draw marker lines in the Qt existing GUI. But we're going to get away from Qt anyway because we want to do something way cooler. But anyway, this is something that people don't realize you can do. And the power of vectors in GNU Radio is really, really big. And we've got some awesome tutorials not done by me that were really fantastic. So please look at the tutorials. They're awesome. Okay.
Thanks. That was fun.
Now I'm done.
PMTs. Where's our lightning talk on PMTs? I'm misinformed, but we still have a lightning talk, not on PMTs.
I put a lot of time and effort into these slides. There we go. Yeah. I'm back, not to talk about PMTs, unless you really want to. So I'm going to talk about Conan. And now we have a slide up. Awesome. So there's a problem that we had, and Conan is a solution to that problem. Conan is a package manager, and I know what everyone is thinking. Exactly what GNU Radio needs is one more package manager in the mix. And you're right, that's exactly what GNU Radio needs. Imagine that you are a maintainer for a out-of-tree module or a maintainer for GNU Radio, or you're trying to help with GNU Radio. And you, as a modern forward-thinking person, are using Ubuntu 22.04, and everything is working, it passes all your unit tests, everybody's happy. And then you get a message from a user using, say, CentOS 7, which, not end of life yet. And they say, hey, this doesn't build for me. You get really annoyed and frustrated, as you probably should. And you look and you see, oh, well, the version of CMake on CentOS is something that was released, I don't know, maybe like 8 years ago. All of the dependencies are really old and out of date. And as much as I would love to blame the CentOS RHEL people for that, it's not that those dependencies can't exist there, it's just they're not in the package manager. And so maybe you go and you add in some hacks to your CMake file, or you give the person some detailed instructions for how to build Boost from source, which never has any problems. And you try and work through it. A similar problem, which is what we had, is we wanted to deploy some GNU Radio on a ARM v7 device. And there are some libraries where you need some super secret extra flags when you compile it. And if you go through enough message boards, you'll find someone saying, oh yes, just add this flag to the GCC line and it will work. And it's a lot of time and effort to get all of that going. So Conan attempts to solve this by making it easy to run the exact same code with the exact same dependencies on different architectures and different OSs. It also works for Windows and Mac. It is not a magic panacea. You still have to make it work in all of those cases, but it is a way of trying to manage that madness. So I told you I put a lot of time into these slides. So here's kind of a diagram without arrows because I didn't have time for that, of the gist of how Conan works. So you start with a recipe file, and this is just like Conda, Debian, or CentOS, or whatever package manager you're using. There's some file that says, here is how you build a package. The Conan file is going to tell you how to build a package for all of these cases. And the vast majority of what you have in there is going to be agnostic to how you're building it, but it does allow for you to have specific instructions for if you're on Windows or Mac. You are going to define a set of profiles, and the profiles can define a lot of things. If you're cross-compiling, which compiler you're using, the architecture. So I put up a handful of examples here, but there could be a wide variety of profiles you use. So you may have Linux using GCC 9 on an AMD 64, which is just your standard Intel chip. You may have ARM v7. You could be doing Windows with MinGW. You could be cross-compiling for Android. And so these profiles are just a description of the settings and the tool set that you're using to build that recipe. And then you can build one at a time, or if you're using a CI system, you can build multiple jobs for each one, or sorry, one job per profile. You can build all of these packages. And then it will eventually get stored into Artifactory, which I'll talk about in a minute. But what's nifty about this is all of the packages are built using the same recipe. And so when I say that I depend on this version of Boost, or I'm using this version of CMake, it doesn't matter that CentOS 7 ships with a completely different version. If there's a Conan package for CMake, which there's over 1,000 supported packages in there. So most of the dependencies of GNU Radio are already in there. Then you will use the version that was specified, not what was installed on your system. And so for us, we've got profiles for the different architectures that we're using. We're only using Linux, but we create these different profiles, we build the different packages, and then we know it's going to work and run in the other places. And it has made integration onto different systems, in particular the embedded ARM v7 device, much, much easier and much more manageable. Important note is that Conan is free, open source software. I file bug reports. I've been able to look at the source code and work with some of the people there. It's really nice. Artifactory is free for Conan, but it's a very powerful tool that they want to charge you lots of money for. Unless you're an open source project, then they'll give it to you for free. Artifactory is a place for storing artifacts, which in this case are the GNU Radio packages. One thing that I think could be really cool for GNU Radio would be there's tons of out-of-tree modules, and there's can't remember the name, the GRRAN or PAN. What was that? The CGRAN. There we go. Where you can get links to the different out-of-tree modules that exist. With software like Artifactory, you could allow the other open source developers to put their packages in, and each of those packages would have a recipe. So it would say that this is the version of GR whatever that works against GR10, or sorry, 3.10.4, or any 3.10, 3.10.x. And so you'd be able to see not just what out-of-tree modules exist, but what versions each of those support. And so this is something that we've been working on for not around the clock for the past year, but off and on for the past year. What we found is that the vast majority of GNU Radio is really easy. It's just when you get into really Qt and the GTK stuff that it gets to be much more difficult. I can install everything but those without having to install any system drivers, any system packages. And it's just using Conan packages for everything, which makes it something that's very easy and portable to use across everything else. And there are ways so you can use the system package manager to get drivers that you need. It's just when you get into when you use Qt, it just feels more complicated to me. But it is something cool that we hope to be able to open source. Right now we're contractors, so it's been paid for by contract dollars, and so we can't release it at this time. But we're hoping that when we get it all buttoned away, that we'll be able to release it to the community and make it something that is useful and makes people's lives easier. So, thanks.
Thank you. See no other talks on the schedule, so I think we probably have oh, wait a minute.
I think Tom Rondeau, are you ready?
Okay, this is going to be our last lightning talk. Tom has a suit. Be very afraid.
Hello. Hey. Yeah, so late add to the schedule. So Tom Rondeau, I am now the principal director for Future G and 5G for the Pentagon. I used to be a DARPA program manager for about 6.5 years, and before that, I was the lead maintainer for GNU Radio for a number of years. Dubious honor of having actually started this conference. So when asked by Samantha if I would give a lightning talk, as a good DARPA program manager, I can't resist a microphone. So here I am. So what I wanted to go over, and I brought a cheat sheet because just in case I forget, is I want to talk about Star Trek. So if you're familiar enough with the Star Trek, film series, let's go back to the original series. You've got Star Trek: The Motion Picture. Who's seen the original Star Trek the motion picture. Not a whole lot of hands. We do have nerds in the audience, right? Okay. Really kind of dreadful movie. Star Trek II, The Wrath of Khan, like that was pretty fun, right? Star Trek III, The Search for Spock, again, pretty, yeah, I mean, we've seen it, but anybody like The Search for Spock? Yeah, that's what I thought, right? Star Trek IV, The Voyage Home, it's actually not bad. Star Trek V, The Final Frontier, has some good components to it, but really, you know, you get to the sixth one, Star Trek VI, The Undiscovered Country. That one I love, partly because it's got all the Shakespeare allusions in it and everything. But so what all these? What's the trend here, right? Only the even ones are good. That's been the running joke for Star Trek for a long time. So I'm the principal director for the DoD on 5G, and what I'm arguing here is that when it comes to cellular generations, only the even ones are good. All right, so you had the first generation amps. Again, I'm going to try to age the audience. Anybody here have an amps phone? Had an amps phone? Yep. Okay. I can. Yeah. Depends on the color of your hair. No offense, but pretty dreadful standard. But it worked, right? And what it did is it proved that there was a market for this, and it kind of created this market for mobile telecommunications. Then you go into 2G, GSM. I think we all have had some experience with GSM. It's still, in many cases, alive and well. We're starting to shut it down in various parts of the world, but it's still there. Brilliant standard. Economically, massive commercial success. Really made the idea of mobile voice communications a reality and work. And then we got into like text messaging, and that became a huge thing. And then people are like, oh, data over phones is really cool. Why don't we do 3G? 3G kind of, I have a lot of friends that worked in the industry. I don't want to badmouth it too much, but you know, there's a reason why we're talking about sunsetting 3G pretty quickly in a lot of places, maybe sometimes faster than 2G. 4G, though, made LTE, and that, I think, is a brilliant standard. Again, massive commercial success, economic, the trend line for what LTE has done for the industry is pretty phenomenal. Even to this day, when I see 5G show up on my phone, I go, maybe I'd almost rather go back to 4G. It's great. So 5G was really, what is 5G doing? 5G is all about this idea of differentiated services. It's if you think about spectrum or think about transport of data across a mobile system, what's that old Einstein quote? A telegraph is if you have if you pull a cat's tail in Los Angeles, you hear it meow in New York. Wireless telegraph is the exact same thing without the cat. So it's just transport of information across here. And if you do that, if you think about it, like a highway system, LTE is a highway for everything. It's the same type of highway for everything you want to do. It's like if I drove I-95 to connect Richmond and DC, and I also had to build I-95 to connect to your house. 5G allows you to differentiate why you need to build roads. So you can have service roads, access roads, driveways, in the backwoods, wherever you want to kind of give you the kind of service that you need for that different architecture. This is where the whole network function virtualization, software-defined networking comes in. So we can more specifically carve out spectrum and resources to enable things like the Internet of Things, IoT type, smart cities, all those things, smart warehousing, all those things that can actually be better use of that resource. Brilliant concept. But how well is our 5G working for us today? Now, of course, we're not really done with 5G. There's still some releases left and some work to be done there. But what I'm arguing here is that 6G is that next revolution. It's that we're proving out, we're revolutionizing the market in the odd generations, and we're going to use that to learn what those markets need and need to be sustainable, and that's what we're going to build towards. So my argument here, my talk today is just to try to give you some context for what you're seeing in the 5G world today, why I'm still super excited about it, because it's going to lead us into understanding what those markets are, what the next real laydown of a telecommunications network is going to look like across the world, and why, if you think through that economic aspect of those generations, the leadership that we've shown in building software and services on top of LTE, that's the kind of thing that I'd like to see us continue to focus on, those application areas for when we have that kind of real 5G, maybe we'll call it 6G at that point, laydown of a network, so we can continue to succeed in creating those services, those applications and technology that has been so successful, and thinking about those new ideas for the future. And so while I'm working for the Department of Defense, I obviously have a very focused aspect of what I care about with those application services, but national economic competitiveness is important to our national security. And so we're really investing in trying to make sure that that's also a part of this story and part of what we're doing. And I'll conclude with that, and hopefully will generate some conversation and a lot of questions for me later. I'll be around most of the week if you find me. So thank you, and I believe we're going into break. All right, great.
We're going to break. We have an extra 5 minutes for coffee, so we are back at 20 after.
first one was real cheap. Yeah, it was cheap. But we were in whichever one was good. It was just the plastic. He was on the faculty. Yeah. Yeah. I followed your interest in it. You're frequent on the chat list, the email list. Working on all the documentation. We'll give you a call out. Just let you know. Documentation is very helpful. Even for someone who's been around forever. Yeah. What instead of saying is that they're all going to do a change don't have some good. Hopefully those blocks are largely the same. That's kind of hopeful. Recording for yeah. You know, I'm correct. Yeah, I'm live. I had emailed about it.
You, okay.
Yeah, I'm trying to do live demos.
Okay.
At Canoe Radio
Then-
Conference. I know.
Not this then. So let's go.
Pull that one.
Pull this one. Put it back when you're done.
Okay.
Put it back and like hit this back. I'll let you know just so it's not get screen. It's like having trouble controlling this from the back. All right.
Okay.
Let's see if this works. Do you have audio in your demo?
No.
That's good. Sometimes works, sometimes doesn't. All right, so you got your PDF, but then you got live stuff.
Yes. Lots of live stuff.
Perfect.
Mostly live. See. Mine's boring without live.
Oh, yeah. Demo. All right.
I like talking
And
about it
then
more.
I'm gonna switch it.
Yeah. Well, it should be mirroring if you're live. Or actually, I'll drag it over to that. Well, yeah, let me. Okay, hang on. It's mirror. Should be mirrored now. Well, it was there. You were there for a second. Okay.
Welcome back from coffee. It is now 3:20 and time for Toby Flynn to tell us all about GR in Ocean. Please give him a warm welcome.
I'm Toby Flynn. I'm going to be talking about GR in Ocean. It's a new out-of-tree module for a commercial IoT protocol. Why did I choose this particular protocol to look into? So GR in Ocean is a developing commercial IoT standard, which is different than a lot of the other ones. It's designed specifically for low power type of platforms, like solar paneled IoT sensors that you would put up in a commercial building. I was actually in a hotel recently that had these types of sensors throughout the hotel, measuring its carbon dioxide and various air quality things throughout the hotel. So that's what it's designed for. They have a lot of variety of sensors. They have contact sensors, temperature, pressure, CO2, occupancy, but it's aimed at a commercial market. And they actually sell a developer kit, which I bought, that allows you to plug into a Aruba network and backhaul it all through Wi-Fi. So it's a developing standard, but it's different than your normal LoRa type standards. The other thing is, the nice thing is it's kind of a commercially available and open standard. All the documents for it are available publicly. You don't have to log in or create NDAs. And then, you know, from a security standpoint, they're adding security into this. Like I said, I found it unsecured in a hotel. Having a file layer implementation in GNU Radio could be fun to play with. And more importantly, I felt like it would be a fun thing to do. And I was just looking for something fun. So for the actual protocol, there are two basic protocols. There's the original one, which is simple ASK or OOK. And then they have a 120 kilohertz FSK. And I've only implemented the FSK because I can't find any ASKs. They were all only sold in Europe, and they have now moved on to their new standards, so you can't hardly find any of the old devices from that aspect. So what does it look like? Like I said, it's just a simple FSK, 62.5 kilohertz offset for the frequency deviation, 125 kilobits per second, with a lot of tolerances and various other standards. That's all part of the spec, which you can go find. It's the in Ocean Radio Protocol 2 document. So what does this look like when we're actually talking over the air FSK for these types of sensors? It's just the typical, you know, give it a second. There we go. So like I said, it's 62.5 kilohertz offset, which is something else just hit us. But what you get for being in ISM bands. But those two peaks that we had up were 62.5 kilohertz deviation, which is what you saw from the spec as far as the FSK is concerned. That's what you were expecting to see. Now for the frame structure, since you know that is just a straight up FSK. I originally thought this was going to be very complicated when I first started looking at the spec, then it turns out to be, no, it really is just a simple FSK. It does have a preamble, which is all ones and zeros, and then there's a sync word attached to it, and if you put it together, it's actually pretty good for locating it. So, you know, first thing I was doing was just playing with it, running it through just a simple quad demod to get out the bits, just for proof that I could actually find sort of where the signal's at. And if we go through and look, there's your 1 0 1 0 1 0 1 0, a couple of zeros at the end, the double ones, just like the synchronous pre-word. Yeah. Still, you're missing parts, right? This is for a full up demod. You need all the GSM Gaussian sync word. You need to have some other things put into it. From the wonderful tutorials that Barry has written, we have a nice documentation in the radio block, kind of shows you how to do all this stuff and set it all up. Oh, shucks. You already transmitted on me. So here, what we've done, or what I've done, is basically set it up with a correlate access tag, which is looking for the preamble that we'd mentioned earlier. And then it's just tagging it and sticking it in. The hardest thing for this is coming up with a sensitivity block for the GFSK, which is straight out of the documentation for the FSK modulation. And it ends up being pi over 2 times samples per second. Which is documented in the code as all places, but you know, it is nicely documented right here. A little bit different than what the documentation says, but the code was, because the documentation has it defaulting to a 1 for the Gaussian, you need to do this. So this is where the first custom block came into play. Basically, this is a tag header to PDU. The spec that we have back here in the documentation specifies that the header length is, the length of the entire packet is specified here. To give you an idea of these packets, roughly, most of the ones we're seeing are only 9 bytes long, which is 0.7 milliseconds of on-air time. So there's some of the bytes coming out of this particular sensor. Well, I actually have multiple sensors up here that are sending different bytes through, and you can see in the lower debug, from the debug printout, this is bytes. The last one here is a CRC check. We've passed all of that. We've checked the CRC at this point, and we're verifying everything. And then from here, that was the end of the spec that associates with all the radio frame. Then they have a gigantic spec for the serial interface to these modules. And they actually have a dongle that you attach that you can attach to a computer that will interface with the with all these sensors. There's some nice Python software that's out available on GitHub that interfaces to the dongle. As you can see, there's been some temperature values. So from one of the temperature sensors that's sitting up here, it's 20 degrees Celsius, or so it thinks. But here was another one who thought it was 30. I'm not going to tell you that the sensors are great. I'm just telling you what they're reading. And this is based on the dongle and this thing's from. So multiple sensors, it's either 22, 20, 30 degrees Celsius, something like that in here. So from the packets that we saw a minute ago, you'll notice that these all start with like A5 and 06A. But the packets that we found all started with 0A. So what it really is there's a header in here, but when they go, and then the 220412DB is the ID of the device sending it. When they come over to the serial LAN, they stick those toward the back. They don't leave them in the front anymore. So they're moving all the data around, they're shifting everything, and it's a very complex serial. And the interface to the serial, to the debugger, has to be put into the serial format that comes out. So, you know, the spec is available out there. It's on the Notion Serial website. And the radio packet format has to be modified. So on this one, you're starting to see now the complete packet. This is matching the USB dongle entirely, but we have a nice file layer implementation, all in GNU Radio. And what ended up happening was we ended up using basically 2 out-of-tree blocks, and everything else in here are just straight up GNU Radio blocks. They needed no modifications. All we had to do was do a little bit of tweaking on the frequency FSK sensitivity. Correlate access block was needed nothing changed to it. One thing to remember, you know, through the documentation it tells you, but the access code pulls the header out when it finds things. I'm hoping one of these other sensors will talk here in a minute. So you can see what the radio actually sees is here. And then in this case, it was one of the temperature sensors came through, and there's your 20.39 degrees Celsius that we were seeing with the dongle. And it's also showing up over here in the dongle. And of course, it crashes. It's all good and so what fun is it if you can't go ahead and try the transmit side? So we went ahead and I made a very simple block that all it's doing is replaying some various radio packets that I have found. I haven't tried to reverse the serial, didn't turn it back into those radio packets because that was already complicated enough to go the other way. But, you know, if you're wanting to do fuzzing attacks, once again, this is just straight up GNU Radio blocks. The only exception is, you know, once again, the sensitivity, getting it correct with the samples and the frequency deviation being functions of it. I've got a little demo set up. Had the demo set up. Working. That's all good live demos go. No, it's not. This particular one is sending out a GNOME packet. Which is the one that's ending in the 143 for the raw value on it, 17 degrees Celsius. It's a hard coded one. I happen to know what it is, so I can find it. I'm receiving it with the ENOcean USB dongle that is their radio interface, so proof that we are actually transmitting it live to the dongle and it is receiving it. So we have a way of doing a replay attack if we choose to do this. Or you can customize it. You can go in and play with the bits. It's a very simple Python replay block that it is just the actual bit values. So it would be fun to play fuzzing attacks. I just haven't had time to do it to see what happens when you do it. I know we can crash the, I have crashed the Python ENOcean serial debugger a lot playing with that. But I don't know how it actually affects the full system until I put it into something where you have the whole service going back through the Aruba network. But I do know that it will crash out of the open source code, which doesn't really mean much more than it crashes the open source code. And the code is available on GitHub. And does anybody have any questions?
I see no questions from the room, but I have two. One, is this part of the CTF? If not, when will it be part of the CTF?
Not part of the CTF? Up to the CTF organizer? It very well could be. Come see me. I will happily help with anything y'all need to make it part of the CTF.
Excellent. And just any advice for people looking to implement new out-of-tree modules to stand up new protocol support for the next weird RF thing that they come across?
The tutorials are very good, even for someone who's been in GNU Radio for a long time. I highly recommend using them. Also, it is open source. Use the source code. Leverage other people's blocks by all means. That's what the whole point of open source is. Sometimes the blocks, like, I had to write a couple of out-of-tree modules for very specific processing for that. But there's good examples, and I intentionally made one of our out-of-tree blocks is C++, the other one is Python. I have the message passing back and forth through all of that. Actually, is more of a test or a proof, but so we already knew GNU Radio did it, but it's more examples out there of both Python and C++, message passing, handling, going back and forth, streaming, and packet handling.
Thanks. Any other questions? Excellent.
I was just doing a quick Google search on ENOcean versus LoRa, and I was just wondering if you had any thoughts on the two IoT protocols.
So I have looked at LoRa a lot. I said I have looked at LoRa. It is so ENOcean is specifically targeted at IoT for commercial infrastructure. So they are setting themselves up, targeting with like Aruba Networks to backhaul their stuff. All of their sensors are relatively small. They pretty much all have little solar panels on them. So it's actually designed to be able to put into a room like this and hidden in the infrastructure and get all of its power off of the lights. They can have a battery backup, but it's not required. And they have they have switches on them for where they may only report once every 10 or 15 minutes. LoRa is, like LoRaWAN. So these are all 902, it's FSK, it's 125, it's relatively short range, in all honesty. LoRa, depending upon how you configure it, could be very long range, LoRaWAN. So it's really good for, I think, things where you're wanting more of, trying to think. So LoRa is a fairly open standard if you've ever tried to play with the LoRa sensors. It's all how you put together a module and how you configure it, and it gives you so many options. These options are really fixed, so it's really nice because they have multiple providers. It's almost like LoRaWAN, part of the LoRa network, but it's not really designed to need something out receiving it. A lot of the LoRaWAN has commercial people operating the LoRaWAN receivers. This one's designed that you put it in your own.
Farmer wants to know soil.
Farmer wants.
The LoRa is agricultural type of sensors, like the soil temperature, the barometric pressure, the air temperature, all the things that a farmer would need. And when you had mentioned that yours is based on solar power, just seemed like a fit. So I was just curious if any of the EnOcean sensors.
Yeah, I just picked EnOcean because it was fun. Not because I'm not an EnOcean salesman by any stretch. So I'm not trying to sell you the protocol. It was just fun. It was just, attacking and reversing an IoT for the sake of reversing an IoT standard. I'm not telling you that EnOcean's good for anything. Yeah, I do SDR, not IoT device manufacturing.
One more question from the internet was, when you were developing this module, did you come across any features that you thought were missing, either in the protocol or in GNU Radio itself?
The thing I had tried to use in GNU Radio that was really hard and led me to doing the custom block was, this is a simple header. The header structure is relatively simple. It has a preamble and a packet length. But trying to get that without writing a custom block to go pull that out and make the packet length based off of that, with the header implementation that's in GNU Radio, it seems like it's very fixed to the header that, like the D header, the header processor is made for the header that GNU Radio automatically puts on something. And trying to figure out how to do that part of it became hard, so I just wrote the custom block. But I did look into I was doing my best to use all standard GNU Radio blocks, but I was having a hard time, and someone else had mentioned earlier too, the packet header processing within GNU Radio is kind of hard to deal with.
Cool, thanks. All right, one more round of applause for this talk. Next up, we have a demonstration of a high data rate QPSK modem. Okay, David Miller is going to tell us about his high rate modem. Please give him a warm round of applause.
Okay, thanks. Well, hello, my name is Dave Miller, and this afternoon I am going to present my project on building a high data rate QPSK 15 megabit per second real-time GNU radio modem using just multi-cores of a general purpose processor in parallel. No FPGAs or graphics processor units are required to get up to this data rate for this project. So first, some background. Last year at the 2021 conference, I did provide a paper and talk on building really just a prototype modem to see if this was feasible at BPSK with 10 megabits per second. This year, I have an improved design with QPSK up to 15 megabits per second. I also created a GitHub site for all the documentation. Also, the Addertree code that's needed, test files, prepared files, and flow graphs. So basically, because of the stagnation of Moore's law in a single core, the chip industry, I really think, has moved forward with Moore's law via multi-cores. So I think we need to take advantage of multi-cores if we really want to increase the data rate capability of a GNU radio modem with just software. So for example, flow graphs and designs that take advantage of these multi-cores by putting them in parallel. So the purpose is to build a radio that can operate well beyond 6 megabits per second with GNU radio. Basically a design that uses multi-cores in parallel. Basically, it would break up the IQ stream coming in into overlapping chunks, basically the incoming stream from the dongle. Then it would process those chunks in parallel cores of the GPP. Then at the end, the trickiest part really is to restitch these parallel streams coming in back together again into the original transmitted frame stream. And we don't want any missing bits or missing frames, and we don't want any duplicates bits or duplicate frames due to this overlapping approach. So the scope exactly is 15.0 megabits per second for this project, and this modem, QPSK, at 15 megabits per second, the parallel multi-core approach. I used an inexpensive, low-cost Lenovo laptop with 8 cores. I used the GNU Radio 3.10.3 for this, the Ubuntu operating system, and a low-cost Lime SDR mini dongle. And that had a USB 3.0 interface for good speed. I did some test loops at 80 megahertz, and you can see the test configuration for those tests, for those loop tests at the bottom of this chart. And again, here's the GitHub site, design documents on there, flow graphs, relevant files like prepared test files, and of course the Addertree code. So this provides a flow graph, one flow graph for the whole modem, transmit and receive. I know the text is very small here, but what I'm going to do is zoom into pieces of this in later charts. But basically, the demodulator portion has 3 parts: the front end, the parallel synchronization chains, and a back end. Note for the Addertree blocks at the bottom of this figure, that is the only part that required Addertree blocks. I tried to use in-tree blocks as much as I could, except for the bottom part, which at the end, which is the tricky part, restitching everything back together again. And again, the GitHub site there with this flow graph and design documentation and test files is available. Also, I put together a paper for the conference, so you can see the paper that goes with this project also on the proceedings. Okay, I'm zooming into the test modulator now. That was at the top of the previous flow graph. What I used here was just a pre-modulated complex IQ file. I put it in the file source and transmitted that out. I did this just so the modulator only required 1 core for this project, and that left me with 7 more cores for the demodulator portion. The pre-modulated complex file that I used is also on the GitHub site. Okay, the first part of the demodulator, the front end, I'm zooming into that right now. Again, no out-of-tree blocks. Basically, what this part of the demodulator does, it breaks the incoming complex IQ stream into parallel overlapping chunk streams, the incoming single stream from the Lime SDR Mini. And then what it does is it adds a 1524 sample fixed pattern chunk preamble. And I'll talk about the chunks in more detail in the later charts. And the chunk preamble is added to each chunk so that I can go ahead and restitch these streams back together again. The chunk preamble is a key part of that. It has a marker in there to identify the different chunks downstream. That 1524 fixed pattern of samples is also on the GitHub site. And you could plug that into the file source block at the top of this flow graph in the middle. Okay, this is the demodulator front end again, but with a functional view. The top rectangle is the incoming stream of samples from the dongle. I chopped those up into chunks with a 12,000 sample overlap at the beginning of each chunk. So 12,000 sample overlap from chunk to chunk. And you could see that here in the figure in the 202, 206, and 209 of this figure. And I'll talk about that overlap more and the reasons for it in a couple charts. Okay, this is another functional view of the front end, but the second half where the chunk preamble is added to the beginning of each chunk. Each chunk is 82,000 samples. The chunk preamble is added to the front of each. So the chunk preamble has three parts. The first part is 960 bits, basically 1, -1, 1, -1, but in complex format. The next part is of the preamble is the marker. That's 64 samples. And again, the marker is used downstream to identify the beginning of each chunk so we can later put things back together again, restitch them. And the third part is just some 500 fill zeros. Okay, this is the second part of the demodulator, the parallel synchronization chains. Please read this right to left. And basically I have three chains for 3 chunk streams. This is where I do the parallel portion of the demodulator to get the speed way up. The symbol sync tends to be the bottleneck for a QPSK or BPSK modem with GNU radios. So trying to put those in parallel and do 3 of them at the same time. So the overlap, the reason for it here is that the symbols per every 82,000 chunk of samples could be a few symbols different for every 82,000 samples, maybe two samples per bit or per symbol, 41,000, but you might get 41,001 or 39,999 for another as it flows through the system. So we have some overlap there. Plus, every chunk that goes through, the symbol sync CASAS loop have to resync 2 times, one for the preamble and one for the chunk itself. So you lose bits or you get error bits during that sync process. So we need some overlap so we don't lose anything. Okay, this is the last part of the demodulator. This is the one that requires all the out-of-tree blocks or many of them. This is the back end. So basically, this part of the modem restitches those 3 parallel chains back together again into the original transmitted frame stream with no errors. These are the list of the blocks I use for out-of-tree. They're on the GitHub site also. I tried to really use even in-tree blocks for this and just modify them a bit and recompile them. For example, to look for a marker that might have 4 phases due to QPSK ambiguity, 45, 135, 225, and 315. I just used the correlate access code block that comes in the entry, but I modified it so it could look for 4 marker patterns for each of the different possible phases. Okay, this provides this chart a functional view again of the demodulator back end, the front part. What the blocks do is they identify the beginning of each chunk in the 3 different chains. I extract each chunk, and then I put all these chunks from the 3 streams back together again in a single stream. Everything's in order again, but the overlap still exists. We still need to handle that part. So that the second half of the back end and the last part of the modem, the demodulator really, read this right to left. We use the distance between ASM markers. If you look at 510 here in the figure above, if it has 4,192 bits, which is the frame length I'm using, the correct frame length, I pull it out, extract it, it continues on downstream. If the distance between markers is more than 4192, I identify that as some bad overlap bits, we pull it out. If it's really, that would be 511 in this figure. 507, if there's just a few bits between the markers, that I have to delete those bits, and also the frame after it, 508, even though it might be the correct 4192, as a duplicate frame. So those that are good are going downstream to the final part, which is the resolve phase block. And basically what I do there is I look at the bits in the ASM of the frame, look for the rotation. There'll be 4 possible patterns there due to the QPS ambiguity. And then I rotate the bits in the data field of the frame as required to match the ASM rotation. So everything coming out now should be the original frame stream that was transmitted, no duplicate bits, no duplicate frames, no errors in the bits. So what I did here is I took advantage of the built-in affinity setting that GNU Radio already has to assign the blocks to the cores. And that was very helpful, this GNU Radio affinity setting that's already available in every block. For example, the shaded rows here for the 3 parallel chunk chains for the symbol synchronizer and the Costas loop went to cores 4, 5, and 6. The core number is on the right column. The name of the block is in the left column. So the results in future work, this is the last chart. Basically, I was able to operate up to 15 megabits per second. I ran it maybe for about 15, 20 seconds. That test file is on the GitHub site also. It of course, becomes a very big file very quickly, but the demonstration was working well. I brought stuff with me, so maybe during the conference, if anyone's interested, I could get this thing up and running with the Lime SDR if there's an interest. Also, the paper that goes with this project for the conference has a lot more details also. And the GitHub site, again, has the outer tree code and more details and prepared test files. I also put a simulation flow graph into the GitHub site. So if you don't have a dongle and you've got 8 cores in your general purpose processor PC, you could still run this, and you should get to about 15 megabits per second. If you don't have 8 cores, only a few cores, you should still be able to run this. You'll just have to lower the data rate and not expect it to run as fast. So the future work, I think this is scalable to even higher data rates. Just add more cores, add parallel chains, add more of them. If I had 16 to 24 cores in a PC, and I think maybe that will be available with consumer desktops, or at least 24 cores maybe in the next year. You can add some coding and maybe do that in parallel, put together a real-time modulator, which might take a few cores to do, and higher data rates. So that pretty much is it. So everyone, well, thanks for your time.
Thanks. I didn't see any questions from the internet about this, but similar to the last talk, were there any features that you found missing in GNU Radio that should be added to make future work on projects like this simpler?
I'm sorry, what was that? That's from the internet?
There were no other questions from the internet, but we have one question from the room here.
Oh, okay, I wasn't sure where it was coming from.
So just a quick question. Have you tested this at low SNR values, and does it tolerate, that kind of performance or not?
Low SNRs, like if I were using coding and you were
Low levels on your signals, low signal levels.
Yes, I have put noise into this, and I could demonstrate that. I do have a noise block. I didn't show that in the flow graph. I have some, so I did test it at noise and kind of see how it performed when you're getting down there where some bit errors are popping up. Yes.
That's it. When using the symbol synchronization block, how did you, the recommended route is to empirically find those values unless you do a lot of research into what you're developing. So how did you match the symbol sync block to match your needs? What research did you do and how did it contribute to that block?
Okay. Yeah, I've used the symbol synchronizer before. Oh, I'm sorry, I'm not close enough to the mic. I have used the symbol synchronizer before and have looked for good parameters. I think some other folks have already done some also in past conferences, some good settings for that. I know, I don't know if Daniel Estevez is here. I know his GR Satellites is a great area. And I think he did like one or two conferences ago, a really good tutorial on setting up a lot of these blocks. So yes, it was a little trial and error getting that up and running first a few years ago when I first started using it. I didn't, it wasn't obvious. So hopefully there is some material on that from the past conferences. I did a talk 3 conferences ago where what parameters I found useful for that. And you can go to the flow graph on the GitHub site and you can see everything that I used to set it up. So if you just use those parameters, it should work for most cases, I think.
Cool. Similar question. I think your setup had a similar clock or the same clock for transmit. Transmit and receive. Have you tested it with Doppler or like changing phase offset and time offsets?
I didn't put any Doppler into this. So to really make this work with Doppler, like if you had a LEO spacecraft where you're moving along at a couple hundred hertz per second, you would have to put some blocks in the front of this to, even if you were doing something low data rate that's not in parallel, to kind of compensate for that Doppler. I have looked at that, and I do have something that that's up and running and working kind of on the side for a low data rate flow graph. So if you're interested, I could probably show you that offline. But you would need to compensate. You would need to maybe take an FFT of where your center frequency is, keep updating that, send that update into an entry block that does the sine, puts out a sine wave in complex form, and keep updating that based on your FFT to kind of keep yourself centered for the symbol synchronizer block. So it never sees that change, is the way I've seen maybe a possible path forward for like LEO Doppler.
Okay. Yeah, there might be a little bit of a different shift across each of the branches that's doing the parallel processing. So when you go to stitch it back together, it could be problematic even if you compensate up front, I think. But it'd be good to, for future work, add 2 clocks at least for transmit and receive.
I'm not quite sure I heard the question exactly.
Oh, the comment was it might be good for future work to add 2 clocks, one for transmit and one for receive. And
one for transmit and receive, kind of split this flow graph up. Yeah, that would probably be the best way forward. To operate the Lime SDR, I really needed just one. I don't think I could operate the one dongle with 2 flow graphs, so I stuck the modulator one in there. So that would work well. I'd probably just need 2 dongles to do that, maybe 2 Lime SDRs, one for a flow graph controlling the transmit one and one the receive. And as long as you have enough USB ports on your laptop or desktop, it would be a good way to go, sure.
And the last question goes to the internet. Which single block would gain most from hardware acceleration?
Which block? Definitely the symbol synchronizer is the block that's the most processing intensive, and that's why I need to go to, it's the bottleneck on the processing. If you just have that with one core, it's the limiting factor without doubt.
Thank you. All right, let's give one more big hand for this talk. And then in just a sec, we have an open source radio platform for enabling ORAN research. Okay, your slides are ready.
Thank you.
Thank you.
My name is Vuk Marevich. Good afternoon. I am associate professor at Mississippi State University. And today I'm going to talk about open source software radio platform that we built for enabling ORAN research, prototyping, and testing. Our mission is to provide an open platform for prototyping and testing artificial intelligence-based radio access network controllers. So it's about cellular network. In the context of cellular networks, we want to develop AI-based controllers for next-generation networks. These are my collaborators, professors at Mississippi State University, George Mason, and Virginia Tech. And just briefly, the outline, I will provide you the necessary background on ORAN to be able to follow this talk. Then I'll present our project called OpenAI Cellular, some software development and a sample project, and conclusions. So in terms of background, we're moving away from the traditional base stations that were monolithic. Everything was integrated on a cell tower. You had antennas on top, you had the cabinet on the bottom, right? And everything was local and proprietary. We're moving towards a bit more software-defined network where the cell towers could be in one spot, and with antennas, and the signal processing can be somewhere else. This means RAN desegregation. We're moving towards more flexible and programmable networks with open interfaces that make them programmable and flexible. So let me talk briefly about RAN desegregation. RAN stands for Radio Access Network. So the idea is to have the different parts of a base station disaggregated. You have the RF part, you have some lower layer, physical layer processing, you have MAC layer, you have other layers, and those can now be disaggregated across sites, locations, right? And the way it works is we define the radio unit, which has the RF front end, essentially, and can have some physical layer processing. We have the distributed unit, which can be someplace else, at the edge, for example. And we have the control unit that does higher layer control. This can be at regional servers or even in the cloud. The third generation partnership project, who standardizes all cellular network generations, offers us 8 options to split our base station. And so vendors can decide what they want to use. But ORAN specifically, ORAN stands for Open RAN and is standardized by the Open ORAN Alliance. They specifically use specific splits, the 7.2x split, which they call open front haul. So they have a little bit of 5-layer processing with the RF part, and the rest is in a distributed unit. And then they use a F1, the option 2 for the F1 interface between the distributed unit and the control unit. Beyond RAN desegregation, what does ORAN offer? ORAN obviously leverages the 3GPP protocols, but adds new features to it. The big features I want to talk about today are the RAN intelligent controllers, or RICs. There are 2 of them. One is called the non-real-time RIC. It is up there in the, It's up there in the service management orchestration part. It operates on data that is slowly processed and feedback that is given at 1 second or above. So the non-real-time RIC features the RApps. So an RAP is a microservice that actually implements some control algorithm to manage the network, right? To optimize the network, right? At slow timescales. Another big block is the near real-time rig, which operates at timescales between 10 milliseconds and 1 second, so near real time. And applications that can control your network or the users or the services are called the X apps. And then these new RAN intelligent controllers control the RAN, which is disaggregated, you can see it here, through open interfaces. The idea is that there are some interfaces that are standardized by 3GPP and some interfaces that are new to ORAN. The E2 interface is for ORAN management between the near real-time rig and the radio access network. So the X apps and R apps that I mentioned before, they can apply artificial intelligence to control the RAN. They don't have to, but this is an inbuilt option of ORAN. So how does it work? So you collect the context data, for example, from the RAN, from a radio access network, you get the key performance indicators. You collect those, put them in a database, or you use all the data to model your a training model of your AI. And this happens in non-real-time rig. This happens non-real-time and can happen offline. And then once the model is trained, you can adapt or control the network through the RAPs or XApps. So that was the background on ORAN. Let me talk about our project called Open Artificial Intelligence Cellular. This is what we want to accomplish. We want to use software radios. We want to use open source software that implements the RAN, 4G, 5G, and who knows, next G, right? And we want to integrate the ORAN framework around it so we can have non-real-time control and near real-time control and possibly real-time control of our RAN, employing artificial intelligence. So we use standard open source software, we use Ethos Research USRPs, and we leverage the ORAN Alliance specifications to do it right and compatible with others. Another part of the project is a testing framework. We call it OAI-CT. It's also based on AI. So the idea is if you have these intelligent RANs, where you have AI to control the RAN, to control the scheduling, control the admission of users, do traffic steering, handover, and whatnot. So these networks, the next generation networks, need to be tested properly, right, against all sorts of signals. So we have this framework that we're developing to generate test signals, test scripts, and test signals to test the network. So if you develop a new XApp that is based on AI or not, you can run our AI testing framework to verify it works in different conditions. And we also want to apply AI to the testing to learn about what signals to generate in order to test the performance of the network. And finally, the project itself is software-based, but we want to deploy it on real hardware, right? I mentioned USRPs. So we want to enable deployment on small test beds in your lab, or on big test beds like Virginia Tech's CoreNet, or platforms for advanced wireless research, the power platforms. So what we've done so far is we released our first code release. You see the GitHub. It's all on GitHub. It's all free and available. It's based on 5G NSA networks with ORAN interfaces. And you can use it with SDRs, with USRPs, or you can use it with ZMQ, with virtual radios. And along with our code, we also release documentation and also some videos to help you install and use our software. Okay, let me talk a little bit about the software development itself, a little bit more technical. So what is essential for developing an ORAN system? Well, I told you before, there are certain blocks that are new, that is the non-real-time rig and the near real-time rig, right? And there are new interfaces that need to be established for the non-real-time rig, in this case, to talk to the RAN, to get the parameters from the RAN and to send configuration commands to the RAN. For example, admit this user associated with this cell or that cell, right? So how we did it is we looked at the specifications, the ORAN Alliance. They standardize the ORAN protocol and the interfaces. So we looked at the interface specifications, copied what we need, compiled it with the ASN1 compiler for C, and then we can generate E2 messages to communicate between the near real-time rig and the RAN. And these E2 messages need to follow a certain format. It's all standardized or specified by the ORAN Alliance. There are IDs that need to be associated. There need to be nodes defined, etc., so that we can verify if this RAN belongs to the network or not and enable certain services. To give you an example, so once we have been able to identify what we need from a standard, compile it, now we have a near real-time rig on the left side that has this E2 termination that receives E2 messages, an E2 manager that manages it. And the right side, we implemented E2 agent. This is an endpoint that interacts with the RAN. So the communication goes between these two E2 endpoints, right? And then through that, we can access the RAN for getting parameters or for configuring the RAN to do something. So on the left side, again, you have the XApp development and execution environment. On the right side, you have the E2 agent and interfaces with the software radios. Now that we have the E2 interface, which is essential for doing near real-time rig to RAN control, we can develop XApps, or we can integrate existing XApps. So industry has been working ORAN for a while now and offers a lot of XApps already that we have integrated in our system. And they come from the ORAN software community, which is a consortium built of industry members, similar to 3GPP. And we also have from other contributors, for example, from Powder, Testbed, we use the NextRAN RAN slicing app. What we're doing now, we're developing our own XApps. One is Age of Information-based scheduler, another AI-enhanced scheduler, and many other XApps that we want to develop because our project is about AI control of next-generation networks. And looking beyond XApps, so XApps is quite popular, right? But looking beyond XApp, what we are interested in, and some of you may also be, is on AI control of the physical layer, or lower layers, right? For that, you need a faster cycle of control. So this is something that's currently not supported by ORAN, but we want to look into that and investigate it. And of course, the RApps, I mentioned them before. Those are the microservices that control the RAN at slower time scales. For example, set new policies or optimize sectors and whatnot. So this is a community project. We want to make it easy for community to use it and to contribute to it, right? So we provide all our source code open and for free download from a GitHub. We also want to make deployment easy, which is for you, so you can download. The goal is you can download a virtual machine that has all the software integrated, all dependencies met, so you can run this OpenAI cellular network on your own computer. If you have software radios, you can set up your own testbed. And finally, the deployment uses the typical tools that we have, like Git pull requests, right? Forking and committing and so forth, everything that you're used to. So for the reminder, let me talk about a recent project for XApp development. So what we're doing, what a student is doing, he's developing an XApp that does the user scheduling, user admission to a base station and scheduling. So what we have, as I showed you before, we have the RAN, the radio access network on one side with the E2 interface, and the other side we have the near real-time rig, which manages the E2 messages. So the near real-time rig also offers databases to store the data that you receive from the RAN. It has an XApp that's called KPI-Mon. This is developed by industry that we use to collect the key performance indicators from the RAN and store them in a database. And then the XApp that we want to develop is on the top that uses the data from the RAN processes it and makes decisions on which users to admit to what cell and how many resources to allocate to them. So for the scheduling XApp, we use reinforcement learning. You develop an agent that determines some actions to maximize the reward, and does this through observations from the environment. Okay, and to not spend much time, there's a paper you can read about the details, but the idea is for the RAN, which consists of multiple base stations, to allocate users, to associate users to certain base stations and give them as much throughput as possible. So here's an example of the results that we have. Instead of using a real-time system, we use the RAN simulator. We use some available RAN simulator and connected it to our near real-time rig to develop the XApp. And you can see here what we did. So we set up 5 base stations, we set up 10 users, and this RAN simulator provides the mobility model of the users. So what we do is, what the XApp does, right, is based on the KPIs that it receives, the channel state, and other things that it receives from the UEs. Then the base stations forward this to the XApp, and the XApp makes decisions which UEs to associate to which base station, how much bandwidth to allocate to them. What you see here is 2 snapshots, right? On the left is after a while, after 10 time slots, and on the right is after 20 time slots. You see the user mobility here. So after we develop the XApp properly in its environment of the near real-time rig, now we need to execute it in the proper real-time environment, right? So for that, we use the modified version of SRS-RAN with the E2 termination and with some modules changed so that it takes actually the actions from the XApp and changes its scheduling decisions. So you can see we can simulate for example, one base station and multiple users. We can use SDRs for that, so SDR hardware. We can also offer the use of virtual radios through ZMQ. So in this case, there's no SDR hardware involved, but still the real-time system. And we can use GNU Radio to generate a flow graph to connect the UEs to the base station properly. So this is our scheduling project. Now, more use cases for GNU Radio, as we see. Of course, GNU Radio is a fantastic tool for quick prototyping and testing with SDRs. For our project, what we envision is to collect IQ samples, for example, for AI model training and testing. We also want to use GNU Radio to create a variety of RF signaling environments. Let's assume future next generation networks, right, will not necessarily operate in licensed spectrum, right? They may operate unlicensed or shared spectrum. So we can create some of the, using easily GNU Radio to create some signals of other users that need to coexist in this band, and then let's see how the XApp or how the RAN adapts to that. We can also do interference, create interference, and do some security research, etc. And what I said, we also want to explore AI-enhanced physical layer modules in the context of ORAN, and we can prototype this with GNU Radio. Okay, I would like to conclude with this slide and ask you for your feedback or ask you for your research interests, and so we can work on these together and solve them together. Just to point you, we have a repository that's open and free. We have an email, you can contact anyone else, and we have a website that has a user survey. You can participate if you like, all links that you need to see what we have developed. And this is a project that just started, so we'll be doing this for another 2 or 3 years or more to get more features in and hopefully engage the community and work with you on that. That's all I have. Thank you.
Do we have any? Yes, we do have questions from the room.
How does this impact latency?
Good question. Latency sensitive applications are not yet supported by ORAN. You've seen it's above 10 milliseconds, right? So what you can do with XApps is you can do decisions that go in time frames of 10 millisecond delay, right? We haven't tested it, but I've seen some people looking at how quickly all the software works together and how quickly the data is moved. That's one aspect of latency. Another aspect of latency is the actual RAN disaggregation, right? So it's to be seen. 3GPP offers it. Industry seems to be picking up on it, but it's to be seen what gets disaggregated and how far away. Like with, remember Cloud RAN, right? So how much gets actually in the cloud or in the Cloud RAN and how much gets local? It remains to be seen. There is latency concerns, and that's also how you make a decision which split you want to choose for your system or application. Thank you.
One more question from the room.
Hello, many thanks. First of all, what RAN emulator you used?
Sorry, what?
For the one of your experiments, right? What RAN emulator did you use?
I forgot. It's something that I need to look it up. I'm so sorry.
Okay.
It's a simulator. It's a commercial simulator that allows you to simulate 10 or more UEs and so forth.
Okay. The second thing, so GNU Radio has is very reconfigurable, versatile, whatnot, has a bunch of ways you can reconfigure variables and parameters on the fly, right, over remote procedure calls and etc. Based on that, do you think there's any way or there be any benefit from expose this control over GNU Radio using service models in the ORAN ecosystem?
Well, dynamic things you need to pick up early, right? You can directly process at the physical layer, let's say modulation encoding scheme, right? You change that at a physical layer. But I see this more as a powerful tool for long-term optimization or near real time, as I said, right? And for the variables that change very quickly need to be, let's say, retransmissions. Decision need to be made quickly, right, to make it in time. This is what we need to explore still, and we want to explore to see if this is possible to use an AI model, train it properly and robustly to operate at these timescales.
One more question from the room.
Hello. You mentioned that you were trying to expand the physical layer access and that wasn't currently supported by the ORAN framework. I was wondering how you were developing XApps that get access to that raw IQ data.
Great question. So we won't use XApps. What we want to do is, or what people are not just us, but people are thinking about implementing the AI as part of the distributed units, not within the near real-time rig. A near real-time rig can control like hundreds of base stations, right? And thousands of users. But where the physical layer real-time control might need to happen is closer to the physical layer, obviously, closer to the, let's say, antennas. I think it should happen probably co-located with the DUs, the distributed units, right, where the physical layer is implemented. So it wouldn't be XApps. People call them DApps or another name, right?
So how do you actually get, like if it's not supported by ORAN, how are you actually getting access though to that IQ?
Well, for us, it's easy because we use open source software.
Okay,
So
so you're
everything
just
is,
rewriting
the full stream is open source, SRS, OAI, whatever you like. And everything is in software. You just plug in the USRP. Everything is in open software.
Okay, so you're rewriting those ORAN modules. So
Yeah,
that
we will work on open source project, but for industry depends. Like I think what someone envisions is that the RU will be the hardware, right? And it can be multiple vendors, not just a single or a few. And then the rest will be implemented in software. Proprietary or open, we'll see.
Cool, thank you very much.
Thank you.
I don't see any other questions from the room, so thank you again. And we have a few minutes before our next talk, a flexible architecture for monitoring public safety communications.
Should I go ahead and get started?
If you want to start now, we can, or we can wait a few minutes.
I guess I'll go ahead and get started now. Last presentation of the day. Thank you for sticking around, everyone. I promise I will get through this as quickly as possible so that we can all achieve our goal of going out to the hotel bar and having some cold drinks. I'm Aaron Rossetto, and I'm very pleased and honored to be able to talk to you about some work that I've been doing in my spare time, which with a 4-year-old and nearly a 2-year-old amounts to about 3.5 minutes per day. Who am I? I'm a former NI employee. I maintained UHD for the last couple of years. I presented a couple of times at GRCon, in fact, and I've got links there. That's a picture of me, by the way, from Charlotte, where GRCon 2021 was, one afternoon when I ran off and had to go to a brew pub and decompress a little bit. And I've also presented at some GRCon related things. And I put links in here because I will be touching on some of the topics that I spoke about in these presentations as part of this presentation. So if you want to go into more depth on some of these things, I encourage you to go take a look at these. But I've also been a long-time SDR and public safety monitoring enthusiast. And I don't presume that everybody understands what public safety monitoring really is. But in short, it's simply listening to first responders in your community as they respond to situations. For me, it is for entertainment purposes, whether it's informational, if you're maybe one of those good government types trying to see where your tax dollars are going, making sure, keeping police in check and whatnot. It's basically being able to listen to their communications and the equipment and techniques that are used to do so. So what does that entail? How exactly do you go about monitoring these public safety systems? Well, first of all, you need to know what frequencies to monitor for the agencies of interest. And back in the day, you could buy books that were based on location with lists of frequencies for police, fire, EMS, state police, road crews, etc. But these days, you're more likely to go to an online database like Radio Reference, which has all of that information plus a lot more, including mapping of talk group IDs to all of the users on trunked radio systems and so on. And so once you know the frequencies that you want to listen, you sit in front of your receiver and you jog the tuning knob back and forth and you have a great time, right? No, it doesn't quite work like that. In fact, that would kind of be a pain in the butt. So there is a specialized receiver known as a scanner that have been around for quite a while. And by the way, I just love this picture from the 1978 Radio Shack catalog, that vision of domesticity where they're sitting around reading the newspaper and doing some knitting in front of a roaring fire, and they've got their tabletop scanner and listening to what's going on in their community. But scanners get their name because they have a list of channels or frequencies that they are programmed with or set up with, and they go through and tune each one and stop when there is traffic on that channel. So when there's a user who is transmitting, the speaker unmutes, you listen to the communication, and as soon as that communication is over, the scanner resumes what it's doing. And you got those very lovely tabletop models on the left and some more mobile models on the right. And these ones required crystals. So you had to go down to your local Radio Shack and say, I'd like to order the following crystals. And presumably they would come in a week or so. And you plug them in, and there you go. Now you can monitor your local public service agencies. Since the 1980s, however, with microprocessors being ubiquitous in everything and digital synthesizers, scanners became a lot more flexible, and now all you had to do is really punch the frequency in that you wanted to listen to, and it would do the rest. Scanners around that time started to add features for monitoring trunked radio systems, which is a whole other ball of wax, and is described more in depth in one of those presentations that I linked to at the beginning. of these slides. And the state of the art for scanners look like these sophisticated devices with touch screens. They don't list frequencies anymore. They just tell you who's talking and what groups they belong to. A lot of features there, very feature rich, great things that you can do with them. They're wonderful. But for the truly adventurous, there are also computer-based solutions. So Unitrunker is one piece of software that's used for monitoring trunked radio systems. DSD Plus is another. There's SDR Trunk. There's quite a few of them out there if you've got the tech savvy to be able to set it up and to do all the configuration. And then this is something I came across a few weeks ago. Somebody took a Steam Deck and they grafted on a USB hub and a couple of RTL SDRs and turned that into a trunked radio monitoring solution. And the first thing I thought of when I saw this was, well, is this really a scanner? But yes, it is, and it looks like it's running SDR trunk. So, you know, good for that person, I suppose. But in my mind, all of these options have some deficiencies associated with them. And really what it boils down to is they don't work the way I want it to, right? Scanners are made for broad audiences, and so they have to serve most of the common use cases. There's not a lot of customization that you could do. Some of them allow serial port control, but it's very, very basic. On the other side, computer-based scanners are difficult to configure, definitely for novices, but even for seasoned hobbyists. You need to have a computer, and you may need specific knowledge and a tool set if you wanted to do any sort of customization. And then, like I said, in both cases, they make design choices that don't serve my particular needs. And so all of this was in my mind when I think about the ideal scanner for me. And I've presented this slide before at a few venues, which is what I envision a DIY open source trunked radio scanner to look like. I'd thought of an SDR connected to a Raspberry Pi, an amplifier and a speaker in a box that would then be controlled headlessly through some sort of web-based, mobile-friendly UI. And with this much computing power, there's a lot that you can do, a lot of customization, a lot of different use cases that you can serve with this that is limited mainly by your imagination. And of course, it would be written in GNU Radio, and it would be wonderful. So keep that in the back of your mind as I present this work that I've been doing, because it is my baby steps towards implementing this dream scanner. When I think about the goals that I want to have around a customized scanning solution, it's really flexibility trumps everything else. I basically separate the notion of the front end, which is all the radio bits, from the back end, which is the business logic, and I want flexibility on both those sides. The front end typically doesn't change too much, especially if you've got one particular system or type of system that you want to monitor, but it's the back end that changes quite a bit. And I wanted to decouple that as much as possible from the front end so I could rapidly iterate on changes without having to go back into GNU Radio Companion and change the front end just because I wanted to change something in the back end. The other thing I wanted to do too was insulate the person implementing the business logic as much as possible from the communication protocol, because the person writing a scanner application typically doesn't care if they see these messages on the control channel. What they really want is a notification that a user is on this frequency now, right? And then to do something in response to that. And then I also wanted to make sure that I used a language that had a really rich library ecosystem so that, if I thought of a really interesting user interface or user experience that I wanted to implement, that I would have a set of tools or libraries at the ready that I could use to quickly prototype these things. And so with that, I created the very boringly named GR Scanner, where GR stands for GNU Radio, not grandpa, as you might infer from this picture. Although this is a really quintessential grandpa picture. If you look in the back, you could see the guy's fireplace mantle, and he's got a box of remote controls on top of that. And then he's got his little scanner table beside his easy chair with a towel over the arm of it, and then what looks like ointments in a bucket on the table as well. Just had to point that out. But what GR Scanner is a GNU Radio module that simplifies the creation of these customized, listener-oriented monitoring solutions. So this is really meant for consumption by human beings, although that's not necessarily a requirement of a monitoring system, right? You could dump all this stuff to disk, but really the intent is to be able to easily create these monitoring applications for listening and for human consumption of trunked, specifically P25 trunked radio systems. So as I mentioned before, I split the application into the notion of this front end, which is the radio, and the back end, the business logic. The front end is a GNU Radio flow graph that looks like a million of other flow graphs that you've seen, but is designed to support multiple simultaneous channel acquisition. So that, for example, you could have a control channel and a separate traffic channel, or if you had the computing and SDR resources, you could maybe have all of the channels of a particular tower all being fed in to the back end at the same time. The back end, being the business logic, is a Python module that's designed to be completely decoupled from GNU Radio and from the front end flow graph, where the common language of data exchange between the two are JSON messages. Because they're well supported in Python, they're easy to parse with the eye. It's just a pretty flexible way to communicate data in a fairly standardized way. Before I go any further, though, I want to be very clear that a lot of the code that is in the GR Scanner out-of-tree module is based very, very heavily on the OP25 project. And I want to make sure that I acknowledge those authors because they did a lot of the hard work of writing a lot of the P25 framing and 4-level slicing code that I used as part of my project, again, in an effort to accelerate my development. So I want to make sure that they get kudos, as well as to all of the other contributors to GNU Radio, UHD, CMake, all of the wonderful open source packages that go into making this possible. All right. What I want to do now is take a look at what the front end looks like, and it's pretty wide when you look at it in GNU Radio Companion. So I've broken it up across a couple of screens here. On the left-hand side are blocks that run in the RF NOC domain. And I was doing my prototyping on a USRP E310, and one of its benefits is it's got an FPGA in it that into which you can deploy processing blocks known as RF NOC blocks. And unfortunately, the E310 is a relatively small FPGA on it. There's not a lot that you can do there, but what I did in the FPGA was to take the radio block, which tunes 10 megahertz of spectrum around a center frequency, splits that stream of IQ data, and connects those two streams to down converter blocks so that I can tune part of that 10 megahertz spectrum down to baseband. And one of those streams represents the trunked system control channel. The other stream represents the traffic channel of interest. The RF NOC RX streamer crosses the bridge between the RF NOC domain and the GNU Radio domain. So everything from this point on is now running on the CPU. The remainder of the flow graph, again, there's nothing really special here. This looks like a pretty standard common narrowband monitoring application. The highlighted modules are one that GR Scanner offers. So there's a 4-level slicer because the P25 protocol is this 4-level FSK encoded signal, and the P25 frame decoder takes in an array of die bits, so basically characters 0, 1, 2, 3, representing the sliced 4-level FSK data, and outputs messages that are those decoded P25 data units. And those go into sort of the first novel block, I think, of this whole effort, not very interestingly, again, called the front end interface. But the front end interface is what helps keep the front end and the back end decoupled. So on the left-hand side of the block are input ports, and on the right-hand side are output ports. And this block has two main responsibilities. The first is to instantiate, load a Python module and instantiate a class based on one of the named, or a couple of the named parameters to this block. The second responsibility that it has is it accepts, I say here PDUs, but I think I should be saying PMTs. I tend to confuse those two terms. But it accepts those PMTs and turns those into function calls on the backend class, so that the backend doesn't need to include any GNU Radio dependencies in order to do its work. Whenever a message comes in, it just turns into a method call on the back end. And similarly, if the back end wants to send data up into the front end for, say, tuning either the control or the traffic channel, it can do the same thing by calling a function that is provided by the front end interface that does that conversion and communication. And the other thing that it does, minor but nice thing, is that that input channel list and output channel list parameters are comma-separated names to assign to these ports. And as you add more items to these lists, the number of ports on the block increases, and they're by default called in0, in1, in2, in3. This is just a nice facility to be able to map one of those very generic port names into something that's a little bit more meaningful for the application. So the way that this front-end interface works in my P25 scanner application is that these JSON strings from the P25 framers come into the ports on the left-hand side and invoke the receive PDU method on the loaded module, sorry, the class, the instantiated class of the loaded module with the name of the port and then basically the data that was in that PMT. And similarly, if I wanted to control the offsets of the DDCs, the radio gain, or the frequency, I can call from my backend class, send PDU function, giving it the friendly name of the port, and then data that basically gets converted into a PMT. So the bulk of the work that went into this is in the class called P25 Scanner. It's well, class and module. It has no GNU Radio dependencies, but it's a base class that is intended to handle most of the common trunk system decoding tasks. It will configure the front end to tune to the middle of a set of frequencies that represent a tower of interest. It will interpret the trunked control channel messages and call user-defined functions on whatever subclasses this class. It decodes the digital voice packets and sends just raw PCM data down to the subclass, so it doesn't have to do any of the hard codec work. And it also accepts trunked radio system files that you can download from Radio Reference if you have a membership, and it parses those files and provides the subclass access to that data as dictionaries. So you don't have to do all the hard work of decoding trunked group number 2468 into, you know, City Patrol North or something, because that is part of what this class is intended to do. And so as you can imagine, you would subclass P25 Scanner and implement all of your application-specific behaviors within that subclass. So one thing I'm particularly proud of, I don't know if I should be, I wanted to talk about this, is one of the worst parts about decoding these digital radio systems is, you know, you've got all these different message types. You can go download the specs, but then you have to decode them, right? So you have to look at the 12 bytes of the trunk signaling message block, and then look at the opcode, and then depending on the opcode, there's a number of different fields in there. And writing all the bit shifting and comparison stuff is a real pain in the butt. So what I ended up doing was creating what I call the decoder ring, which is a map of these P25 control system message names to a list of fields associated with that message and decoders for each of those fields. And those decoders can be in one of two forms. It can either be a list of byte offsets, masks, and shifts for each field, which is very common stuff that you need to do to extract the value of these fields from the raw packets. Or it can be a lambda function where for some fields, the data is encoded in a specific way and we want to do a transformation on that before we call into the subclass. And the example I'll give here is the frequency field of the OSP group voice channel grant isn't a frequency in terms of megahertz, it's a channel number. And so to convert that channel number to frequency, you need to have seen some other messages from the control channel, and that's what that self.system.channel to frequency function does. So you need a little bit of extra support in these decoders. We'll just provide a callable. And then what happens is once all of the data for the message is decoded, it tries to call a function in the subclass with that message's opcode name. So it will try to call a function OSP GRP V channel grant, and then each of the things in the decoder ring turns into a separate parameter on that function. Now, try that in C++. And I'm a longtime C++ programmer, and I'm trying to get better with Python. And when I realized you could do stuff like this, it was mind-blowing. This is really powerful and goes towards that goal of accelerating my own development and prototyping of these different applications. Okay, the backend also includes an IMBE audio decoder. Again, this code came from OP25. It's a fixed point implementation. It's not the greatest sounding, but it's definitely armchair copy, and probably due to the fact that it's a fixed point implementation that's meant to be relatively efficient. I did have some thoughts about running this within the USRP E310 instead of on a separate host connected to the SDR. I never got that far though. But again, what the code does is it decodes those packets, turns it into PCM data, and calls a subclass method with just raw 16-bit samples at 8 kilohertz, which you can then stream to disk, play through dev DSP, or what have you. And then there's one other thing that I added called the out-of-process proxy, which allows that instantiated class to run in a separate process, which is then connected to the main GNU Radio flow graph process via pipes. So those calls to receive PDU and the calls back, the send PDU function callback, are proxied across these pipes. So you can run your code essentially in a completely different process, thus further creating that separation between the front end flow graph and the back end business logic. And so what I did with all of the stuff that I put together was to create a proof of concept that inches towards this do-it-yourself open source trunk radio scanner with a mobile web-based interface. And it's written completely in Python. It's pretty basic, but what it can do is show you real-time site activity with all of the users on a given tower. It can monitor audio from those channels. You can choose to lock out or prioritize specific talk groups that you want to listen to, which is table stakes for commercial scanners, by the way. And then it also provides a nice visual feedback of the signal quality, basically how well is it able to decode these control channel and traffic channel messages. Essentially, it's meant to be a playground so that I could start implementing user interface ideas that really appeal to me and the way that I monitor these systems and what I want to hear. The architecture looks like this. The left-hand side of this diagram is the GNU Radio process. It's the front end interface, and then the out-of-process proxy that sends all of the control channel and traffic channel messages through pipes to the scanner server process. That server process reads in metadata that I downloaded from Radio Reference with all of the different sites and talk groups of the system that I monitor most frequently. It then spawns a Python web server process that serves up static presentation data to the mobile client, right? So the mobile client connects to the web server, gets the HTML, CSS, and hilariously bad JavaScript because I don't like writing JavaScript, but then opens another connection to a port that is opened by the scanner server process that's sharing WebSockets messages. And that WebSockets message link sends events and PCM data between the server process and the mobile client. So hopefully we'll get some audio here. I took a couple of minutes of video of me playing with this thing. Doesn't look like there's going to be any video here, I guess. That's kind of unfortunate. But what you would see, if you could see this video, is traffic that is being monitored. So as traffic is noticed on frequencies of the tower, a new row opens up. So you'll see these rows being created in the web page that indicate which talk group is on the frequency, who owns that talk group, you know, what it maps to. The green background means that it's monitoring that channel, so you'll hear audio when somebody's transmitting. And then when you click the row, you get a set of buttons that say lock out this talk group or prioritize this talk group. And a locked out talk group shows up in gray, indicating that if it's encountered, it won't play. And then pressing priority, I think, puts a little star beside the name to indicate that's kind of a favorite. So you get a pretty nice experience, a pretty intuitive, user-friendly experience for monitoring these systems, and you can do it sort of from the comfort of your mobile phone. Oh wait, it will play. Awesome. Okay, great. I'm glad I hit that button. So what you can see is rows being added as traffic is detected on the frequencies of this given tower. The green highlighted line is what's currently playing. It's the Austin Water Plant talk group. And I think at some point here, I click one of these rows, and you can see what happens when I click on a row. It opens up this sort of drawer of buttons underneath it any moment now. Yeah, there it is. So I can click lockout group, and that group is now turned gray, meaning that it's locked out, and if it's eligible to be listened to, it won't play. And I just prioritized TCSO Adam. So, you know, Adam, Baker, Charlie. So Adam is the West Patrol of the Travis County Sheriff. So it's Travis County Sheriff, Adam West. I thought that was kind of funny. And so you can kind of imagine how you can pretty quickly create a really intuitive and flexible user interface without having to write a lot of custom code because it was provided there in the base class. And you can see the flashing heart at the top indicating that it's seeing frame syncs and that the radio is actually working. And then those two quality bars that indicate basically how well the decoder is able to error correct and whether the CRCs match it and whatnot. It's sort of a proxy for the signal quality. Whoops. I did not mean to do that. This is one of those Macs. How do I make this big? How do I embiggen this? That's sort of play. Well, that's no. That'll teach me for touching somebody else's computer. Anyway, we'll go back to the slides. This is all up on GitHub. There's the link there. It's pretty rough right now, I'm not gonna lie. Like I said, I don't have a lot of free time to play with this. And I'm prioritizing pace over perfection, so I know there's a lot of deficiencies with it. But there's a lot of fun things that you could do with it. It's USRP E310 specific right now, as I mentioned, but there's nothing saying that you couldn't rewrite that front end. It wouldn't take a lot of work to support RTL SDRs or AirSpies or Lime SDR or what have you, as long as you get enough bandwidth from it that it's able to sort of see all of the frequencies in the tower of interest at once. And you don't need those FPGA-based DDCs. You know, there's blocks in tree GNU radio blocks that do basically the same thing in the CPU. So there's a couple of potential areas that I list here for feature additions, areas of improvement. The repo needs some TLC. The JavaScript code is particularly hilarious. So yeah, that's basically it. If you're interested, I invite you to take a look. And so if you're, driving around town and you stop to have a drink and you see some guy sitting outside with his laptop that's got a Spectrum display on it and an antenna and a beer, that's probably me. So stop by and say hello. And that's it. Thank you very much.
Unless you're hanging around someplace in the Caribbean, in which case it might be me.
Pardon me, I missed that.
Oh, in which case, unless you're hanging out in the Caribbean and you see somebody with a radio and a spectrum analyzer, and that might be me. Any questions from the room? Otherwise, this is really exciting. We might have some updates on the CTF scoreboard. Excellent. Scores are going up. They're very exciting. Martin, I think you want to tell us about it.
Yeah. So I'm actually going to close out. I'm just going to start. Is this on the screen? No. Can you, who's ever, can this laptop be? All right. Yeah. So remember there was a CTF going on and a couple of teams have been pretty active. And I don't want to, I could spend ages here. So you can see the score going up for a bunch of teams. A lot of these people are known here in this community, but what's cool is a bunch of these people aren't actually here. So I think Danny Estevez is pretty much, he's definitely not here. And I think he's in the lead right now. And we have Aerospace, Jeff Long, our maintainer, nice. I'm guessing this might be Ben, just based on the, I'm not sure. Yeah, so congrats to all the people in the lead, but the conference is going on for a while. And I think if I go here, I might see the actual, can I see the, where do I see? Oh, here we are. Yeah, so it's nice to see some of our sponsors actually participating, like Rampart Communications, that's cool. I guess that's their bread and butter. I don't know if are these my fellow NIS? I'm not quite sure. That's pretty nice. Rick Sanchez, yeah, I don't know who that is, but I just like the reference. And let's see who's right at the bottom. We have M7TWS, RNL, and Natalie. Go Natalie, whoever you are. I'm sure these guys are gonna catch up. So yeah, cool. Thanks for everyone for participating. Anyway, before we close out, I just want to say this is the end of the organized program today. So I think the expo people are already shutting down. So with the end of this talk, that'll be the end of GRCon, the official program. But then you obviously need to have dinner. So as you go out for dinner, look around in the lobby if there's other people who might want to join you. The official program is over, but that doesn't mean the unofficial part is over. So yeah, if you can find some like-minded people to to join you for dinner, that'll spark some nice conversations. Chat? Yeah, so GNU Radio Chat is a great place to coordinate, especially if you're here by yourself. You should not be having dinner by yourself. If you're having dinner by yourself tonight, unless that's what you really want, that'd be sad. We don't want that. So yeah, go on chat, see who else is going somewhere. Everyone's having food somewhere, so please join it. And well, finally, thanks for all the presenters today. And yeah, I'd like to give one final round of applause for all the presenters today, and that'll be the last thing. Okay. See you guys tomorrow.